Learn SQL for analytics. Vlad is a data engineer, and in this course he covers both the theory and the practice so you can confidently solve hard SQL challenges on your own. No previous experience required, and you'll do everything in your browser using BigQuery.
Hi everyone, my name is Vlad and I'm a data engineer. Welcome to Intuitive SQL for Analytics. This here is the main webpage for the course. You will find it in the video description, and this will get updated over time with links and resources, so be sure to bookmark it. Now, the goal of this course is to quickly enable you to use SQL to analyze and manipulate data. This is arguably the most important use case for SQL. And the practical objective is that by the end of this course, you should be able to confidently solve hard SQL problems of the kind that are suggested during data interviews. The course assumes no previous knowledge of SQL or programming, although it will be helpful if you've worked with spreadsheets such as Microsoft Excel or Google Sheets, because there's a lot of analogies between manipulating data in spreadsheets and doing it in SQL. And I also like to use spreadsheets to explain SQL concepts. Now, there are two parts to this course, theory and practice. The theory part is a series of short and sweet explainers about the fundamental concepts in SQL. And for this part, we will use Google BigQuery. BigQuery, which you can see here, is a Google service that allows you to upload your own data and run SQL on top of it. So in the course, I will teach you how to do that and how to do it for free. You won't have to spend anything. And then we will load our data and we will run SQL code. And besides this, there will be drawings, and we will also be working with spreadsheets and anything it takes to make the SQL concepts as simple and understandable as possible. The practice part involves doing SQL exercises, and for this purpose I recommend this website, PostgreSQL Exercises. This is a free and open source website where you will find plenty of exercises and you will be able to run SQL code to solve these exercises, check your answer, and then see a suggested way to do it. So I will encourage you to go here and attempt to solve these exercises on your own. However, I have also solved 42 of these exercises, the most important ones, and I have filmed explainers where I solve the exercise, break it apart, and then connect it to the concepts of the course. So after you've attempted the exercise, you will be able to see me solving it and connect it to the rest of the course. So how should you take this course? There are actually many ways to do it, and you're free to choose the one that works best. If you are a total beginner, I recommend doing the following. You should watch the theory lectures and try to understand everything. And then once you are ready, you should attempt to do the exercises on your own on the exercise website that I've shown you here. And if you get stuck or after you're done, you can watch how I solved the exercise. But like I said, this is just a suggestion, and you can combine theory and practice as you wish. And for example, a more aggressive way of doing this course would be to jump straight into the exercises and try to do them. And every time that you are stuck, you can actually go to my video and see how I solved the exercise. And then if you struggle to understand the solution, that means that maybe there's a theoretical gap, and then you can go to the theory and see how the fundamental concepts work. So feel free to experiment and find the way that works best for you. Now, let us take a quick look at the syllabus for the course. So getting started, this is a super short explainer on what SQL actually is. And then I teach you how to set up BigQuery, the Google service where we will load our data and run SQL for the theory part. The second chapter, writing your first query. So here I explain to you how BigQuery works and how you can use it, and how you are able to take your own data and load it in BigQuery so you can run SQL on top of it. And at the end of it, we finally run our first SQL query. Chapter 3 is about exploring some essential SQL concepts. So this is a short explainer of how data is organized in SQL, how the SQL statement works, meaning how we write code in SQL. And here is actually the most important concept of the whole course, the order of SQL operations. This is something that is not usually taught properly and a lot of beginners miss, and this causes a lot of trouble when you're trying to work with SQL. So once you learn this from the start, you will be empowered to progress much faster in your SQL knowledge. And then finally, we get into the meat of the course. This is where we learn all the different components in SQL, how they work and how to combine them together. So this happens in a few phases. In the first phase, we look at the basic components of SQL. So these are, there's a few of them. There's select and from. There's learning how to transform columns, the where filter, the distinct, union, order by limit. And then finally, we see how to do simple aggregations. At the end of this part, you will be empowered to do the first batch of exercises. Don't worry about the fact that there's no links yet. I will add them, but this is basically involves going to this PostgreSQL exercises website and going here and doing this first batch of exercises. And like I said before, after you've done the exercises, you can watch the video of me also solving them and breaking them down. Next, we take a look at complex queries, and this involves learning about subqueries and common table expressions. And then we look at joining tables. So here is where we understand how SQL tables are connected with each other and how we can use different types of joins to bring them together. And then you are ready for the second batch of exercises, which are those that involve joins and subqueries. And here there are 8 exercises. The next step is learning about aggregations in SQL. So this involves the group by, the having and window functions. And then finally, you are ready for the final batch of exercises, which actually bring together all the concepts that we've learned in this course. And these are 22 exercises. And like before, for each exercise, you have a video from me solving it and breaking it apart. And then finally, we have the conclusion. In the conclusion, we see how we can put all of this knowledge together, and then we take a look at how to use this knowledge to actually go out there and solve SQL challenges, such as the ones that are done in data interviews. And then here you'll find all the resources that are connected to the course. So you have the files with our data, you have the link to the spreadsheet that we will use, the exercises and all the drawings that we will do. This will definitely evolve over time as the course evolves, so bookmark this page and keep an eye on it. That was all you needed to know to get started, so I will see you in the course. If you are working with SQL or you are planning to work with SQL, you're certainly in great company. In the 2023 Developer Survey by Stack Overflow, there is a ranking of the most popular technologies out there. If we look at professional developers, where we have almost 70,000 responses, we can see that SQL is ranked as the 3rd most popular technology. SQL is certainly one of the most in-demand skills out there, not just for developers, but for anyone who works with data in any capacity. And in this course, I'm going to help you learn SQL the way I wish I would have learned it when I started out on my journey. Since this is a practical course, we won't go too deep into the theory. All you need to know for our purposes is that SQL is a language for working with data. Like most languages, SQL has several dialects. You may have heard of PostgreSQL or MySQL, for example. You don't need to worry about these dialects because they're all very similar. So if you learn SQL in any one of the dialects, you'll do well on all the others. In this course, we will be working with BigQuery, and thus we will write SQL in the Google SQL dialect. Here is the documentation for Google BigQuery, the service that we will use to write SQL code in this course. You can see that BigQuery uses Google SQL, a dialect of SQL which is ANSI compliant. ANSI compliant means that Google SQL respects the generally recognized standard for creating SQL dialects, and so it is highly compatible with all other common SQL dialects. As you can read here, Google SQL supports many types of statements, and statements are the building blocks that we use in order to get work done with SQL. And there are several types of statements listed here. For example, query statements allow us to retrieve and analyze and transform data. Data definition language statements allow us to create and modify database objects such as tables and views. Whereas data manipulation language statements allows us to update and insert and delete data from our tables. Now in this course, we focus exclusively on query statements, statements that allow us to retrieve and process data. And the reason for this is that if you're going to start working with BigQuery, you will most likely start working with this family of statements. Furthermore, query statements are in a sense the foundation for all other families of statements. So if you understand query statements, you'll have no trouble learning the others on your own. Why did I pick BigQuery for this course? I believe that the best way to learn is to load your own data and follow questions that interest you and play around with your own projects. And BigQuery is a great tool to do just that. First of all, it is free, at least for the purposes of learning and for the purposes of this course. It has a great interface that will give you really good insights into your data. And most importantly, it is really easy to get started. You don't have to install anything on your computer. You don't have to deal with complex software. You just sign up for Google Cloud and you're ready to go. And finally, as you will see next, BigQuery gives you many ways to load your own data easily and quickly and get started writing SQL right away. I will now show you how you can sign up for Google Cloud and get started with BigQuery. So it all starts with this link, which I will share in the resources, and this is the homepage of Google Cloud. And if you don't have an account with Google Cloud, you can go here and select Sign In. And here you need to sign in with your Google account, which you probably have, but if you don't, you can go here and select Create Account. So I have now signed in with my Google account, which you can see here in the upper right corner, and now I get a button that says Start Free. So I'm going to click that, and now I get taken to this page, and on the right you see that the first time you sign up for Google Cloud, you get $300 of free credits so that you can try the services, and that's pretty neat. And here I have to enter some extra information about myself, so I will keep it as is and agree to the terms of service and continue. Finally, I need to do the payment information verification. So unfortunately, this is something I need to do even though I'm not going to be charged for the services, and this is for Google to be able to verify my identity. So I will pick individual as account type and insert my address. And finally, I need to add a payment method. And again, I need to do this even though I'm not going to pay. I will actually not do it here because I don't intend to sign up, but after you are done, you can click Start My Free Trial and then you should be good to go. Now, your interface may look a bit different, but essentially, after you've signed up for Google Cloud, you will need to create a project. And the project is a tool that organizes all your work in Google Cloud. And essentially, every work that you do in Google Cloud has to happen inside a specific project. Now, as you can see here, there is a limited quota of projects, but that's not an issue because we will only need one project to work in this course. And of course, creating a new project is totally free. So I will go ahead and give it a name. And I don't need any organization, and I will simply click on Create. Once that's done, I can go back to the home page for Google Cloud, and here, as you can see, I can select a project, and here I find the project that I have created before, and once I select it, the rest of the page won't change, but you will see the name of the project in the upper bar here. Now, although I've created this project as an example for you, for the rest of the course, you will see me working within this other project, which was the one that I had originally. Now, I will show you how you can avoid paying for Google Cloud services if you don't want to. So from the home page, you have this search bar over here, and you can go here and write billing and click payment overview to go to the billing service. Now here on the left, you will see your billing account, which could be called like this or have another name. And clicking here, I can go to Manage Billing Accounts. Now here, I can go to my Projects tab and I see a list of all of my projects in Google Cloud. And a project might or might not be connected to a billing account. If a project is not connected to a billing account, then Google won't be able to charge you for this project. Although keep in mind that if you link your project with a billing account and then you incur some expenses, if you then remove the billing account, you will still owe Google Cloud for those expenses. So what I can do here is go to my projects, and on actions, I can select disable billing in case I have a billing account connected. Now, while this is probably the surest way to avoid incurring any charges, you will see that you will be severely limited in what you can do in your project if that project is not linked to any billing account. However, you should still be able to do most of what you need to do in BigQuery, at least for this course. And we can get more insight into how that works by going to the BigQuery pricing table. So this page gives us an overview of how pricing works for BigQuery. I will not analyze this in depth, but what you need to know is that when you work with BigQuery, you can fundamentally be charged for two things. One is compute pricing, and this basically means all the data that BigQuery scans in order to return the results that you need when you write your query. And then you have storage pricing, which is what you pay in order to store your data inside BigQuery. Now, if I click on compute pricing, I will go to the pricing table, and here you can select the region that most reflects where you are located. and I have selected Europe here. And as you can see, you are charged $6.25 at the time of this video for scanning a terabyte of data. However, the first terabyte per month is free. So every month you can write queries that scan 1 terabyte of data and not pay for them. And as you will see more in detail, this is more than enough for what we will be doing in this course, and also for what you'll be doing on your own in order to experiment with SQL. And if I go back to the top of the page and then click on storage pricing, you can see here that again, you can select your region and see several pricing units, but here you can see that the first 10 gigabytes of storage per month is free. So you can put up to 10 gigabytes of data in BigQuery and you won't need a billing account, you won't pay for storage, and this is more than enough for our needs in order to learn SQL. In short, BigQuery gives us a pretty generous free allowance for us to load data and play with it, and we should be fine. However, I do urge you to come back to this page and read it again, because things may have changed since I recorded this video. To summarize, go to the billing service, check out your billing account, and you have the option to decouple your project from the billing account to avoid incurring any charges, and you should still be able to use BigQuery. But as a disclaimer, I cannot guarantee that things will work just the same at the time that you are watching this video. So be sure to check the documentation or maybe discuss with Google Cloud support to avoid incurring any unexpected expenses. Please do your research and be careful in your usage of these services. For this course, I have created an imaginary dataset with the help of ChatGPT. The dataset is about a group of fantasy characters, as well as their items and inventories. I then proceeded to load this data into BigQuery, which is our SQL system. I also loaded it into Google Sheets, which is a spreadsheet system similar to Microsoft Excel. This will allow me to manipulate the data visually and help you develop a strong intuition about SQL operations. I'm going to link a separate video which explains how you can also use ChatGPT to generate imaginary data according to your needs, and then load this data in Google Sheets or BigQuery. I will also link the files for this data in the description, which you can use to reproduce this data on your side. Next, I will show you how we can load the data for this course into BigQuery. So I'm on the homepage of Google Cloud and I have a search bar up here, and I can write BigQuery and select it from here, and this will take me to the BigQuery page. Now, there is a panel on the left side that appears here if I hover, or it could be fixed. And this is showing you several tools that you can use within BigQuery. And you can see that we are in the SQL workspace, and this is actually the only tool that we will need for this course. So if you're seeing this panel on the left, I recommend going to this arrow in the upper left corner and clicking it so you can disable it and make more room for yourself. Now, I want to draw your attention to the Explorer tab, which shows us where our data is and how it is organized. So I'm going to expand it here. Now, data in BigQuery and in SQL in general exists in the form of tables. And a table looks just like this. As you can see here, the customers table. It is a collection of rows and columns, and it is quite similar to a spreadsheet. So this will be familiar to you if you've ever worked with Microsoft Excel or Google Sheets or any spreadsheet program. So your data is actually living in a table, and you could have as many tables as you need in BigQuery. There could be quite a lot of them. So in order to organize our tables, we use datasets. For example, in this case, my data is a dataset which contains the table customers and employee data. And a dataset is just that. It's a collection of tables, and it's similar to how a folder works in a file system. It is like a folder for tables. Finally, in BigQuery, each dataset belongs to a project. So you can see here that we have two datasets, SQL course and my data, and they both belong to this project, Idyllic Physics and so on. And this is actually the ID of my project. This is the ID of the project that I'm working in right now. The reason the Explorer tab shows the project as well is that in BigQuery, I'm not limited to working with data that lives in my project. I could also, from within my project, query data that lives in another project. For example, the BigQuery public data is a project that is not mine, but it's actually a public project by BigQuery. And if I expand this, you will see that it contains a collection of several datasets, which are in themselves collections of tables, and I would be able to query these tables as well. But you don't need to worry about that now, because in this course, we will only focus on our own data that lives in our own project. So this, in short, is how data is organized in BigQuery. Now, for the purpose of this course, I recommend creating a new dataset so that our tables can be neatly organized. And to do that, I can click the three dots next to the project ID over here and select Create Dataset. And here I need to pick a name for the dataset. So I will call this Fantasy, and I suggest you use the same name, because if you do, then the code that I share with you will work immediately. Then, as for the location, you can select multi-region and choose the region that is closest to you. And finally, click on Create Dataset. So now the dataset Fantasy has been created, and if I try to expand it here, I will see that it is empty because I haven't loaded any data yet. The next step is to load our tables. So I assume that you have downloaded the zip file with the tables and extracted it on your local computer. And then we can select the action point here next to the Fantasy dataset and select Create Table. Now, as a source, I will select Upload. And here I will click on Browse and access the files that I have downloaded. And I will select the first table here, which is the characters table. The file format is CSV, so Google has already understood that. And scrolling down here, I need to choose a name for my table. So I will call it just like the file, which is characters. And very important, under schema, I need to select auto detect. And we will see what this means in a bit. But basically this is all we need. So now I will select create table. And now you will see that the characters table has appeared under the Fantasy dataset. And if I click on the table and then go on preview, should be able to see my data. I will now do the same for the other two tables. So again, create table, source is upload, file is inventory, repeat the name, and select auto detect. And I have done the same with the third table. So at the end of this exercise, the fantasy dataset should have 3 tables, and you can select them and go on preview to make sure that the data looks as expected. Now our data is fully loaded and we are ready to start querying it within BigQuery. Now let's take a look at how the BigQuery interface works. So on the left here, you can see the Explorer, which shows all the data that I have access to. And so to get a table in BigQuery, first of all, you open the name of the project, and then you look at the datasets that are available within this project. You open a dataset, and finally you see a table such as characters. And if I click now on characters, I will open the table view. Now in the table view, I will find a lot of important information about my table in these tabs over here. So let's look at the first tab, Schema. The Schema tab shows me the structure of my table, which, as we shall see, is very important. And the schema is defined essentially by 2 things: the name of each column in my table and the data type of each column. So here we see that the characters table contains a few columns such as ID, name, guild, class, and so on. And these columns have different data types. For example, ID is an integer, which means that it contains natural numbers, whereas name is string, which means that it contains text. And as we shall see, the schema is very important because it defines what you can do with the table. And next, we have the Details tab, which contains a few things. First of all is the table ID, and this ID represents the full address of the table. And this address is made up of 3 components. First of all, you have the ID of the project, which is, as you can see, the project in which I'm working, and is the same that you see here on the left in the Explorer tab. The next component is the dataset that contains the table, and again you see it in the Explorer tab. And finally you have the name of the table. This address is important because it's what we use to reference the table, and it's what we use to get data from this table. And then we see a few more things about the table, such as when it was created, when it was last modified. And here we can see the storage information. So we can see here that this table has 15 rows, and on the disk it occupies approximately 1 kilobyte. If you work extensively with BigQuery, this information will be important for 2 reasons. Number 1, it defines how much you are paying every month to store this table. And number 2, it defines how much you would pay for a query that scans all the data in this table. And as we have seen in the lecture on BigQuery pricing, these are the 2 determinants of BigQuery costs. However, for the purpose of this course, you don't need to worry about this because the tables we are working with are so small that they won't put a dent in your free monthly allowance for using BigQuery. Next, we have the Preview tab, which is really cool to get a sense of the data, and this basically shows you a graphical representation of your table, and as you will notice, it looks very similar to a spreadsheet. So you can see our columns, the same ones that we saw in the Schema tab: ID, name, guild, and so on. And as you remember, we saw that ID is an integer column, so it can only contain numbers. Name is a text column. And then you see that this table has 15 rows, and because it's such a small table, all of it fits into this graphical representation. But in the real world, you may have tables with millions of rows, and in this case, the preview will show you only a small portion of that table, but still enough to get a good sense of the data. Now, there are a few more tabs in the table view. We have lineage, data profile, data quality, but I'm not going to look at them now because they are like advanced features in BigQuery and you won't need them in this course. Instead, I will run a very basic query on this table. And this is not for the purpose of understanding the query, that will come soon. It is for the purpose of showing you what the interface looks like after you run a query. So I have a very basic query here that will run on my table, and you can see that the interface is telling me how much data this query will process. And this is important because this is the main determinant of cost in BigQuery. Every query scans a certain amount of data and you have to pay for that. But as we saw in the lecture of BigQuery pricing, this table is so small that you could run 1 million or more of these queries and not exhaust your monthly allowance. So if you see 1 kilobyte, you don't have to worry about that. So now I will click run and my query will execute, and here I get the query results view. This is the view that appears after you have successfully run a query. So we have a few tabs here, and the first tab that you see is results, and this shows you graphically the table that was returned by your query. So as we shall see, every query in SQL runs on a table and returns a table. And just like the preview tab showed you a graphical view of your table, the results tab shows you a graphical view of the table that your query has returned. And this is really the only tab in the query results view that you will need on this course. The other ones show different features or more advanced features that we won't look at, but feel free to explore them on your own if you are curious. But what's also important in this view is this button over here, Save Results, which you can use to export the result of your query towards several different destinations, such as Google Drive or local files on your computer in different formats, or another BigQuery table, a spreadsheet in Google Sheets, or even copying them to your clipboard so that you can paste them somewhere else. But we shall discuss this more in detail in the lecture on getting data in and out of BigQuery. Finally, if you click on this little keyboard icon up here, you can see a list of shortcuts that you can use in the BigQuery interface. And if you end up running a lot of queries and you want to be fast, this is a nice way to improve your experience with BigQuery. So be sure to check these out. We are finally ready to write our first query, and in the process we will keep exploring the fantastic BigQuery interface. So one way to get started would be to click this plus symbol over here so that we can open a new tab. Now, to write the query, the first thing I will do is to tell BigQuery where the data that I want lives. And to do that, I will use the from clause. So I will simply write from, and my data lives in the fantasy dataset and in the characters table. Next, I will tell SQL what data I actually want from this table. And the simplest thing to ask for is to get all the data. And I can do this by writing select star. Now my query is ready, and I can either click run up here, or I can press Command Enter on my Mac keyboard, and the query will run, and here I get a new tab which shows me the results. Now the results here are displayed as a table, just as we saw in the preview tab of the table, and I can get an idea of my results, and this is actually the whole table because this is what I asked for in the query. There are also other ways to see the results which are provided by BigQuery, such as JSON, which shows the same data but in a different format, but we're not going to be looking into that for this course. One cool option that the interface provides is if I click on this arrow right here in my tab, I can select split tab to right, and now I have a bit of less room in my interface, but I'm seeing the table on the left and the query on the right, so that I can look at the structure of the table while writing my query. For example, if I click on schema here, I could see which columns I'm able to reference in my query, and that can be pretty handy. I could also click this toggle to close the Explorer tab temporarily if I don't need to look at those tables, so I can make a bit more room, or I can reactivate it when needed. I will now close this tab over here, go back to the characters table, and show you another way that I can write a query, which is to use this query command over here. So if I click here, I can select whether I want my query in a new tab or in a split tab. Let me say in new tab. And now BigQuery has helpfully written a template for a query that I can easily modify in order to get my data. And to break down this template, as you can see, we have the select clause that we used before, we have the from clause, and then we have a new one called limit. Now the from clause is doing the same job as before. It is telling BigQuery where we want to get our data. But you will notice that the address looks a bit different from the one that I had used. Specifically, I used the address fantasy.characters. So what's happening here is that fantasy.characters is a useful shorthand for the actual address of the table. And what we see here that BigQuery provided is the actual full address of the table, or in other words, it is the table ID. And as you remember, the table ID indicates the project ID, the dataset name, and the table name. And importantly, this ID is usually enclosed by backticks, which are a quite specific character. Long story short, if you want to be 100% sure, you can use the full address of the table and BigQuery will provide it for you. But if you are working within the same project where the data lives, so you don't need to reference the project, you can also use this shorthand here to make writing the address easier. And in this course, I will use these two ways to reference a table interchangeably. I will now keep the address that BigQuery provided. Now the limit statement, as we will see, is simply limiting the number of rows that will be returned by this query. No more than 1000 rows will be returned. And next to the select, we have to say what data we want to get from this table. And like before, I can write star, and now my query will be complete. Before we run our query, I want to draw your attention to this message over here. This query will process 1 kilobyte when run. So this is very important because here BigQuery is telling you how much data will be scanned in order to give you the results of this query. In this case, we are returning all the data in the table. Therefore, all of the table will be scanned. And actually, limit does not have any influence on that. It doesn't reduce how much data is scanned. So this query will scan 1 kilobyte of data. And the amount of data that is scanned by the query is the primary determinant of BigQuery costs. Now, as you remember, we are able to scan up to 1 terabyte of data each month within the Sandbox program. And if we wanted to scan more data, then we would have to pay. So the question is, how many of these queries could we run before running out of our free allowance? Well, to answer that, we could check how many kilobytes are in a terabyte. And if you Google this, the conversion says it's 1 to multiplied by 10 to the power of 9, which ends up being 1 billion. Therefore, we can run 1 billion of these queries each month before running out of our allowance. Now you understand why I've told you that as long as you work with small tables, you won't really run out of your allowance and you don't really have to worry about costs. However, here's an example of a query that will scan a large amount of data. And what I've done here is I've taken one of the public tables provided by BigQuery, which I've seen to be quite large, and I have told BigQuery to get me all the data for this table. And as you can see here, BigQuery says that 120 gigabytes of data will be processed once this query runs. Now, you would need about 8 of these queries to get over your free allowance. And if you had billing connected to BigQuery, you could also be charged money for any extra work that you do. So be very careful about this, and if you work with large tables, always check this message over here before running the query. And remember, you won't actually be charged until you actually hit run on the query. And there you have it. We learned how the BigQuery interface works and wrote our first SQL query. It is important that we understand how data is organized in SQL. So we've already seen a preview of the characters table, and we've said that this is quite similar to how you would see data in a spreadsheet. Namely, you have a table, which is a collection of rows and columns, and then in this case, on every row, you have a character, and for every character, you have a number of information points, such as their ID, their name, their class, level, and so on. The first fundamental difference with a spreadsheet is that if I want to have some data in a spreadsheet, I can just open a new one and insert some data in here, right? So ID, level, name, and so on. And then I could say that I have a character ID 1 who is level 10 and his name is Gandalf. And this looks like the data I have in SQL. And I could add some more data as well. A new character, ID 2, level 5, and the name is Frodo. Now I will save this spreadsheet, and then some days later, someone else comes in, let's say a colleague, and they want to add some new data, and they say, oh, ID is unknown, level is 20.3, and the name here, and then I also want to show their class, so I will just add another column here and call this mage. Now, spreadsheets are of course extremely flexible because you can always add another column and write in more cells, and you can basically write wherever you want. But this flexibility comes at a price, because the more additions we make to these to the data model that is represented here, the more complex it will get with time, and the more likely it will be that we make confusions or mistakes, which is what actually happens in real life when people work with spreadsheets. SQL takes a different approach. In SQL, before we insert any actual data, we have to agree on the data model that we're going to use. And the data model is essentially defined by two elements: the name of our columns and the data type that each column will contain. For example, we can agree that we will use 3 columns in our table: ID, level, and name. And then we can agree that ID will be an integer, meaning that it will contain whole numbers. Level will be an integer as well, and name will be a string, meaning that it contains text. Now that we've agreed on the structure, we can start inserting data on the table, and we have a guarantee that the structure will not change with time. And so any queries that we write on top of this table, any sort of analysis that we create for this table will also be durable in time, because it will have the guarantee that the data model of the table will not change. And then if someone else comes in and wants to insert this row, they will actually not be allowed to. First of all, because they are trying to insert text into an integer column. And so they are violating the data type of the column, and they are not allowed to do that. In level, they are also violating the data type of the column, because this column only accepts whole numbers, and they're trying to put a floating point number in there. And then finally, they are also violating the column definition, because they're trying to add a column class that was not actually included in our data model and that we didn't agree on. So the most important difference between spreadsheets and SQL is that for each SQL table, you have a schema, and as we've seen before, the schema defines exactly which columns our table has and what is the data type of each column. So in this case, for the characters table, we have several columns, and here we can see their names. And then each column has a specific data types, and all the most important data types are actually represented here. Specifically, by integer, we mean a whole number, and by float, we mean a floating point number. String is a piece of text. Boolean is a value that is either true or false, and timestamp is a value that represents a specific point in time. All of this information, so the number of columns, the name of each column, and the type of each column, they constitute the schema of the table. And like we've said, the schema is assumed as a given when working in SQL, and it is assumed that it will not change over time. Now, in special circumstances, there are ways to alter the schema of a table, but it is generally assumed as a given when writing queries, and we shall do the same in this course. And why is it important to keep track of the data type? Why is it important to distinguish between integer, string, boolean? The simple answer is that the data type defines the type of operations that you can do to a column. For example, if you have an integer or a float, you can multiply the value by 2 or divide it and so on. If you have a string, you can turn that string to uppercase or lowercase. If you have a timestamp, you can subtract 30 days from that specific moment in time, and so on. So by looking at the data type, you can find out what type of work you can do with a column. The second fundamental difference from spreadsheets is that spreadsheets are usually disconnected, but SQL has a way to define connections between tables. So what we see here is a representation of our three tables, and for each table you can see the schema, meaning the list of columns and their types. But the extra information that we have here is the connection between the tables. So you can see that the inventory table is connected to the items table and also to the characters table. Moreover, the characters table is connected with itself. Now, we're not going to explore this in depth now because I don't want to add too much theory. We will see this in detail in the chapter on joins. But it is a fundamental difference from spreadsheets that SQL tables can be clearly connected with each other. And that's basically all you need to understand how data is organized in SQL for now. You create a table, and when creating that table, you define the schema. The schema is the list of columns and their names and their data types. You then insert data into these tables, and finally you have a way to define how the tables are connected with each other. I will now show you how SQL code is structured and give you the most important concept that you need to understand in order to succeed at SQL. Now this is a SQL statement. It is like a complete sentence in the SQL language. The statement defines where we want to get our data from and how we want to receive this data, including any processing that we want to apply to it. And once we have a statement, we can select Run and it will give us our data. Now, the statement is made up of building blocks, which we call clauses. And in this statement, we have a clause for every line. So the clauses that we see here are select, from, where, group by, having, order, and limit. And clauses are really the building blocks that we assemble in order to build statements. What this course is about is understanding what each clause is and how it works, and then understanding how we can put together these clauses in order to write effective statements. Now, the first thing that you need to understand is that there is an order to writing these clauses. You have to write them in the correct order, and there is no flexibility there. If you write them in the wrong order, you will simply get an error. For example, if I were to take the where clause and put it below the group clause, you can see that I'm already getting an error here, which is a syntax error. But you don't have to worry about memorizing this now, because you will pick up this order as we learn each clause in turn. Now, the essential thing that you need to understand, and that slows down so many SQL learners, is that while we are forced by SQL to write clauses in this specific order, this is not actually the order in which the clauses are executed. If you've interacted with another programming language such as Python or JavaScript, you're used to the fact that each line of your program is executed in turn from top to bottom, generally speaking, and that is pretty transparent to understand. But this is not what is happening here in SQL. To give you a sense of the order in which these clauses are run, on a logical level, what SQL does is that first it reads the from, then it does the where, then the group by, then the having, then it does the select part. After the select part, it does the order by, and finally the limit. All of this just to show that the order in which operations are executed is not the same as the order in which they're written. In fact, we can distinguish three orders that pertain to SQL clauses, and this distinction is so important to help you master SQL. The first level is what we call the lexical order, and this is simply what I've just shown you. It's the order in which you have to write these clauses so that SQL can actually execute the statement and not throw you an error. Then there's the logical order, and this is the order in which the clauses are actually run logically in the background. And understanding this logical order is crucial for accelerating your learning of SQL. And finally, for the sake of completeness, I had to include the effective order here, because what happens in practice is that your statement is executed by a SQL engine, and that engine will usually try to take shortcuts and optimize things and save on processing power and memory. And so the actual order might be a bit different because the clauses might be moved around in the process of optimization. But like I said, I've only included it for the sake of completeness, and we're not going to worry about that level in this course. We are going to focus on mastering the lexical order and the logical order of SQL clauses. And to help you master the logical order of SQL clauses or SQL operations, I have created this schema. And this is the fundamental tool that you will use in this course. This schema, as you learn it progressively, will allow you to build a powerful mental model of SQL that will allow you to tackle even the most complex and tricky SQL problems. Now, what this schema shows you is all of the clauses that you will work with when writing SQL statements. So these are the building blocks that you will use in order to assemble your logic. And then the sequence in which they're shown is corresponding to the logical order in which they are actually executed. And there are three simple rules for you to understand this schema. The first rule is that operations are executed sequentially from left to right. The second rule is that each operation can only use data that was produced by operations that came before it. And the third rule is that each operation cannot know anything about data that is produced by operations that follow it. What this means in practice is that if you take any of these components, for example, the having component, you already know that having will have access to data that was produced by the operations that are to its left. So aggregations, group by, where, and from. However, having will have absolutely no idea of information that is produced by the operations that follow. For example, window or select or union, and so on. Of course, you don't have to worry about understanding this and memorizing it now, because we will tackle this gradually throughout the course. And throughout the course, we will go back to the schema again and again in order to make sense of the work we're doing and understand the typical errors and pitfall that happen when working with SQL. Now, you may be wondering why there are these two cases where you actually see two components stacked on top of each other. That being from and join, and then select and alias. These are actually components that are tightly coupled together, and they occur at the same place in the logical ordering, which is why I have stacked them like this. In this section, we tackle the basic components that you need to master in order to write simple but powerful SQL queries. And we are back here with our schema of the logical order of SQL operations, which is also our map for everything that we learn in this course. But as you can see, there is now some empty space in this schema because to help us manage the complexity, I have removed all of the components that we will not be tackling in this section. Let us now learn about from and select, which are really the two essential components that you need in order to write the simplest SQL queries. Going back now to our data, let's say that we wanted to retrieve all of the data from the characters table in the fantasy dataset. Now, when you have to write a SQL query, the first question you need to ask yourself is, where is the data that I need? Because the first thing that you have to do is to retrieve the data, which you can then process and display as needed. So in this case, it's pretty simple. We know that the data we want lives in the characters table. Once you've figured out where your data lives, you can write the from clause. So I always suggest starting queries with the from clause. And to get the table that we need, we can write the name of the dataset, followed by a dot, followed by the name of the table. And you can see that BigQuery has recognized the table here. So I have written the from clause and I have specified the address of the table, which is where the data lives. And now I can write the select clause. And in the select clause, I can specify which columns of the table I want to see. So if I click on the characters table here, it will open in a new tab in my panel. And as you remember, it shows me here the schema of the table. And the schema includes the list of all the columns. Now I can simply decide that I want to see the name and the guild. And so in the select statement here, I will write name and guild. And when I run this, I get the table with the 2 columns that I need. And one neat thing about this, I could write the columns in any order. It doesn't have to be the original order of the schema, and the result will show that order. And if I wanted to get all of the columns of the table, I could write them here one by one, or I could write star, which is a shorthand for saying, please give me all of the columns. So this is the corresponding data to our table in Google Sheets. And if you want to visualize select in your mind, you can imagine it as vertically selecting the parts of the table that you need. For example, if I were to write select guild and level, this would be equivalent to taking these 2 columns over here and selecting them. Let us now think of the logical order of these operations. So first comes the from, and then comes the select. And this makes logical sense, right? Because the first thing you need to do is to source the data. And later you can select the parts of the data that you need. In fact, if we look at our schema over here, from is the very first component in the logical order of operations, because the first thing that we need to do is to get our data. We have seen that the select clause allows us to get any columns from our table in any order. But the select clause has many other powers. So let's see what else we can do with it. One useful thing to know about SQL is that you can add comments in the code, and comments are parts of text which are not executed as code. They're just there for you to keep track of things or explain what you are doing. So I'm going to write a few comments now. And the way we do comments is by doing dash dash. And now I'm going to show you aliasing. Aliasing is simply renaming a column. So I could take the level column and say as character level, provided a new name. And after I run this, we can see that the name of the column has changed. Now, one thing that's important to understand as we now start transforming the data with our queries is that any sort of change that we apply, such as in this case, we change the name of the column, it only affects our results. It does not affect the original table that we are querying. So no matter what we do here moving forward, the actual table, fantasy characters, will not change. All that will change are the results that we get after running our query. And of course, there are ways to go back to fantasy characters and permanently change it, but that is outside the scope for us. And going back to our schema, you will see that alias has its own component and it happens at the same time as the select component. And this is important because, as we will see in a bit, that it's a common temptation to use these aliases, these labels that we give to columns, in the phases that precede this stage, which typically fails because, as our rules say, every component does not have access to data that is computed after it. So something that we will come back to. Now, another power of select that we want to show is constants. And constants is the ability of creating new columns which have a constant value. For example, let's say that I wanted to implement a versioning system for my characters. And I would say that right now, all the characters I have are version 1. But then in the future, every time I change a character, I will increase that version. And so that will allow me to keep track of changes. I can do that by simply writing 1 over here in the column definition. And when I run this, you will see that SQL has created a new column and it has put 1 for every row in that column. This is why we call it a constant column. So if I scroll down, all of it will be 1. And this column has a weird name because we haven't provided a name for it yet, but we already know how to do this. We can use the aliasing command to call it version. And here we go. So in short, when you write a column name in the select statement, SQL looks for that column in the table and gives you that column. But when instead you write a value, SQL creates a new column and puts that value in every row. The next thing that SQL allows me to do is calculations. So let me call the experience column here as well and get my data. Now, one thing I could do is to take experience and divide it by 100. So what we see here is a new column, which is the result of this calculation. Now, 100 is a constant value, right? So you can imagine in the background, SQL has created a new column and put 100 in every row, and then it has done the calculation between experience and that new column, and we get this result. And in short, we can do any sort of calculation we want, combining current columns and constants as will. For example, although this doesn't make any sense, I could take experience, add 100 to it, divide it by character level, and then multiply it by 2. And we see that we got an error. Can you understand why we got this error? Pause the video and think for a second. I am referring to my column as character level. But what is character level really? It is a label that I have assigned over here. Now, if we go back to our schema, we can see that select and alias happen at the same time. So this is the phase in which we assign our label, and this is also the phase in which we try to call our label. Now, if you look at our rules, this is not supposed to work because an operation can only use data produced by operations before it. And alias does not happen before select, it happens at the same time. In other words, this part over here, when we say character level, is attempting to use information that was produced right here when we assign the label. But because these parts happen at the same time, it's not aware of the label. All this to say that the logical order of operations matters, and that what we want here is to actually call it level, because that is the name of the column in the table. And now when I run this, I get a resulting number. And so going back to our original point, we are able to combine columns and constants with any sort of arithmetic operations. Another very powerful thing that SQL can do is to apply functions. And a function is a pre-packaged piece of logic that you can apply to our data. And it works like this. There is a function called sqrt, which stands for square root, which takes a number and computes the square root. So you call the function by name, and then you open round brackets. And in round brackets, you provide the argument. And the argument can be a constant, such as 16, or it can be a column, such as level. And when I run this, you can see that in this case, the square root of 16 is calculated as 4, and this creates a constant column. And then here, for each value of level, we have also computed the square root. There are many functions in SQL, and they vary according to the data type which you provide. As you remember, we said that knowing the data types of columns, such as distinguishing between numbers and text, is important because it allows us to know which operations we can apply. And so there are functions that work only on certain data types. For example, here we see square root, which only works on numbers, but we also have text functions or string functions which only work on text. One of them is upper. So if I take upper and provide guild as an argument, what do you expect will happen? We have created a new column where the guild is shown in all uppercase. So how can I remember which functions there are and how to use them? The short answer is I don't. There are many functions in SQL, and here in the documentation you can see a very long list of all the functions that you can use in BigQuery. And as we said, the functions vary according to the data that they can work on. So if you look here on the left, we have array functions, date functions, mathematical functions, numbering functions, time functions, and so on and so on. It is impossible to remember all of these functions, so all you need to know is how to look them up when you need them. For example, if I know I need to work with numbers, I could scroll down here and go to mathematical functions. And here I have a long list of all the mathematical functions, and I can see them all on the right. And I should be able to find the square root function that I have showed you. And here the description tells me what the function does, and it also provides some examples. To summarize, these are some of the most powerful things you can do with the select statement. Not only you can retrieve every column you need in any order, you can rename columns according to your needs. You can define constant columns with a value that you choose. You can combine columns and constant columns in all sorts of calculations. And you can apply functions to do more complex work. I definitely invite you to go ahead and put your own data in BigQuery as I've shown you, and then start playing around with select and see how you can transform your data with it. One thing worth knowing is that I can also write queries that only include select without the from part. That is, queries that do not reference a table. Let's see how that works. Now, after I write select, I clearly cannot reference any columns because there is no table, but I can still reference constants. For example, I could say hello, 1, and false. And if I run this, I get this result. So remember, in SQL, we always query tables and we always get back tables. In this case, we didn't reference any previous table. We've just created constants. So what we have here are 3 columns with constant values, and there is only 1 row in the resulting table. This is useful mainly to test stuff. So let's say I wanted to make sure that the square root function does what I expect it to do. So I could call it right here and look at the result. Let's use this capability to look into the order of arithmetic operations in SQL. So if I write an expression like this, would you be able to compute the final result? In order to do that, you should be able to figure out the order in which all these operations are done. And you might remember this from arithmetic in school because SQL applies the same order that is taught in school. And we could define the order as follows. First, you would execute any specific functions that take a number as target. And then you have multiplication and division. Then you have addition and subtraction. And finally, brackets go first. So you first execute things that are within brackets. So pause the video and apply these rules and see if you can figure out what this result will give us. Now let's do this operation and do it in stages like we were doing in school. So first of all, we want to worry about what's in the brackets, right? So I will now consider this bracket over here. And in this bracket, we have the multiplication and addition. Multiplication goes first. So first I will execute this, which will give me 4. And then I will have 3 plus 4 plus 1, which should give me 8. Next, I will copy the rest of the operation. And here I reach another bracket. To execute what is in these brackets, I need to first execute the function. So this is the power function. So it takes 2 and exponentiates it to the power of 2, which gives 4. And then 4 minus 2 will give me 2. And this is what we get. Now we can solve this line. And first of all, we need to execute multiplication and division in the order in which they occur. So the first operation that occurs here is 4 divided by 2, which is 2. And I will just copy this for clarity. 8 minus 2 times 2 divided by 2. The next operation that occurs now is 2 times 2, which is 4. So that will be 8 minus 4 divided by 2. And the next operation is 4 divided by 2, which is 2. So I will have 8 minus 2, and all of these will give me a 6. Now all of these are comments, and we only have one line of code here. And to see whether I was right, I just need to execute this code. And indeed, I get 6. So that's how you can use the select clause only to test your assumptions and your operations, and a short refresher on the order of arithmetic operations, which will be important for solving certain SQL problems. Let us now see how the where statement works. Now, looking at the characters table, I see that there is a field which is called isAlive, and this field is of type Boolean. That means that the value can be either true or false. So if I go to the preview here and scroll to the right, I can see that for some characters this is true and for others it is false. Now let's say I only wanted to get those characters which are actually alive. And so to write my query, I would first write the address of the table, which is fantasy characters. Next, I could use the where clause to get those rows where isAlive is true. And finally, I could do a simple select star to get all the columns. And here I see that I only get the rows where isAlive is equal to true. So where is effectively a tool for filtering table rows. It filters them because it only keeps rows where a certain condition is true and discards all of the other rows. So if you want to visualize how the where filter works, you can see it as a horizontal selection of certain slices of the table, like in this case where I have colored all of the rows in which isAlive is true. Now the where statement is not limited to Boolean fields, it's not limited to columns that can only be true or false. We can run the where filter on any column by making a logical statement about it. For example, I could ask to keep all the rows where health number is bigger than 50. This is a logical statement, health bigger than 50, because it is either true or false for every row. And of course, the where filter will only keep those rows where this statement evaluates to true. And if I run this, I can see that in all of my results, health will be bigger than 50. And I can also combine smaller logical statements with each other to make more complex logical statements. For example, I could say that I want all the rows where health is bigger than 50 and isAlive is equal to true. Now, all of this becomes one big logical statement, and again, this will be true or false for every row, and we will only keep the rows where it is true. And if I run this, you will see that in the resulting table, the health value is always above 50 and isAlive is always true. In the next lecture, we will see in detail how these logical statements work and how we can combine them effectively. But now let us focus on the order of operations and how the where statement fits in there. When it comes to the lexical order, the order in which we write things, it is pretty clear from this example. First you have select, then from, and after from you have the where statement. And you have to respect this order. When it comes to the logical order, you can see that the where clause follows right after the from clause. So it is second actually in the logical order. If you think about it, this makes a lot of sense because the first thing that I need to do is to get the data from where it lives. And then the first thing I want to do after that is that I'm going to drop all the rows that I don't need so that my table becomes actually smaller and easier to deal with. There is no reason why I should carry over rows that I don't actually need, data that I don't actually want, and waste memory and processing power on it, so I want to drop those unneeded rows as soon as possible. And now that you know that where happens at this stage in the logical order, you can avoid many of the pitfalls that happen when you're just learning SQL. Let's see an example. Now take a look at this query. I'm going to the fantasy characters table, and then I'm getting the name and the level. And then I'm defining a new column. This is simply level divided by 10, and I'm calling this level scaled. Now let's say that I wanted to only keep the rows that have at least 3 as level scaled. So I would go here and write a where filter where level scaled bigger than 3. And if I run this, I get an error, unrecognized name. Can you figure out why we get this error? Level scaled is an alias that we assign in the select stage, but the where clause occurs before the select stage, so the where clause has no way to know about this alias. In other words, the where clause is at this point, and our rules say that an operation can only use data produced by operations before it. So the where clause has no way of knowing about the label which is assigned at this stage. So how can we solve this problem right here? The solution is to not use the alias and to instead repeat the logic of the transformation. And this actually works because it turns out that when you write logical statements in the where filter, you can not only reference the columns of the tables, but you can also reference operations on columns. And this way of writing operations on columns and combinations between columns works just as what we have shown in the select part. So that was all you need to know to get started with the where clause, which is a powerful clause that allows us to filter out the rows that we don't need and keep the rows that we need based on logical conditions. Now let's delve a bit deeper into how exactly these logical statements work in SQL. And here is a motivating example for you. This is a selection from the characters table, and we have a where filter, and this where filter is needlessly complicated. And I did this intentionally because by the end of this lecture, you should have no trouble at all interpreting this statement and figuring out for which rows it will be true. And likewise, you will have no problem writing complex statements yourself or deciphering them when you encounter them in the wild. The way that these logical statements work is through something called Boolean algebra, which is an essential theory for working with SQL, but also for working with any other programming language, and is indeed fundamental to the way that computers work. And though the name may sound a bit scary, it is really easy to understand the fundamentals of Boolean algebra. Now, let's look back at so-called normal algebra, meaning the common form that is taught in schools. In this algebra, you have a bunch of elements, which in this case, I'm only showing a few positive numbers, such as 0, 25, 100. You also have operators that act on these elements. For example, the square root symbol, the plus sign, the minus sign, the division sign, or the multiplication sign. And finally, you have operations, right? So in operations, you apply the operators to your elements, and then you get some new elements out of them. So here are two different types of operation. In one case, we take this operator, the square root, and we apply it to a single element. And out of this, we get another element. In the second kind of operation, we use this operator, the plus sign, to actually combine two elements. And again, we get another element in return. Boolean algebra is actually very similar, except that it's simpler in a way because you can only have two elements, either true or false. Those are all the elements that you are working with. And of course, this is why when there's a Boolean field in SQL, it is a column that can only have these two values, which are true and false. Now, just like normal algebra, Boolean algebra has several operators that we can use to transform the elements. And for now, we will only focus on the three most important ones, which are not, and or. And finally, in Boolean algebra, we also have operations. And in operations, we combine operators and elements and get back elements. Now we need to understand how these operators work. So let us start with the not operator. To figure out how a Boolean operator works, we have to look at something that's called a truth table. So let me look up the truth table for the not operator, and in this Wikipedia article, this is available here at logical negation. Now, first of all, we see that logical negation is an operation on one logical value. What does this mean? It means that the not operator works on a single element, such as not true or not false. And this is similar to the square root operator in algebra that works on a single element, a single number. Next, we can see how exactly this works. So, given an element that we call P, and of course P can only be true or false, the negation of P is simply the opposite value. So, not true is false and not false is true. And we can easily test this in our SQL code. So if I say select not true, what do you expect to get? We get false. And if I do select not false, I will of course get true. Next, let's see how the AND operator works. So we've seen that the not operator works on a single element. On the other hand, the AND operator connects two elements, such as writing true and false. And in this sense, the AND operator is more similar to the plus sign here, which is connecting two elements. So what is the result of true and false? To figure this out, we have to go back to our truth tables. And I can see here at the logical conjunction section, which is another word for the AND operator. Now the AND operator combines two elements, and each element can either be true or false. So this creates four combinations that we see here in this table. And what we see here is that only if both elements are true, then the AND operator will return true. In any other case, it will return false. So going back here, if I select true and false, what do you expect to see? I am going to get false. And it's only in the case when I do true and true that the result here will be true. And finally, we can look at the OR operator, which is also known as a logical disjunction. It's also combining two elements. It also has four combinations. But in this case, if at least one of the two elements is true, then you get true. And only if both elements are false, then you get false. And so going back to our SQL, true or true will of course be true. But even if one of them is false, we will still get true. And only if both are false, we will get false. So now you know how the three most important operators in Boolean algebra work. Now, the next step is to be able to solve long and complex expressions such as this one, and you already know how operators work. The only information you're missing is the order of operations. And just like in arithmetic, we have an agreed upon order of operations that helps us solve complex expressions, and the order of operations is written here. First, you solve for not, then you solve for and finally for or. And as with arithmetic, you first solve for the brackets. So let's see how that works in practice. Let us now simplify this expression. So the first thing I want to do is to deal with the brackets. So if I copy all of this part over here as a comment so it doesn't run as code, you will see that this is the most nested bracket, the innermost bracket in our expression, and we have to solve for this. So what is true or true? This is true, right? And now I can copy the rest of my expression up to here. And here I can solve the innermost bracket as well. So I can say true, and what I have here is false and true. So this is false, right? Because when you have and, both of them need to be true for it to return true, otherwise it's false. So I will write false. Moving on to the next line, I need to solve what's in the brackets. So I can copy the not, and now I have to solve what's in this bracket over here. Now, there are several operators here, but we have seen that not has the precedence, right? So I will copy true, and here I have not false, which becomes true. And then I can copy the last of the bracket. I'm not gonna do any more at this step to avoid confusion. And then I have or, and I can solve for this bracket over here, and true and false is actually false. Moving on, I can keep working on my bracket, and so I have a lot of operations here, but I need to give precedence to the ands. So the first and that occurs is this one, and that means I have to start with this expression over here. True and true results in true. And then moving on, I will copy the or over here, and now I have another and, which means that I have to isolate this expression. False and true results in false. And finally, I can copy the final and because I'm not able to compute it yet because I needed to compute the left side. And I can copy the remaining part as well. Moving on to the next line, I need to still do the and because the and takes precedence. And so this is the expression that I have to compute. So I will say true or, and then this expression false and true computes to false. And then copy the rest. Now let me make some room over here and go to the next line. And I can finally compute this bracket. We have true or false, which we know is true. Next, I need to invert this value because I have not true, which is false. And then I have or false. And finally, this computes to false. And now for the moment of truth, pun intended, I can run my code and see if the result actually corresponds to what we got. And the result is false. So in short, this is how you can solve complex expressions in Boolean algebra. You just need to understand how these three operators work, and you can use truth tables like this one over here to help you with that. And then you need to remember to respect the order of operations, and then if you proceed step by step, you will have no problem solving this. But now let's go back to the query with which we started, because what we have here is a complex logical statement that is plugged into the where filter, and it isolates only certain rows, and we want to understand exactly how this statement works. So let us apply what we've just learned about Boolean algebra to decipher this statement. Now, what I've done here is to take the first row of our results, which you see here, and just copy the values in a comment. And then I've taken our logical statement and copied it here as well. So let us see what SQL does when it checks for this row. The first thing that we need to do is to take all of these statements in our where filter and convert them to true or false. And to do that, we have to look at our data. Let us start with the first component, which is level bigger than 20. So for the row that we are considering, level is 12. So this comes out as false. Next, I will copy this and here we have isAlive equals true. Now for our row, isAlive equals false, so this statement computes as false. Mentor ID is not null, with null representing absence of data. In our case, mentor ID is 1, so it is indeed not null. So here we have true. And finally, what we have in here is class in Mage Archer. So we have not seen this before, but it should be pretty intuitive. This is a membership test. This is looking at class, which in this case is Hobbit, and checking whether it can be found in this list. And in our case, this is now false. So now that we've plugged in all the values for our row, what we have here is a classic Boolean algebra expression, and we are able to solve this based on what we've learned. So let us go and solve this, and first I need to deal with the brackets. And what I have here, I have an AND and an OR, and the AND takes precedence. So false and false is false, and I will copy the rest. And here I have not false, which is true. Next, we have false or true, which is true, and in the end, this computes to true. Now, in this case, we sort of knew that the result was meant to come out as true because we started from a row that survived the where filter, and that means that for this particular row, this statement had to compute as true. But it's still good to know exactly how SQL has computed this and understand exactly what's going on. And this is how SQL deals with complex logical statements. For each row, it looks at the relevant values in the row so that it can convert the statement to a Boolean algebra expression, and then it uses the Boolean algebra rules to compute a final result, which is either true or false. And then if this computes as true for the row, then the row is kept, and otherwise the row is discarded. And this is great to know because this way of resolving logical statements applies not only to the where component, but to all components in SQL which use logical statements and which we shall see in this course. Let us now look at the distinct clause, which allows me to remove duplicate rows. So let's say that I wanted to examine the class column in my data. So I could simply select it and check out the results. So what if I simply wanted to see all the unique types of class that I have in my data? This is where distinct comes in handy. If I write distinct here, I will see that there are only 4 unique classes in my data. Now, what if I was interested in the combinations between class and guild in my data? So let me remove the distinct from now and add guild here. And for us to better understand the results, I'm going to add an ordering. And here are the combinations of class and guild in my data. There is a character who is an archer and belongs to Gondor, and there are actually two characters who are archers and belong to Mirkwood, and there are many hobbits from Shirefolk, and so on. But again, what if I was interested in the unique combinations of class and guild in my data? I could add the distinct keyword here, and as you can see, there are no more repetitions here. Archer and Mirkwood occurs only once. Hobbit and Shirefolk occurs only once, because I'm only looking at unique combinations. And of course, I could go on and add more columns and expand the results to show the unique combinations between these columns. So here Hobbit and Shirefolk has expanded again because some hobbits are alive and others unfortunately are not. At the limit, I could have a star here, and what I would get back is actually my whole data, all the 15 rows, because what we're doing here is looking at rows that have the same value on all columns, rows that are complete duplicates, and there are no such rows in the data. So when I do select star, in this case, distinct has no effect. So in short, how distinct works, it looks at the columns that you've selected, only those which you have selected, and then it looks at all the rows, and two rows are duplicate if they have the exact same values on every column that you have selected. And then duplicate rows are removed, and only unique values are preserved. So just like the where filter, the distinct is a clause that removes certain rows, but it is more strict and less flexible in a sense. It only does one job, and that job is to remove duplicate rows based on your selection. And if we look at our map of SQL operations, we can place distinct. It occurs right after select, right? And this makes sense because we have seen that distinct works only on the columns that you have selected, and so it has to wait for select to choose the columns that we're interested in, and then we can deduplicate based on those. For the following lecture on unions, I wanted to have a very clear example, so I decided to go to the characters table and split it in two and create two new tables out of it. And then I thought that I should show you how I'm doing this, because it's a pretty neat thing to know, and it will help you when you are working with SQL in BigQuery. So here's a short primer on yet another way to create a table in BigQuery. You can use your newly acquired power of writing SQL queries to turn those queries into permanent tables. So here's how you can do it. First, I've written a simple query here, and you should have no trouble understanding it by now. Go to the fantasy characters table, keep only rows where isAlive is true, and then get all the columns. Next, we need to choose where the new table will live and how it will be called. So I'm placing it also in the fantasy dataset, and I'm calling it characters alive. And finally, I have a simple command, which is create table. Now, what you see here is a single statement in SQL. It's a single command that will create the table. And you can have, in fact, multiple statements within the same code. And you can run all the statements together when you hit run. The trick is to separate all of them with this semicolon over here. The semicolon tells SQL, hey, this command over here is over, and next I might add another one. So here we have the second statement that we're going to run, and this looks just like the one above, except that our query has changed because we're getting rows where isAlive is false, and then we are calling this table characters dead. So I have my two statements, they're separated by semicolons, and I can just hit run, and I will see over here that BigQuery is showing me the two statements on two different rows. And you can see that they are both done now. So if I open my Explorer over here, I will see that I have two new tables, characters alive and characters dead. And if I go here, for characters alive, is alive will of course be true on every row. Now, what do you think would happen if I ran this script again? Let's try it. So I get an error. The error says that the table already exists. And this makes sense because I've told SQL to create a table, but SQL says that table already exists. I cannot create it again. So there are ways that we can tell SQL what to do if the table already exists again, so that we specify the behavior we want and we are not going to just get an error. One way is to say create or replace table fantasy characters alive, and what this will do is that if the table already exists, BigQuery will delete it and then create it again, or in other words, it will overwrite the data. So let's write it down too, and let's make sure that this query actually works. So when I run this, I will get no errors even if the table already existed, because BigQuery was able to remove the previous table and create a new one. Alternatively, we may want to create the table only if it doesn't exist yet and leave it untouched otherwise. So in that case, we could say create table if not exists. So what this will do is that if this table is already existing, BigQuery won't touch it and it won't throw an error, but if it doesn't exist, it will create it. So let us write it down too, and make sure that this query runs without errors. And we see that also here we get no errors. And that, in short, is how you can save the results of your queries in BigQuery and make them into full-fledged tables that you can save and query at will. And I think this is a really useful feature if you're analyzing data in BigQuery, because any results of your queries that you would like to keep, you can just save them and then come back and find them later. Let's learn about unions. Now, to show you how this works, I have taken our characters table and I have split it into two parts. And I believe the name is quite self-descriptive. There is a separate table now for characters who are alive and a separate table for characters who are dead. And you can look at the previous lecture to see how I've done this, how I've used a query to create two new tables. But this is exactly the characters table with, the same schema, the same columns, the same times. It's just split in two based on the is alive column. Now let us imagine that we do not have the fantasy.characters table anymore. We do not have the table with all the characters because it was deleted or we never had it in the first place. And let's pretend that we only have these two tables now, characters alive and characters dead. And we want to reconstruct the characters table out of it. We want to create a table with all the characters. How can we do that? Now what I have here are two simple queries: select star from fantasy characters alive and select star from fantasy characters dead. So these are two separate queries, but actually in BigQuery there are ways to run multiple queries at the same time. So I'm gonna show you first how to do that. Now, an easy way to do that is to write your queries, and then add a semicolon at the end. And so what you have here is basically a SQL script which contains multiple SQL statements, in this case 2, and if you hit run, all of these will be executed sequentially. And when you look at the results, so you're not just getting a table anymore because it's not just a single query that has been executed, but you can see that there have been 2 commands that have been executed, which are here. And then for each of those 2, you can simply click View Results and you will get to the familiar Results tab for that. And if I want to see the other one, I will click on the back arrow here and click on the other View Results, and then I can see the other one. Another way to handle this is that I can select the query that I'm interested in and then click Run, and here I see the results. So BigQuery has only executed the part that I have selected. Or I can decide to run the other query in my script, select it, click Run, and then I will see the results for that query. And this is a pretty handy functionality in BigQuery. It's also a functionality that might give you some headaches if you don't know about it, because if for some reason you selected a part of the code during your work and then you just want to run everything, you might hit Run and get an error here because BigQuery is only seeing the part that you selected and cannot make sense of it. So it's good to know about this. But our problem has not been solved yet, because remember, we want to reconstruct the characters table, and what we have here are 2 queries, and we can run them separately and we can look at the results separately, but we still don't have a single table with all the results. And this is where union comes into play. Union allows me to stack the results from these 2 tables. So if I first I will take off the semicolons because this will become a single statement. And then in between these 2 queries, I will write union distinct. And when I run this, you can verify for yourself, we have 15 rows and we have indeed reconstructed the characters table. So what exactly is going on here? Well, it's actually pretty simple. SQL is taking all of the rows from this first query and then all of the rows for the second query, and then it's stacking them on top of each other. So you can really imagine the act of horizontally stacking a table on top of the other to create a new table which contains all of the rows of these 2 queries combined. And that, in short, is what union does. Now, there are a few details that we need to know when working with union. And to figure them out, let us look at a toy example. So I've created 2 very simple tables, toy1 and toy2, and you can see how they look in these comments over here. They all have 3 columns, which are called imaginatively col1, col2, col3, and then this is the toy1 table, and then this is the toy2 table. Now, just like before, we can combine these tables by selecting all of them and then writing a union in between them. Now, in BigQuery, you're not allowed to write union without a further qualifier, a keyword, and it has to be either all or distinct. So you have to choose one of these 2. And what is the choice about? Well, if you do union all, you will get all of the rows that are in the first table and those that are in the second table, regardless of whether they are duplicate. Okay? But with union distinct, you will get, again, all of the rows from the 2 tables, but you will only consider unique rows. You will not get any duplicates. Now we can see that these 2 tables share a column which is actually identical. 1 true yes over here and the same row over here. Now, if I write union all, I expect the result to include this row twice. So let us verify that. And you can see that here you have 1 true yes, and at the end you also have 1 true yes. And in total you get 4 rows, which are all the rows in the 2 tables. However, if I do union distinct, I expect to get 3 rows, and I expect this row to appear only once and not to be duplicated. Again, you need to make sure you're not selecting any little part of your script before you run it, so the whole script will be run. And as you can see, we have 3 rows and there are no duplicates. Now, it's interesting that BigQuery actually forces you to choose between all or distinct, because in many SQL systems, for your information, you are able to write union without any qualifier, and in that case, it means union distinct. So in other SQL systems, when you write union, it is understood that you want union distinct, and if you actually want to keep the duplicate rows, you will explicitly write union all. But in BigQuery, you always have to explicitly say whether you want union all or union distinct. Now, the reason this command is called union and not like stack or something else is that this is a set terminology, right? This comes from the mathematical theory of sets, which you might remember from school. And the idea is that a table is simply a set of rows. So this table over here is a set of 2 rows, and this table over here is a set of 2 rows. And once you have 2 sets, you can do various set operations between them. And the most common operation that we do in SQL is unioning, and unioning means combining the values of 2 sets. So you might remember from school the Venn diagram, which is a typical way to visualize the relations between sets. So in this simple Venn diagram, we have 2 circles, A and B, which represent 2 sets. And in our case, A represents the collection of rows in the first table, and B represents all the rows that are in the second table. So what does it mean to union these sets? It means taking all of the elements that are in both sets. So taking all of the rows that are in both tables. And what is the difference here between union distinct and union all? Where you can see that the rows of A are this part over here plus this part over here, and the rows of B are this part over here plus this part over here. And so when we combine them, we're actually counting the intersection twice. We're counting this part twice. And so what do you do with this double counting? Do you keep it or do you discard it? If you do union all, you will keep it, so rows that are in common between A and B will duplicate, you will see them twice. But if you do union distinct, you will discard it, and so you won't have any duplicates in the results. So that's one way to think about it in terms of sets. But we also know that union is not the only set operation, right? There are other set operations. A very popular one is the intersect operation. Now the intersect looks like this, right? It says take only the elements that are in common between these 2 sets. So can we do that in SQL? Can we say, give me only the rows that are in common between the 2 tables? And the answer is yes, we can do this. And if we go back here, we can, instead of union, write intersect and then distinct. And what do you expect to see after I run this command? Take a minute to think about it. So what I expect to see is to get only the rows that are shared between the 2 tables. Now there is one row which is shared between these 2 tables, which is the one true yes row, which we have seen. And if I run this, I will get exactly this row. So intersect distinct gives me the rows that are shared between the 2 tables, and I have to write intersect distinct. I cannot write intersect all because actually it doesn't mean anything, so it's not going to work. And here's another set operation which you might consider, which is subtraction. So what if I told you, give me all of the elements in A except the elements that A shares with B. So what would that look on the drawing? It would look like this, right? So this is taking all of the elements that are in A, except these ones over here, because they are in A, but they're also in B, and I don't want the elements shared with B. And yes, I can also do that in SQL. I can come here and I could say, give me everything from toy 1, except distinct everything from toy 2. And what this means is that I want to get all of my rows from toy 1, except the rows that are shared with toy 2. So what do you expect to see when I run this? Let's hit run. And I expect to see only this row over here, because this other row is actually shared with B. And this is what I get. Again, you have to write except distinct. You cannot write except all because it actually doesn't mean anything. And keep in mind that unlike the previous two operations, which are union and distinct, the except operation is not symmetric, right? So if I swap the tables over here, I actually expect to get a different result, right? I expect to see this row over here selected because I'm saying, give me everything from this table, toy 2, except the rows that are shared with toy 1. So let us run this and make sure. And in fact, I get the 3 true maybe row. So careful that the except operation is not symmetric. The order in which you put the two tables matters. So that was a short overview of union, intersect, except, and I will link this here, which is the BigQuery documentation on this, and you can see that they're actually called set operators. In fact, in real life, you almost always see union. Very rarely you will see somebody using intersect or except. A lot of people also don't know about them. But I think it's worth it that we briefly looked at all three, and it's especially good for you to get used to thinking about tables as sets of rows and thinking about SQL operations in terms of set operations, and that will also come in handy when we study joins. But let us quickly go back to our toy example, and there are two essential prerequisites for you to be able to do a union or any type of sort operations. Number one, the tables must have the same number of columns. And number two, the columns must have the same data type. So as you can see here, we are combining toy 2 and toy 1, and both of them have 3 columns. And the first column is an integer, the second is a Boolean, and the third is a string in both tables. And this is how we are able to combine them. So what would happen if I went to the first table and I got only the first 2 columns and then I tried to combine it? You guessed it, I would get an error because I have a mismatched column count. So if I want to select only the first 2 columns in a table, I need to select only the first 2 columns in another table. And then the union will work. Now what would happen if I messed up the order of the columns? So let's say that here I will select column 1 and column 3, and here I will select column 1 and column 2. Let me run this, and I will get an error because of incompatible types, string and bool. So what's happening here is that SQL is trying to get the values of col 3 over here and put it into col 2 over here. And it's trying to get a string and put it into a Boolean column. And that simply doesn't work because, as you know, SQL enforces strict types on columns. And so this will not work. But of course, I could select col 3 in here as well. And now again, we will have a string column going into a string column, and of course, this will work. So to summarize, you can union or intersect or accept any two tables as long as they have the same number of columns and the columns have the same data types. Let us now illustrate a union with a more concrete example. So we have our items table here and our characters table here. So the items table represents like magical items, right? While the characters table, we're familiar with it, represents actual characters. So let's say that you are managing a video game and someone asks you for a single table that contains all of the entities in that video game, right? And the entities include both characters and items. So you want to create a table which combines these two tables into one. We know we can use union to do that. We know we can use union to stack all the rows. But we cannot directly union these two tables because they have a different schema, right? They have a different number of columns, and then those columns have different data types. But let's analyze what these two tables have in common and how we could maybe combine that. So first of all, they both have an ID, and in both cases it's an integer. So that's already pretty good. They both have a name, and in both cases the name is a string, so we can combine that as well. The item type can be thought of being similar to the class, and then each item has a level of power, which is expressed as an integer, and each character has a level of experience, which is expressed as an integer, and you can think that they are kind of similar. And then finally, we have a timestamp field representing a moment in time for both columns, which are date added and last active. So looking at these columns that the two have sort of in common, we can find a way to combine them. And here's how we can translate this into SQL, right? So I went to the fantasy items table and I selected the columns that I wanted. And then I went to the characters table and I selected the columns that I wanted to combine with those in the right order. So we have ID with ID, name with name, class with item type, level with power, and last active with date added. So I have my columns, they're in the right order. I wrote union distinct, and if I run this, you will see that I have successfully combined the rows from these two tables by finding out which columns they have in common and then writing them in the right order and then adding union distinct. Now all the columns that we've chosen for the combination have the same type, but what would happen if I wanted to combine two columns that are not actually the same type? So let's say, what if we wanted to combine rarity, which is a string, with experience, which is an integer? As you know, I cannot do this directly, but I can go around it by either taking rarity and turning it into an integer, or taking experience and turning it into a string. I just have to make sure that they both have the same data type. Now, the easiest way is usually to take any other data type and turn it into a string, because you just turn it into text. So let's say that for the sake of this demonstration, we will take integer experience, which is an integer, and turn it into a string, which is text, and then combine that with rarity. So I will go back to my code and I will make some room over here. And here in items, I will add rarity. And here in characters, I will add experience. And you can see that I already get an error here saying that the union distinct has incompatible types, just like expected. So what I want to do here is to take experience and turn it into string, and I can do that with the cast function. So I can do cast experience as string, and what this will do is basically take these values and convert them to string. And if I run this, you can see that this has worked. So we combined two tables into one, and now the result is a single table. It has a column called rarity. The reason it's called rarity is that it's taking the name from the first table in the operation, but we could of course rename it to whatever we need. And this is now a text column because we have combined a text column with also a text column thanks to the casting function. So what we see here are a bunch of numbers which came originally from the experience column from the characters table, but they're now converted to text. And if I scroll down, then I will also see the original values of rarity from the items table. Finally, let us examine union in the context of the logical order of SQL operations. So you can see here that we have our logical map, but it looks a bit different than usual. And the reason it's different is that we are considering what happens when you union two tables. And here the blue represents one table and the red represents the other table. So I wanted to show you that all of the ordering that we have seen until now, so first get the table, then use the filter with where, then select the columns you want, and if you want, use distinct to remove duplicates. All of this happens in the same order separately for the two tables that you are unioning. And this applies to all of the other operations like joining and grouping, which we will see later in the course. So at first, the two tables are working on two separate tracks, and SQL is doing all these operations on them in this specific order. And only at the end of all this, only after all of these operations have run, then we have the union. And in the union, these two tables are combined into one. And only after that, only after the tables have been combined into one, you apply the last two operations, which are order by and limit. And actually, nothing forces you to combine only two tables. You could actually have any number of tables that you are combining in union, but then the logic doesn't change at all. All of these operations will happen separately for each of the tables, and then only when all of these operations are done, only when all of the tables are ready, then they will be combined into one. And if you think about it, it makes a lot of sense because first of all, you need the select to have run in order to know what is the schema of the tables that you are combining. And then you also need to know if distinct has run on each table because you need to know which rows you need to combine in the union. And that is all you need to know to get started with union, this very powerful statement that allows us to combine rows from different tables. Let us now look at order by. So I'm looking at the characters table here, and as you can see, we have an ID column that goes from 1 to 15, which assigns an ID to every character, but you will see that the IDs don't appear in any particular order. And in fact, this is a general rule for SQL. There is absolutely no order guarantee for your data. Your data is not stored in any specific order, and your data is not going to be returned in any specific order. And the reason for this is fundamentally one of efficiency, because if we had to always make sure that our data was perfectly ordered, that would add a lot of work. It would add a lot of overhead to the engine that makes the queries work, and there's really no reason to do this. However, we do often want to order our data when we are querying it. We want to order the way that it is displayed, and this is why the order by clause is here. So let us see how it works. I am selecting everything from fantasy characters, and again, I'm going to get the results in no particular order, but let's say I wanted to see them in order by name, so then I would do order by name. And as you can see, the rows are now ordered alphabetically according to the name. I could also invert the order by writing desc, which stands for descending, and that means descending alphabetical order, which means from the last letter in the alphabet to the first. I can of course also order by number columns such as level, and we would see that the level is increasing here. And of course that could also be descending to go in the opposite direction. And the corresponding keyword here is ask, which stands for ascending, and this is actually the default behavior, so even if you omit this, you will get the same, going from the smallest to the largest. I can also order by multiple columns, so I could say order by class and then level. And what that looks like is that, first of all, the rows are ordered by class. So as you can see, this is done alphabetically. So first archer, and then the last is warrior. And then within each class, the values within the class are ordered according to the level, going from the smallest level to the biggest level. And I can invert the order of one of them, for example, class. And in this case, we will start with warriors, and then within the warrior class, we will still order the level in ascending order. So for every column that's in the ordering, I can decide whether that ordering is in ascending order or descending order. Now let us remove this and select the name and the class. And once again, I get my rows in no particular order, and I'm seeing the name and the class. So I wanted to show you that you can also order by columns which you have not selected. So I could order these elements by level, even though I'm not looking at level, and it will work all the same. And finally, I can also order by operations. So I could say take level divided by experience and then multiply that by 2 for some reason. And it would also work in the ordering. Even though I am not seeing that calculation is being done in the background and used for the ordering. So I could actually take this here and copy it, create a new column, call it calc for calculation. And if I show you this, you will see the results are not very meaningful, but you will see that they are in ascending order. So we have ordered by that. And sometimes you will see this notation over here, order by 2, 1, for example. And as you can see, what we've done here is that we've ordered by class, first of all, because we starting with archers and going to warriors. And then within each class, we are ordering by name, also in ascending order. So this is basically referring to the columns that are referenced in the select. 2 means order by the second column, which you have referenced, which in this case is class. And 1 means order by the first column that you referenced. So it's basically a shortcut that people sometimes use to avoid rewriting the names of columns that they have selected. And finally, when we go back to the order of operations, we can see that order by is happening really at the end of all of this process. So as you will recall, I have created this diagram that's a bit more complex to show what happens when we union different tables together. What happens is that basically all these operations, they run independently on each table, and then finally the tables get unioned together. And after all of this is done, SQL knows the final list of rows that we will include in our results. And that's the right moment to order those rows. It would not be possible to do that before, so it makes sense that order is located here. Let us now look at the limit clause. So what I have here is a simple query. It goes to the characters table, it filters for the rows where the character is alive, and then it gets 3 columns out of this. So let's run this query. And you can see that this query returns 11 rows. Now let us say that I only wanted to see 5 of those rows, and this is where limit comes into place. Limit will look at the final results and then pick 5 rows out of those results, reducing the size of my output. And here you can see that we get 5 rows. Now, as we said in the lecture of ordering, by default, there is no guarantee of order in a SQL system. So when you are getting all your data with a query and then you run limit 5 on top of it, you have no way of knowing which of the rows will be selected to fit amongst those 5. You're basically saying that you're okay with getting any 5 of all of the rows from your result. Because of this, people often will use limit in combination with order by. For example, I could say order by level and then limit 5. And what I would get here is essentially the first 5 most inexperienced characters in my dataset. And let us say that you have a problem of finding the least experienced character in your data, the character with the lowest level. So, of course, you could say order by level and then limit 1, and you would get the character with the lowest level, right? And this works. However, it is not ideal. There is a problem with this solution. So can you figure out what the problem with this solution is? The problem will be obvious once I go back to limit 5 and I look here and I see that I actually have 2 characters which have the lowest level in my dataset. So in theory, I should be able to return both of them because they both have the lowest level. However, when I write limit 1, it simply cuts the rows in my output and it is unaware of that further information that is here in this second row. And in the further lectures, we will see how we can solve this better and get results which are more precise. And if we look at the logical order of operations, we can see that limit is the very last operation. And so all of the logic of our query is executed, all our data is computed, and then based on that final result, we sometimes decide to not output all of it, but to output a limited number of rows. So a common mistake for someone who is starting with SQL is thinking that they can use limit in order to have a cheaper query. For example, you could say, oh, this is a really large table. This table has 2 terabytes of data. It would cost a lot to scan the whole table. So I will say select star, but then I will put limit 20 because I only want to see the first 20 rows. And that means that I will only scan 20 rows and my query will be very cheap, right? No, that is actually wrong. That doesn't save you anything. And you can understand this if you look at the map because all of the logic is going to execute before you get to limit. So you're going to scan the whole table when you say select star and you're gonna apply all of the logic, and the limit is actually just changing the way your result is displayed. It's not actually changing the way your result is computed. If you did want to write your query so that it scans less rows, one thing you should do is focus on the where statement actually, because the where statement is the one that runs in the beginning right after getting the table, and it is able to actually eliminate rows, which usually saves you on computation and money and so on. However, I do need to say that there are systems where writing limit may actually turn into savings because different systems are optimized in different ways and allow you to do different things with the commands. But as a rule, usually with SQL, limit is just changing the way your result is displayed and doesn't actually change anything in the logic of execution. Let us now look at the case clause, which allows us to apply conditional logic in SQL. So you can see here a simple query. I am getting the data from the characters table. I am filtering it so that we only look at characters who are alive, and then for each character we're getting the name and the level. Now, when you have a column that contains numbers such as level, one typical thing that you do in data analysis is bucketing. And bucketing basically means that I look at all these multiple values that level can have and I reduce them to a smaller number of values so that whoever looks at the data can make sense of it more easily. Now, the simplest form of bucketing that you can have is the one that has only two buckets, right? So looking at level, our two buckets, for example, could be in one bucket we'd put values that are equal or bigger than 20, so characters who have a level that's at least 20, and in the other bucket we put all the characters that have a level that is less than 20, for example. Now, how could I define those two buckets? So we know that we can define new columns in the select statement and that we can use calculations and logical statements to define those columns. So one thing that I could do would be to go here and then write level bigger or equal than 20. And then call this new column level at least 20, for example. And when I run this, I get my column. Now, of course, this is a logical statement, and for each row, this will be true or false. And then you can see that our new column here gives us true or false on every column. And this is a really basic form of bucketing because it allows us to take, level has basically 11 different values in our data, and it can be complicated to look at this many values at once. And now we've taken these 11 values and reduced them to two buckets so that we have organized our data better and it's easier to read. But there are two limitations with this approach. One, I might not want to call my buckets true or false. I might want to give more informative names to my buckets, such as experienced or inexperienced, for example. The other limitation is that with this approach, I can effectively only divide my data in two buckets, because once I write a logical statement, it's either true or false, so my data gets divided in two. But often it's the case that I want to use multiple buckets for my use case. Now, bucketing is a typical use case for the case when statement, so let's see it in action now. So let me first write a comment, not any actual code, where I define what I want to do, and then I will do it with the code. So I have written here the buckets that I want to use to classify the character's level. So up to 15, they are considered low experience. Between 15 and 25, they are considered mid, and anything above 25, we will classify as super. Now let us apply the case clause to make this work. So the case clause is always bookended by these two parts, case and end. So it starts with case, it ends with end, and a typical error when you're getting started is to forget about the end part. So my recommendation is to always start by writing both of these and then going in the middle to write the rest. Now in the middle, we're going to define all the conditions that we're interested in, and each condition starts with the keyword when and is then followed by a logical condition. So our logical condition here is level smaller than 15. Now we have to define what to do when this condition is true, and it follows with the keyword then, And when this condition is true, we want to return the value low, which is a string, a piece of text that says low. Next, we proceed with the following condition. So when level is bigger and equal to 15 and level is lower than 25. So if you have trouble understanding this logical statement, I suggest you go back to the lecture about Boolean algebra. But what we have here, there are two microstatements, right? Level under 25 and level equal or bigger than 15. They are connected by AND, which means that both of these statements have to be true in order for the whole statement to be true, which is what we want in this case, right? And what do we want to return in this case? We will return the value mid. And the last condition that we want to apply, when level is bigger or equal than 25, then we will return super. Now, all of this that you see here, this is the case clause, right? Or the case statement. And all of this is basically defining a new column in my table. And given that it's a new column, I can use the aliasing to also give it a name. And I can call this level bucket. Now let's run this and see what we get. And as you can see, we have our level bucket, and the characters that are above 25 are super, and then we have a few mids, and then everyone who's under 15 is low. So we got the results we wanted, and now let us see exactly how the case statement works. So I'm going to take Gandalf over here, and he has level 30. So I'm going to write over here level equals 30 because we're looking at the first row, and that is the value of level. And then I'm going to take the conditions for the case statement that we are examining and add them here as a comment. Now, because in our first row level equals 30, I'm going to take the value and substitute it here for level. Now what we have here is a sequence of logical statements, and we have seen how to work with these logical statements in the lecture on Boolean algebra. Now our job is to go through each of these logical statements in turn and evaluate them, and then as soon as we find one that's true, we will stop. So the first one is 30 smaller than 15. Now this is false, so we continue. The second one is a more complex statement. We have 30 greater or equal to 15, which is actually true, and 30, oops, I did not substitute it there, but I will do it now, and 30 smaller than 25, which is false. And we know from our Boolean algebra that true and false evaluates to false. Therefore, the second statement is also false, so we continue. And now we have 30 greater or equal than 25, which is true, so we finally found a line which evaluates as true, and that means that we return the value super. And as you can see for Gandalf, we have indeed gotten the value super. Let us look very quickly at one more example. We get Legolas, which is level 22. And so I will once again copy this whole thing and comment it. And I will substitute 22 for every value of level, because that's the row we're looking at. And then looking at the first row, 22 smaller than 15 is false, so we proceed. And then looking at the second row, 22 bigger than 15 is true, and 22 smaller than 25 is also true, so we get true and true, which evaluates to true, and so we return mid. And then looking at Legolas, we get mid. So this is how the case when statement works in short. For each row, you insert the values that correspond to your row, in this case, the value of level, and then you evaluate each of these logical conditions in turn, and as soon as one of them returns true, then you return the value that corresponds to that condition, and then you move on to the next row. Now I will clean this up a bit. And now looking at this statement now and knowing what we know about the way it works, can we think of a way to optimize it, to make it nicer, to remove redundancies? Think about it for a minute. Now, one thing we could do to improve it is to remove this little bit over here, because if you think about it, this part that I've highlighted is making sure that the character is not under 15, so that it can be classified as mid. But actually, we already have the first condition that makes sure that if the character is under 15, then the statement will output low and then move on. So if the character is under 15, we will never end up in the second statement. But if we do end up in the second statement, we already know that the character is not under 15. This is due to the fact that case when proceeds condition by condition and exits as soon as a condition is true. So effectively, I can remove this part over here, and then at the second condition, only make sure that the level is below 25, and you will see if you run this that our bucketing system works just the same. And the other improvement that I can add is to replace this last line with an else clause. So the else clause takes care of all the cases that did not meet any of the conditions that we specified. So the case statement will go condition by condition and look for a condition that's true, but in the end, if none of the conditions were true, it will return what the else clause says. So it's like a fallback for the cases when none of our conditions turned out to be true. And if you look at our logic, you will see that if this has returned false and this has returned false, all that's left is characters that have a level which is either 25 or bigger than 25. So it is sufficient to use an else and to call those super. And if I run this, you will see that our bucketing works just the same. For example, Gandalf is still marked as super because in the case of Gandalf, this condition has returned false and this condition has returned false, and so the else output has been written there. Now, what do you think would happen if I completely removed the else? What do you think would happen if I only had two conditions, but it can be the case that none of them is true? What will SQL do in that case? Let us try it and see what happens. So the typical response in SQL when it doesn't know what to do is to select a null value, right? And if you think about it, it makes sense because we have specified what happens when level is below 15 and when level is below 25, but none of these are true, and we haven't specified what we want to do when none of these are true. And because we have been silent on this issue, SQL has no choice but to put a null value in there. So this is practically equivalent to saying else null. This is the default behavior for SQL when you don't specify an else clause. Now, like every other piece of SQL, the case statement is quite flexible. For instance, you are not forced to always create a text column out of it. You can also create an integer column, so you could define a simpler leveling system for your characters by using 1 and 2, else 3 for the higher level characters. And this of course will also work, as you can see here. However, one thing that you cannot do is to mix types, right? Because what this does is that it results in one column, in a new column. And as you know, in SQL, you're not allowed to mix types between columns. So always keep it consistent when it comes to typing. And then when it comes to writing the when condition, all the computational power of SQL is available. So you can reference columns that you are not selecting. You can run calculations as I am doing here, and you can chain logical statements, right? Boolean statements in complex ways. You can really do anything you want. Although I generally suggest to keep it as simple as possible for your sake and the sake of the people who use your code. And that is really all you need to know to get started with the case statement. To summarize, the case statement allows us to define a new columns whose values are changing conditional on the other values of my row. This is also called conditional logic, which means that we consider several conditions and then we do have different behaviors based on which condition is true. And the way it works is that in the select statement, when you are mentioning all your columns, you create a new column, which in our case is this one, and you bookend it with a case and an and. And then between those, you write your actual conditions. So every condition starts with a when, is followed by a logical statement, which needs to evaluate to true or false, and then has the keyword then, and then a value. And then the case when statement will go through each of these conditions in turn, and as soon as one of them evaluates to true, it will output the value that you have specified. If none of the conditions evaluate to true, then it will output the value that you specify in the else keyword, and if the else keyword is missing, it will output null. And so this is what you need to use the case statement, and then experience and exercise and coding challenges will teach you when it's the case to use it, pun intended. Now, where does the case statement fit in our logical order of SQL operations? And the short answer is that it is defined here at the step when you are selecting your columns. That's when you can use the case when statement to create a new column that applies your conditional logic. And this is the same as what we've shown in the lecture on SQL calculations. You can use select statement not only to get columns which already exist, but to define new columns based on calculations and logic. Now, let us talk about aggregations, which are really a staple of any sort of data analysis. And an aggregation is a function that takes any number of values and compresses them down to a single informative value. So I'm looking here at my usual characters table, but this is the version that I have in Google Sheets. And as you know, we have this level column, which contains the level of each character. And if I select this column in Google Sheets, you will see that in the bottom right corner, I can see here a number of aggregations on this column. And like I said, no matter how many values there are in the level columns, I can use aggregations to compress them to one value. And here you see some of the most important aggregations that you will work with. Sum, simply adding up all values together. The average, which is doing the sum and then dividing by the number of values. The minimum value, the maximum, the count, and the count numbers, which is the same here. So these are basically summaries of my column, and you can imagine in cases where you have thousands or millions of values, how useful these aggregations can be for you to understand your data. Now here's how I can get the exact same result in SQL. I simply need to use the functions that SQL provides for this purpose. So as you can see here, I'm asking for the sum, average, minimum, maximum, and count of the column level. And you can see the same results down here. Now, of course, I could also give names to this column. For example, I could take this one and call it max level. And in the result, I would get a more informative column name, and I can do the same for all columns. Now, of course, I can run aggregations on any columns that I want. For example, I could also get the maximum of experience and call this max experience. And I can also run aggregations on calculations that involve multiple columns as well as constants. So everything we've seen about applying arithmetic and logic in SQL also applies. Now, of course, looking at the characters table, we know that our columns have different data types, and the behavior of the aggregate functions also is sensitive to the data types of the columns. For example, let us look at the many text columns that we have, such as class. Now, clearly not all of the aggregate functions that we've seen will work on class, because how would you take the average of these values? It's not possible, right? However, there are some aggregate functions that also work on strings. So here's an example of aggregate functions that we can run on a string column such as class. First, we have count, which simply counts the total number of non-null values. And I will give you a bit more detail about the count functions soon. Then we have minimum and maximum. Now, the way that strings are ordered in SQL is something called lexicographic order, which is basically a fancy word for alphabetical order. And basically you can see here that for minimum, we get the text value that occurs earlier in alphabetical order, whereas warrior occurs last. And finally, here's an interesting one called string ag. And what this does is that this is a function that actually takes two arguments. The first argument, as usual, is the name of the column, and the second argument is a separator. And what this outputs is now a single string, a single piece of text, where all of the other pieces of text have been glued together and then separated by this character that we specified over here, which in our case is a comma. Now, if you go to the Google documentation, you will find an extensive list of all the aggregate functions that you can use in Google SQL. And this includes the ones that we've just seen, such as average or max, as well as a few others that we will not explore in detail here. So let us select one of them, such as average, and see what the description looks like. Now, you can see that this function returns the average of all values that are not null, and don't worry about this expression in an aggregated group. For now, just think about this as meaning all the values that you provide to the function, all the values in the column. Now, there is a bit about window functions, which we will see later. And here there are, in the caveat section, there are some interesting edge cases. For example, what happens if you use average on an empty group, or if all values are null, in that case it returns null, and so on. You could see what the function does when it finds these edge cases. And here is perhaps the most important section, which is supported argument types. And this tells you what type of columns you can use this aggregation function on. So you can see that you can use average on any numeric input type, right? Any column that contains some kind of number, and also on interval. An interval, we haven't examined it in detail, but this is actually a data type that specifies a certain span of time. So interval could express something like 2 hours or 4 days or 3 months. it is a quantity of time. And finally, in this table, returned data types, you can see what the average function will give you based on the data type that you insert. So if you insert an integer column, it will return to you a float column. And that makes sense because the average function involves a division, and that division will usually give you floating point values. But for any other of the allowed input types, such as numeric, bit numeric, and so on, and these are all data types which represent numbers in BigQuery, the average function, as you can see here, will preserve that data type. And finally, we have some examples. So whenever you need to use an aggregate function, that is, whenever you need to take many values, a sequence of multiple values, and compress them all down to one value, but you're not sure about which function to use or what the behavior of the function is, you can come to this page and look up the functions that interest you and then read the documentation to see how they work. Now here's an error that typically occurs when starting out with aggregations. So you might say, well, I want to get the name of each character and their level, but I also want to see the average of all levels, and because I want to compare those two values. I want to compare the level of my character with the average on all levels. So I can write a query that looks like this, right? Go to the fantasy characters table and then select name, level, and then average level. But as you can already see, this query is not functioning. It's giving me an error, and the error says that the select list expression references column name, which is neither grouped nor aggregated. So what does this actually mean? To show you what this means, I've gone back to my Google Sheets where I have the same data for my characters table, and I have copy-pasted our query over here. Now, what this query does, it takes the name column, so I will copy-paste it over here, and then it takes the level column, copy-paste this here as well, and then it computes the average over level. Now, I can easily compute this with sheet formula by writing equal and then calling the function, which is actually called average. And then within the function, I can select all these values over here, and I get the average. Now, this is the result that SQL computes, but SQL is actually not able to return this result. And the reason is that there are 3 columns, but they have mismatching number of values. Specifically, these 2 columns have 15 values each, whereas this column has a single value. And SQL is not able to handle this mismatch. Because, as a rule, every SQL query needs to return a table. And a table is a series of columns where each column has the same number of values. If that constraint is not respected, you will get an error in SQL. And we will come back to this limitation when we examine advanced aggregation techniques. But for now, just remember that you can mix non-aggregated columns with other non-aggregated columns, such as name and level, and you can mix aggregated columns with aggregated columns, such as average level with sum level, for example. So I could simply do this, and I would be able to return this as a table, because as you can see, there are 2 columns. Both columns have a single row. The number of rows matches, and this is actually valid. But you might ask, can't I simply take this value over here and just copy it in every row, and until I make sure that average level has the same number of values as name and level, and so return a table and respect that constraint? Indeed, this is possible. You can totally do this, and then it would work, and then this whole table would become a single table, and you would be able to return this result. However, this requires the use of window functions, which is a feature that we will see in later lectures. But yes, it is totally possible, and it does solve the problem. Now, here's a special aggregation expression that you should know about because it is often used, which is the count star. And count star is simply counting the total number of rows in a table. And as you can see, if I say from fantasy characters, select count star, I get the total count of rows in my results. And this is a common expression used across all SQL systems to figure out how many rows a table has. And of course, you can also combine it with filters with the where clause in order to get other types of measures. For example, I could say where is alive equals true, and then the count would become actually the count of characters who are alive in my data. So this is a universal way to count rows in SQL, although you should know that if you're simply interested in the total rows of a table and you are working with BigQuery, an easy and totally free way to do it is to go to the Details tab and look at the number of rows here. So this was all I wanted to tell you about simple aggregations for now. And last question is, why do we call them simple? Simple as opposed to what? I call them simple because the way we've seen them until now, the aggregations take all of the values of a column and simply return one summary value. For example, the sum aggregation will take all of the values of the level column and then return a single number, which is the sum of all levels. And more advanced aggregations involved grouping our data. For example, a question we might ask is, what is the average level for mages as opposed to the average level for archers and for hobbits and for warriors and so on? So now you're computing aggregations not over your whole data, but over groups that you find in your data. And we will see how to do that in the lecture on group by. But for now, you can already find out a lot of interesting stuff about your data by running simple aggregations. Let us now look at subqueries and common table expressions. And these are two fundamental functionalities in SQL. These functionalities solve a very specific problem. And the problem is the following. Sometimes you just cannot get the result you require with a single query. Sometimes you have to combine multiple SQL queries to get where you need to go. So here's a fun problem that will illustrate my point. So we're looking at the characters table and we have this requirement. We want to find all those characters whose experience is between the minimum and the maximum value of our experience. Another way to say this, we want characters who are more experienced than the least experienced character, but less experienced than the most experienced character. In other words, we want to find that middle ground that is between the least and the most experienced characters. So let us see how we could do that. I have here a simple start where I am getting the name and experience column from the characters table. Now let us focus on the first half of the problem. Find characters who have more experience than the least experienced character. Now, because this is a toy dataset, I can sort of eyeball it. So I can scroll down here and I can see that the lowest value of experience is Pippin with 2100. And so what I need to do now is to filter out from this table all the rows that have this level of experience. But apart from eyeballing, how would we find the lowest level of experience in our data? If you thought of aggregate functions, you are right. So we have seen in a previous lecture that we have aggregated functions that take any number of values and spit out a single value that's a summary. For example, minimum and maximum. And indeed, we need to use a function like that for this problem. So your first instinct might be, let us take this table and let us filter out rows in this way. So let's say where experience is bigger than the minimum of experience. And on the surface, this makes sense, right? I am using an aggregation to get the smallest value of experience, and then I'm only keeping rows that have a higher value than that. However, as you see from this red line, this actually does not work because it tells us aggregate function is not allowed in the where clause. So what is going on here? So if you followed the lecture on aggregation, you might have a clue as to why this doesn't work, but it is good to go back to it and understand exactly what the problem is. So I'm going back to my Google Sheet over here where I have the exact same data, and I copied our current query down here. And now let's see what happens when SQL tries to run this. So SQL goes to the fantasy characters table, and the second step in the logical order, as you remember, is to filter it. And for the filter, it has to take the column of experience. So let me take this column and copy it down here. And then it has to compute minimum of experience, right? So I will define this column here, and I will use Google Sheets function to achieve that result. So equals min, and then selecting the numbers. And here I get the minimum value of experience. And now SQL has to compare these columns, but this comparison doesn't work, right? Because these are two columns that have a different number of rows. They have a different number of values. So SQL is not able to do this comparison. You cannot do an element by element comparison between a column that has 15 values and a column that has a single value. So SQL throws an error. But you might say, wait, there is a simple solution to this. Just take this value and copy it all over here until you have two columns of the same size, and then you can do the comparison. Indeed, that would work, that's a solution, but SQL doesn't do it automatically. Whereas if you work with other analytics tools such as pandas in Python or NumPy, you will find that in a situation like this would be done automatically. This value would be copied all over here, and there's a process called broadcasting for that. But SQL does not take so many assumptions and so many risks with your data. If it literally doesn't work, then SQL will not do it. So hopefully now you have a better understanding of why this solution does not work. So how could we actually approach this problem? Now, a key insight is that I can run a different query. So I will open this on the right to find out the minimum experience, right? I can go back to the characters table and I can select the minimum of experience. This is simply what we've learned to do in the lecture on aggregations. And I get the value here that is the minimum value of experience. Now that I know the minimum value of experience, I could simply copy this value and insert it here into a where filter. And if I run this, this will actually work. It will solve my problem. The issue, of course, is that I do not want to hard code this value. First of all, it is not very practical to run a separate query and copy paste the value in the code. And second, the minimum value might change someday, and then I might not remember to update it in my code, and then this whole query would become invalid. To solve this problem, I will use a subquery. And I will simply delete the hard-coded value. And I will open round brackets, which is a way to get started on a subquery. And I will take the query that I have over here and put it in the round brackets. And when I run this, I get the result that I need. So what exactly is going on here? We are using a subquery, or in other words, a query within a query. So when SQL looks at this code, it says, all right, so this is the outer query, right? And it has a inner query inside it, a nested query. So I have to start with the innermost query. I have to start with the nested query. So let me compute this. And so SQL runs this query first, and then it gets a value out of it, which in our case, we know that is 2100. And after that, SQL substitutes this code over here by the value that was computed, and we know from before that this works as expected. And to compute the other half of our problem, we want our character to have less experience than the most experienced character. So this is just another condition in the where filter. And so I can add an AND here and copy this code over here, except that now I want my experience to be smaller than the maximum of experience in my table. Now, you might know this trick that if you select only part of your code, like this, and then you click run, SQL will only execute that part of the code. And so here we get the actual maximum for our experience, and we can write it here in the comment. And now we know that when SQL runs this query, all of this will be computed to 15,000, and then experience will be compared on that, and the query will work as intended. And here is the solution to our problem. Now here's a second problem, which shows another side of subqueries. We want to find the difference between a character's experience and their mentors. So let us solve it manually for one case in the characters table. So let us look at this character over here, which is Saruman with ID 11, and their experience is 8500. And then Saruman has character ID 6 as their mentor. So if I look for ID 6, we have Gandalf. This is not very canon compared to the story, but let's just roll with it. And Gandalf has 10,000 of experience. And now if we select the experience of Gandalf minus the experience of Saruman, we can see that there is a 1500 difference between their experience. And this is what I want to find with my query. Now back to my query, I will first alias my columns in order to make them more informative. And this is a great trick to make problems clearer in your head. Assign the right names to things. So here, instead of ID, I will call this Mentee ID. And here I have Mentor ID. And here, instead of experience, I will call this Mentee Experience. So I have just renamed my columns. Now, the missing piece of the puzzle is the mentor experience, right? So how can I get the mentor experience? For example, in the first case, I know that character 11 is mentored by character 6. How can I get the experience of character 6? Now, of course, I can take a new tab over here, split it to the right, go to fantasy characters, filter for ID being equal to 6, which is the ID of our mentor, and get their experience. And the experience in this case is 10,000. This is the same example that we saw before. But now I would have to write this separate query for each of my rows. So here 6 I've already checked, but then I will need to check 2 and 7 and 1, and this is really not feasible, right? And the solution, of course, is to solve it with a subquery. So what I'm gonna do here is open round brackets, and in here I will write the code that I need. And here I can simply copy the code that I've written here, get experience from the characters where ID equals 6. Now, the 6 part is still hard-coded because in the first row, mentor ID is 6. To avoid hard-coding this part, there are two components to this. The first one is noticing that I am referencing the same table, fantasy.characters, in two different places in my code. And this could get buggy and this could get confusing. And the solution is to give separate names to these two instances. Now, what are the right names to give? So, if we look at this outer query right here, this is really information about the mentee, right? Because we have the mentee ID, the ID of their mentor, and the mentee experience. So I can simply call this mentee table. And as you can see, I can alias my table by simply writing it like this, or I could also add the as keyword. It would work just the same. On the other hand, this table will give us the experience of the mentor. This is really information about the mentor, so we can call this mentor table. Now, we're not going to get confused anymore because these two instances have different names. And now, what do we want this ID to be if we're not going to hard code it? We want it to be this value over here. We want it to be the mentor ID value from the mentee table. We want it to be the mentee's mentor. And to refer to that column, I will get the table name dot the column name. So this is telling me get the mentor ID value from mentee table. And now that I have the subquery, which defines a column with these two brackets, I can alias the result just like I always do and run this. And now you will see, after making some room here, that we have successfully retrieved the experience value for the mentor. Now I realize that this is not the simplest process, so let us go back to our query over here and make sure that we understand exactly what is happening. Now, first of all, we're going to the characters table, which contains information about our mentee, the person who is being mentored. And we label the table so that we remember what it's about. We filter it because we're not interested in characters that do not have a mentor. And then we're getting a few data, right? The ID, in this case, represents the ID of the mentee. And we also have their mentor ID. And we also have the experience, which again, this is the table about the mentee, represents the mentee experience. Now, our goal is to also get the experience of their mentor. Our goal is to see that we have a mentor ID 6 and we want to know that their experience is 10,000. And we do that with a subquery. It's a query within a query. And in this subquery, which is an independent piece of SQL code, we are going back to the characters table, but this is another instance of the table, right, that we're looking at. So to make sure we remember that, we call this mentor table because it contains information about the mentor. And how do we make sure that we get the right value over here, that we don't get confused between separate mentors? We make sure that for each row, the ID of the character in this table is equal to the mentor ID value in the mentee table. In other words, we make sure that we plug in this value over here, in this case 6, into the table to get the right row. And then from that row, we get the experience value. All of this code over here defines a new column, which we call mentor experience. And this is basically the same thing that we did manually when we opened a table on the right and queried the table and copy-pasted the hard-coded value. This is just the way to do it dynamically with a subquery. Now we are not fully done with the problem, right? Because we wanted to see the difference between the characters' experience and their mentors. So let's see how to do this. And the way to do it is with a column calculation, just like the ones we've seen before. So given that this column represents the mentor experience, I can remove the alias over here and over here as well, and I can subtract the experience from this, and a column minus a column gives me another column, which I can then alias as experience difference. And if I run this, I will see the value that we originally computed manually, which is the difference between the mentor and the mentee's experience. There's nothing really new about this, as long as you realize that this expression over here defines a column, and this is the reference to a column, and so you can subtract them and then give a name, an alias to the result. And now we can look at our two examples of nested queries side by side, and we can figure out what they have in common and where do they differ. So what they have in common is that they're both problems that you cannot resolve with a simple query, because you need to use values that you have to compute separately, values that you cannot simply refer to by name like we usually do with our columns. In this case, on the left, you need to know what are the minimum and maximum values for experience. And in this case, on the right, you need to know what is the experience of a character's mentor. And so we solve that problem by writing a new query, a nested query, and making sure that SQL solves this query first, gets the result, and then plugs that result back into the original query to get the data we need. There is, however, a subtle difference between these two queries that turns out to be pretty important in practice. And I can give you a clue to what this difference is by telling you that on the right we have something that's called a correlated subquery, and on the left we define this as uncorrelated subquery. Now what does this really mean? It means that here on the left our subqueries are computing the minimum and the maximum experience, and these are actually fixed values for all of our characters. It doesn't matter which character you're looking at, the whole dataset has the same values from minimum experience and maximum experience. So you could even imagine computing these values first before running your queries. For example, you could say minimum experience is the minimum and maximum experience is the max, and then you could imagine replacing these values over here, right? This will not actually work because you cannot define variables like this in SQL, but on a logical level, you can imagine doing this, right? Because you only need to compute these two once. I will revert this here so we don't get confused. On the other hand, on the right, you will see that the value that is returned by this subquery needs to be computed dynamically for every row. This value, as you also see in the results, is different for every row because every row references a different mentor ID. And so SQL cannot compute this one value here for all rows at once, it has to recompute it for every row. And this is why we call it a correlated subquery, because it's connected to the value that is in each row, and so it must run for each row. And an important reason to distinguish between uncorrelated and correlated subqueries is that you can imagine that correlated subqueries are actually slower and more expensive to run because you're running a SQL query for every row, at least at the logical level. So this was our introduction to subqueries. They allow you to implement more complex logic, and as long as you understand it logically, you're off to a great start. And then by doing exercises and solving problems, you will learn with experience when it's the case to use them. In the last lecture, we saw that we could use subqueries to retrieve singular values. For example, what is the minimum value of experience in my dataset? But we can also use subqueries and common table expressions as well to create new tables altogether. So here's a motivating example for that. So what I'm doing in this query right here is that I am scaling the value of level based on the character's class. And you might need this in order to create some balance in your game or for whatever reason. Now, what this does is that if the character is mage, the level gets divided by half or multiplied by 0.5. If the character is archer or warrior, the level, we take the 75% of it, and in all other cases, the level gains 50%. So the details are not very important, it's just an example, but the point is that we modify the value of level based on the character class, and we do this with the case when statement that we saw in a previous lecture. And as you can see in the results, we get a new value of power level for each character that you can see here. But now, let's say that I wanted to filter my characters based on this new column of power level. Say that I wanted to only keep characters that have a power level of at least 15. How would I do that? Well, we know that the where filter can be used to filter rows, so you might just want to go here and add a where statement and say where power level is equal or bigger than 15. But this is not going to work, right? We know this cannot work because we know how the logical order of SQL operations works. And so the case when column that we create, power level, is defined here at the select stage. But the where filter occurs here at the beginning, right after we source our table. So due to our rules, the where component cannot know about this power level column that will actually get created later. So the query that we just wrote actually violates the logical order of SQL operations, and this is why we cannot filter here. Now, there is actually one thing that I could do here to avoid using a subquery and get around this error. And that something would be to avoid using this alias power level that we assign here and that the where statement cannot know about, and replace it with the whole logic of the case when statement. So this is gonna look pretty ugly, but I'm going to do it. And if I run this, you will see that we in fact get the result we wanted. Now, in the where lecture, we saw that the where clause doesn't just accept simple logical statements. You can use all the calculations and all the techniques that are available to you at the select stage. And you can also use case when statements. And this is why this solution here actually works. However, this is obviously very ugly and impractical, and you should never duplicate code like this. So I'm going to remove this where clause over here and show you how you can achieve the same result with a subquery. So let me first rerun this query over here so that you can see the results. And now what I'm going to do, I'm going to select this whole logic over here and wrap it in round brackets. And then up here, I'm going to say select star from. And when I run this new query, this data that I'm seeing over here should be unchanged. So let us run it. And you will see that the data has not changed at all. But what is actually happening here? Well, it's pretty simple. Usually we say select star from fantasy characters, right? And by this, we indicate the name of a table that our system can access. But now, instead of a table name, we are showing a subquery. And this subquery is a piece of SQL logic that obviously returns a table. So SQL will look at this whole code and will say, okay, there is a outer query, which is this one, and there is an inner query, a nested query, which is this one. So I will compute this one first, and then I will treat this as just another table that I can then select from. And now, because this is just another table, we can actually apply a where filter on top of it. We can say where power level is equal or greater than 15, and you will see that we get the result we wanted, just like before. But now our code looks actually better and the case when logic is not duplicated. If you wanted to visualize this in our schema, it would look something like this. So the flow of data is the following. First, we run the inner query that works just like all the other queries we've seen until now. It starts with the from component, which gets the table from the database, and then it goes through the usual pipeline of SQL logic that eventually produces a result, which is a table. Next, that table gets piped into the outer query. The outer query also starts with the from component, but now the from component is not reading directly from the database, it is reading the result of the inner query. And now the outer query goes through the usual pipeline of components, and finally it produces a table, and that table is our result. And this process could have many levels of nesting because the inner query could reference another query which references another query, and eventually we would get to the database, but it could take many steps to get there. And to demonstrate how multiple levels of nesting works, I will go back to my query over here and I will go into my inner query, which is this one, and this is clearly referencing the table in the database, but now instead of referencing the table, I will reference yet another subquery, which can be something like from fantasy characters, where is alive equals true, select star. So I will now run this and we have added yet another subquery to our code. This was actually not necessary at all. You could add the where filter up here, but it is just to demonstrate the fact that you can nest a lot of queries within each other. The other reason I wanted to show you this code is that I hope you will recognize that this is also not a great way of writing code. It can get quite confusing and it is not something that can be easily read and understood. One major issue is that it interrupts the natural flow of reading code because you constantly have to interrupt a query because another nested query is beginning within it. So you will read select star from, and then here another query starts, and this is also querying from another subquery. And after reading all of these lines, you will find this where filter that actually refers to the outer query that has started many lines back. And if you find this confusing, well, I think you're right, because it is. And the truth is that when you read code on the job or in the wild, or when you see solutions that people propose to coding challenges, unfortunately, this is something that occurs a lot. You have subqueries within subqueries within subqueries, and very quickly the code becomes impossible to read. Fortunately, there is a better way to handle this, and a way that I definitely recommend over this, which is to use common table expressions, which we shall see shortly. It is, however, very important that you understand this way of writing subqueries and that you familiarize yourself with it, because whether we like it or not, a lot of code out there is written like this. We've seen that we can use the subquery functionality to define a new table on the fly just by writing some code. A new table that we can then query just like any other SQL table. And what this allows us to do is to run jobs that are too complex for a single query. And to do that without defining new tables in our database and storing new tables in our database. It is essentially a tool to manage complexity, and this is how it works for subqueries. So instead of saying from and then the name of a table, we open round brackets and then we write a independent SQL query in there. And we know that every SQL query returns a table, and this is the table that we can then work on. What we do here is to select star from this table and then apply a filter on this new column that we created in the subquery power level. And now I will show you another way to achieve the same result, which is through a functionality called common table expressions. To build a common table expression, I will take the logic of this query right here and I will move it up. And next I will give a name to this table. I will call it power level table. And then all I need to say is with power level table as, followed by the logic. And now this is just another table that is available in my query, and it is defined by the logic of what occurs within the round brackets. And so I can refer to this over here and query it just like I need. And when I run this, you see that we get the same results as before. And this is how a common table expression works. You start with the keyword with, you give an alias to the table that you're going to create, you put as, open round brackets, write an independent query that will of course return a table under this alias over here, and then in your code you can query this alias just like we've done until now for any SQL table. And although our data result hasn't changed, I would argue that this is a better and more elegant way to achieve the same result, because we have separated in the code the logic for these two different tables. Instead of putting this logic in between this query and sort of breaking the flow of this table, we now have a much cleaner solution where first we define the virtual table that we will need. And by virtual, I mean that we treat it like a table, but it's not actually saved in our database. It's still defined by our code. And then below that, we have the logic that uses this virtual table. We can also have multiple common table expressions in our query, let me show you what that looks like. So in our previous example on subquery, we added another part where here, instead of querying the fantasy characters table, we queried a filter on this characters table, and it looked like this. We were doing select star where is alive equals true. So I'm just reproducing what I did in the previous lecture on subqueries. Now you will notice that this is really not necessary because all we're doing here is add a where filter, and we could do this in this query directly, but please bear with me because I just want to show you how to handle multiple queries. The second thing I want to tell you is, although this code actually works and you can verify for yourself, I do not recommend doing this, meaning mixing common table expressions and subqueries. It is really not advisable because it adds unnecessary complexity to your code. So here we have a common table expression that contains a subquery, and I will rather turn this into a situation where we have two common table expressions and no subqueries at all. And to do that, I will take this logic over here and paste it at the top. And I will give this now an alias. So I will call it characters alive, but you can call it whatever is best for you. And then I will do the keyword as, add some lines in here to make it more readable. And now, once we are defining multiple common table expressions, we only need to do the with keyword once at the beginning, and then we can simply add a comma, and please remember this, the comma is very important. And then we have the alias of the new table, the as keyword, and then the logic for that table. All that's needed to do now is to fill in this from, because we took away the subquery, and we need to query the characters alive virtual table here, and this is what it looks like. And if you run this, you will get your result. So this is what the syntax looks like when you have multiple common table expressions. You start with the keyword with, which you're only going to need once. And then you give the alias of your first table, as keyword, and then the logic between round brackets. And then for every extra virtual table that you want to add, for every extra common table expression, you only need to add a comma, and then another alias, the as keyword, and then the logic between round brackets. And when you are done listing your common table expressions, you will omit the comma. You will not have a comma here because it will break your code. And finally, you will run your main query. And in each of these queries that you can see here, you are totally free to query real tables, material tables that exist in your database, as well as common table expressions that you have defined in this code. And in fact, you can see that our second virtual table here is querying the first one. However, be advised that the order in which you write these common table expressions matters, because a common table expression can only reference common table expressions that came before it. It's not going to be able to see those that came after it. So if I say here, instead of from fantasy characters, I try to query from power level table, you will see that I get an error from BigQuery because it doesn't recognize it basically because the code is below. So the order in which you write them matters. Now, an important question to ask is, when should I use subqueries and when should I use common table expressions? And the truth is that they have a basically equivalent functionality. What you can do with the subquery, you can do with a common table expression. My very opinionated advice is that every time you need to define a new table in your code, you should use a common table expression because they are simpler, easier to understand, cleaner, and they will make your code more professional. In fact, I can tell you that in the industry, it is a best practice to use common table expressions instead of subqueries. And if I were to interview you for a data job, I would definitely pay attention to this issue. But there is an exception to this, and this is the reason why I'm showing you this query, which we wrote in a previous lecture on subqueries. This is a query where you need to get a single specific value, right? So if you remember, we wanted to get characters whose experience is above the minimum experience in the data and also below the maximum experience. So characters that are in the middle. To do this, we need to dynamically find at any point, when this query is being run, what is the minimum experience and the maximum experience. And the subquery is actually great for that. You will notice here that we don't really need to define a whole new table. We just really need to get a specific value. And this is where a subquery works well because it implements very simple logic and doesn't actually break the flow of the query. But for something more complex like power level table, this specific query we're using here, which takes the name, takes the level, then applies a case when logic to level to create a new column called power level. You could do this with a subquery, but I actually recommend doing it with a common table expression. And this is a cool blog post on this topic by the company DBT. It talks about common table expressions in SQL, why they are so useful for writing complex SQL code, and the best practices for using common table expressions. And towards the end of the article, there's also an interesting comparison between common table expressions and subqueries. And you can see that CTE's common table expressions are more readable, whereas subqueries are less readable, especially if there are many nested ones. So, a subquery within a subquery within a subquery quickly becomes unreadable. Recursiveness is a great advantage of CTEs, although we won't examine this in detail. But basically what this means is that once you define a common table expression in your code, you can reuse it in any part of your code. You can use it in multiple parts, right? You can use it in other CTEs, you can use it in your main query, and so on. On the other hand, once you define a subquery, you can really only use it in the query in which you defined it. You cannot use it in other parts of your code, and this is another disadvantage. This is a less important factor, but when you define a CTE, you always need to give it a name, whereas subqueries can be anonymous. You can see it very well here. We of course had to give a name to both of these CTEs, but the subqueries that we're using here are anonymous. However, I wouldn't say that's a huge difference. And finally, you have that CTEs cannot be used in a where clause, whereas subqueries can. And this is exactly the example that I've shown you here. Because this is a simple value that we want to use in our where clause in order to filter our table, subqueries are the perfect use case for this, whereas CTEs are suitable for more complex use cases when you need to define entire tables. In conclusion, the article says CTEs are essentially temporary views that you can use. I've used the term virtual table, but temporary view works just as well, conveys the same idea. They are great to give your SQL more structure and readability, and they also allow reusability. Before we move on to other topics, I wanted to show you what an amazing tool common table expressions are to create complex data workflows. Because common table expressions are not just a trick to execute certain SQL queries, they're actually a tool that allows us to build data pipelines within our SQL code and that can really give us data superpowers. So here I have drawn a typical workflow that you will see in complex SQL queries that make use of common table expressions. Now what we're looking at here is a single SQL query. It's, however, a complex one because it uses CTEs. And the query is represented graphically here and in a simple code reference here. The blue rectangles represent the common table expressions, these virtual tables that you can define with the CTE syntax. Whereas the red square represents the base query, the query at the bottom of your code that ultimately will return the result. So a typical flow will look like this. You will have a first common table expression called T1 that is a query that references a real table, a table that actually exists in your dataset, such as fantasy characters. And of course, this query will do some work, right? It can apply filters, it can calculate new columns, and so on, everything that we've seen until now. And then the result of this query gets piped in to another common table expression. This one is T2, that gets the result of whatever happened at T1 and then applies some further logic to it, applies some more transformations. And then again, the result gets piped into another table where more transformations run, and this can happen for any number of steps until you get to the final query. And in the base query, we finally compute the end result that will then be returned to the user. So this is effectively a data pipeline that gets data from the source and then applies a series of complex transformations. And this is similar to the logical schema that we've been seeing about SQL, right? Except that this is one level further. Because in our usual schema, the steps are done by clauses, by these components of the SQL queries. But here, every step is actually a query in itself. So of course, this is a very powerful feature. And this data pipeline applies many queries sequentially until it produces the final result. And you can do a lot with this capability. And also, you should now be able to understand how this is implemented in code. So we have our usual CTE syntax with, and then the first table we call T1, and then here we have the logic within round brackets for T1. And you can see here that in the from, we are referencing a table in the dataset. And then for every successive common table expression, we just add a comma, a new alias and the logic, comma, new alias and the logic. And finally, when we're done, we write our base query. And you can see that the base query is selecting from T3, T3 is selecting from T2, T2 is selecting from T1, and T1 is selecting from the database. But you are not limited to this type of workflow. Here is another, maybe slightly more complex workflow that you will also see in the wild. And here you can see that at the top we have two common table expressions that reference the database. So you can see it here, like the first one is getting data from table 1 and then transforming it. The second one is getting data from table 2 and then transforming it. And next we have the third CTE that's actually combining data from these two tables over here. So we haven't yet seen how to combine data except through the union. I wrote the join here, which we're going to see shortly, but all you need to know is that T3 is combining data from these two parent tables. And then finally, the base query is not only using the data from T3, but also going back to T1 and using that data as well. And you remember we said that great thing about CTEs is that tables are reusable. You define them once and then you can use them anywhere. Well, here's an example with T1, because T1 is defined here at the top of the code, and then it is referenced by T3, but it is also referenced by the base query. So this is another example of a workflow that you could have, and really the limit here is your imagination and the complexity of your needs. You can have complex workflows such as this one, which can implement very complex data requirements. So this is a short overview of the power of CTEs, and I hope you're excited to learn about them and to use them in your SQL challenges. We now move on to joins, which are a powerful way to bring many different tables together and combine their information. And I'm going to start us off here with a little motivating example. Now, on the left here, I see my characters table, and by now we're familiar with this table. So let's say that I wanted to know for each character how many items they are carrying in their inventory. Now you will notice that this information is not available in the characters table. However, this information is available in the inventory table. So how exactly does the inventory table works? When you are looking at a table for the first time and you want to understand how it works, the best question you can ask is the following: what does each row represent? So what does each row represent in this table? Well, if we look at the columns, we can see that for every row of this table, we have a specific character ID and an item ID, as well as a quantity and some other information as well, such as whether the item is equipped, when it was purchased, and so on. So looking at this, I realized that each row in this table represents a fact. The fact that a character has an item, right? So I know by looking at this table that character ID 2 has item 101 and character ID 3 has item 6, and so on. So clearly I can use this in order to answer my question. So how many items is Gandalf carrying? To find this out, I have to look up the ID of Gandalf, which as you can see here is 6. And then I have to go to the inventory table and in the character ID column, look for the ID of Gandalf, right? Now, unfortunately, it's not ordered, but I can look for myself here and I can see that at least this row is related to Gandalf because he has character ID 6. And I can see that Gandalf has item ID 16 in his inventory. And I'm actually seeing another one now, which is this one, which is 11. And I'm not seeing any other item at the moment. So for now, based on my imperfect visual analysis, I can say that Gandalf has 2 items in his inventory. Of course, our analysis skills are not limited to eyeballing stuff, right? We have learned that we can search a table for the information we need. So I could go here and query the inventory table in a new tab, right? And I could say, give me from the inventory table where character ID equals 6. This should give me all the information for Gandalf. And I could say, give me all the columns. And when I run this, I should see that indeed we have 2 rows here, and we know that Gandalf has items 16 and 11 in his inventory. We don't know exactly what these items are, but we know that he's carrying 2 items. So that's a good start. Okay, but what if I wanted to know which items Frodo is carrying? Well, again, I can go to the characters table and look up the name Frodo, and I find out that Frodo is ID 4. So going here, I can just plug that number into my where filter, and I will find out that Frodo is carrying a single type of item, which has ID 9, although it's in a quantity of 2. And of course, I could go on and do this for every character, but it is quite impractical to change the filter every time. And what if I wanted to know how many items each character is carrying, or at least which items each character is carrying, all at once? Well, this is where joins come into play. What I really want to do in this case is to combine these two tables into one, and by bringing them together to create a new table which will have all of the information that I need. So let's see how to do this. Now, the first question we must answer is, what unites these two tables? What connects them? What can we use in order to combine them? And actually, we've already seen this in our example. The inventory table has a character ID field, which is actually referring to the ID of the character in the characters table. So we have two columns here, the character ID column in inventory and the ID column in characters, which actually represent the same thing, the identifier for a character. And this logical connection, the fact that these columns represent the same thing, can be used in order to combine these tables. So let me start a fresh query over here. And as usual, I will start with the from part. Now, where do I want to get my data from? I want to get my data from the characters table, just as we've been doing until now. However, the characters table is not enough for me anymore. I need to join this table on the fantasy.inventory table. So I want to join these two tables. How do I want to join these two tables? Well, we know that the inventory table has a character ID column, which is the same as the characters table's ID column. So like we said before, these two columns from the different tables, they represent the same thing. So there's a logical connection between them, and we will use it for the join. And I want to draw your attention to the notation that we're using here, because in this query, we have two tables present. And so it is not enough to simply write the name of columns. It is also necessary to specify to which table each column belongs. And we do it with this notation. So the inventory.character is saying that we are talking about the character ID column in the inventory table and the ID column in the characters table. So it's important to write columns with this notation in order to avoid ambiguity when you have more than one table in your query. So until now, we have used the from clause to specify where do we want to get data from. And normally this was simply specifying the name of a table. Here we are doing something very similar, except that we are creating a new table that is obtained by combining two pre-existing tables. Okay, so we are not getting our data from the characters table and we are not getting it from the inventory table, but we are getting it from a brand new table that we have created by combining these two. And this is where our data lives. And to complete the query for now, we can simply add a select star and you will now see the result of this query. So let me actually make some room here and expand these results so I can show you what we got. And as you can see here, we have a brand new table in our result. And you will notice if you check the columns that this table includes all of the columns from the characters table and also all of the columns from the inventory table, as you can see here. And they have been combined by our join statement. Now, to get a better sense of what's happening, let us get rid of this star and let us actually select the columns that we're interested in. And once again, I will write columns with this notation in order to avoid ambiguity. And in selecting these columns, I will remind you that we have all of the columns from the characters table and all of the columns from the inventory table to choose from. So what I will do here is that I will take the ID columns from characters and I will take the name column from characters. And then I will want to see the ID of the item. So I will take the inventory table and the item ID column from that table. And from the inventory table, I will also want to see the quantity of each item. And to make our results clearer, I will order my results by the characters ID and the item ID. And you can see here that we get the result that we needed. We have all of our characters here with their IDs and their name. And then for each character, we can tell which items are in their inventory. So you can see here that Aragorn has item ID 4 in his inventory in quantity of 2. He also has item 99. So because of this, Aragorn has 2 rows. If we look back at Frodo, we see the information that we retrieved before, and the same for Gandalf, who has these 2 items. So we have combined the characters table and the inventory table to get the information that we needed. What does each row represent in our result? Well, it's the same as the inventory table. Each row is a fact, which is that a certain character possesses a certain item. But unlike the inventory table, we now have all the information we want for a character and not just the ID. So here we're showing the name of each character, but we could of course select more columns and get more information for each character as needed. Now a short note on notation. When you see SQL code in the wild and a query is joining on 2 or more tables, people, programmers were usually quite lazy and we don't feel like writing the name of the table all of the time, right? Like we were doing in this case with characters. So what we usually do is that we add an alias on the table like this. So from fantasy characters, call it C, we will join on inventory, call it I, and then basically we use this alias everywhere in the query, both in the instructions for joining and in the column names, and the same with characters. So I will substitute everything here. And yes, maybe it's a bit less readable, but it's faster to write and we programmers are quite lazy, so you'll often see this notation. And you will often also see that in the code we omit the as keyword, which can be, let's say, implicit in SQL code. And so we write it like this: from fantasy.character C, join fantasy.inventory I, and then C and I refer to the two tables that we're joining. And I can run this and show you that the query works just as well. Now, we've seen why join is useful and how it looks like, but now I want you to get a detailed understanding of how exactly the logic of join works. And for this, I'm gonna go back to my spreadsheet, and what I have here is my characters table and my inventory table. These are just like you've seen them in BigQuery, except that I'm only taking 4 rows each in order to make it simpler for the example. And what you see here is the same query that I've just run on BigQuery. This is a query that takes the characters table, joins it on the inventory table on this particular condition, and then picks a few columns from this. So let us see how to simulate this query in Google Sheets. Now, the first thing I need to do is to build the table that I will run my query on. Because as we've said before, the from part is now referencing not the characters table, not the inventory table, but the new table, which is built by combining these two. And so our first job is to build this new table. And the first step to building this new table is to take all of the columns from characters and put them in the new table. And then take all of the columns from inventory and then put them in the new table. And what we've obtained here is the structure of our new table. The structure of our new table is simply created by taking all of the columns of the table on the left along with all of the columns from the table on the right. Now, I will go through each character in turn and consider the join condition. The join condition is that the ID of a character is present in the character ID column of inventory. So let us look at my first character. We have Aragorn and he has ID 1. Now, is this ID present in the character ID column? Yes, I see it here in the first row, so we have a match. Given that we have a match, I will take all of the data that I have in the characters table for Aragorn, and then I will take all of the data in the inventory table for the row that matches. And I have built here my first row. Do I have any other row in the inventory table that matches? Yes, the second row also has a character ID of 1. So because I have another match, I will repeat the operation. I will take all of the data that I have in the left table for Aragorn, and I will add all of the data from the right column in the row that matches. Now, there are no more matches for ID 1 in the inventory table, so I can proceed. And I will proceed with Legolas. He has character ID of 2. Question, is there any row that has the value 2 in the character ID column? Yes, I can see it here. So I have another match. So just like before, I will take the information for Legolas and paste it here. And then I will take the matching row, which is this one, and paste it here. We move on to Gimli because there's no other matches for Legolas. Now, Gimli has ID 3 and I can see a match over here. So I will take the row for Gimli, paste it here, and then take the matching row, character ID 3, and paste it here. Great. Finally, we come to Frodo, character ID 4. Is there any match for this character? I can actually find no match at all. So I do nothing. This row does not come into the resulting table because there is no match. And this completes the job of this part of the query over here, building the table that comes from joining these two tables. This is my resulting table. And now to complete the query, I simply have to pick the columns that the query asks for. So the first column is character.id, which is this column over here. So I will take it and I will put it in my result. The second column I want is character.name, which is this column over here. The third column is the item ID column, which is this one right here. And finally, I have quantity, which is this one right here. And this is the final result of my query. And of course, this is just like any other SQL table, so I can use all of the other things I've learned to run logic on this table. For example, I might only want to keep items that are present in a quantity of 2. And so to do that, I will simply add a where filter here, and I will refer the inventory table because that's the parent table of the quantity column. So I will say I.quantity bigger or equal to 2. And then how my query will work is that first it will build this table like we've seen. So it will do this stage first, and then it will run the where filter on this table, and it will only keep the rows where quantity is at least 2. And so as a result, we will only get this row over here instead of this result that we see right here. Except that we will of course also have to only keep the columns that are specified in the select statement. So we will get ID, name, item ID, and quantity. So this will be the result of my query after I've added a where filter. So let us actually take this and add it to BigQuery and make sure that it works. So I have to add that after the from part and before the order by part, right? This is the order. And after I run this, I will see that indeed I get Aragorn and Frodo. Is not exactly the same as in our sheet, but that's because our sheet has less data. But this is what we want to achieve. And now let us go back to our super important diagram of the order of SQL operation, and let us ask ourselves, where does the join fit in this schema? And as you can see, I have placed join at the very beginning of our flow together with the from, because the truth is that the join clause is not really separate from the from clause. They are actually one and the same component in the logical order of operations. So as you remember, the first stage specifies where our data lives, where do we want to get our data from. And until now, we were content to answer this question with a single table name, with the address of a single table, because all the data we needed was in just one table. And now, instead of doing this, we are taking it a step further. We are saying our data lives in a particular combination of 2 or more tables. So let me tell you which tables I want to combine and how I want to combine them. And the result of this will be, of course, yet another table. And then this table will be the beginning of my flow. And after that, I can apply all the other operations that I've come to know on my table, and it will work just like all our previous examples. The result of a join is, of course, just another table. So when you look at a SQL query and this query includes a join, you really have to see it as one and the same with the from part. It defines the source of your data by combining tables, and everything else that you do will be applied not to a single table, not to any of the tables that you're combining. Everything that you do will be applied to the resultant table that comes from this combination. And this is why from and join are really the same component, and this is why they are the first step in the logical order of SQL operations. Let us now briefly look at multiple joins, because sometimes the data that you need is in 3 tables or 4 tables, and you can actually join as many tables as you want, or at least as many tables as your system allows you to join before it becomes too slow. So we have our example here from before. We have each character and we have their name, and we know which items are in their inventory, but we actually don't know what the items are. We just know their ID. So how can I know that if Aragorn has item 4, what item does Aragorn actually have? What is the name of this item? Now, obviously this information is available in the items table that you have here on the right, and you can see here that we have a name column. And just like before, I can actually eyeball it, I can look for it myself. I know that I'm looking for item ID 4, and if I go here and I go to 4, I can see that this item is a healing potion. And now let us see how we can add this with the join. So now I will go to my query, and after joining with characters and inventory, I will take that result and simply join it on a 3rd table. So I will write join on fantasy.items, and I can call this IT to use a brief form because I am lazy, as all programmers are. And now I need to specify the condition on which to join. So the condition is that the item ID column, which actually came from the inventory table, right? That's its parent. So I'm going to call it inventory.item ID, except that, yeah, I'm referring to inventory as a simple I. That is the brief form, is the same as the items table, the ID column in the items table. And now that I've added my condition, the data that I'm searching is now a combination of these 3 tables. And in my result, I now have access to the columns of the items table. And I can access these columns simply by referring to them. So I will say it.name and some other thing, it.power. And after I run this query, I should be able for each item to see the name and the power, right? So Aragorn has a healing potion with power of 50, Legolas has a elven bow with power of 85, and so on. Now, you may have noticed something a bit curious, and it's that name here is actually written as name_1. And can you figure out why this is happening? Well, it's happening because there's an ambiguity, right? The characters table has a column called name, and the items table also has a column called name. And because BigQuery is not referring to the columns the way we are doing it, right, by saying the parent table and then the name of the column, it would find itself in a position of having 2 identically named columns. So the second one, it tries to distinguish it by adding _1. And how we can remedy this is by renaming the column to something more meaningful. For example, we could say call this item name, which would be a lot clearer for whoever looks at the result of our query. And as you can see, now the name makes more sense. So you can see that the multiple join is actually nothing new, because when we join the first time, like we did before, we have combined two tables into a new one. And then this new table gets joined to a third table. So it's simply repeating the join operation twice. It's nothing actually new. But let us actually simulate a multiple join in our spreadsheet to make sure that we understand it and that it's nothing new. So again, I have our tables here, but I have added the items table, which we will combine. And I've written here our query, right? So take the characters table and join it with inventory like we did before. And then take the result of that table and join it to items. And here we have the condition. So the first thing we need to do is to process our first join. And this is actually exactly what we've done before. So let us do it again. First of all, the combined table, characters and inventory, its structure is obtained by taking all the columns of characters and then all the columns of inventory and putting them side by side. And this is the result table. Now for the logic of this table, I will now do it faster because we've done it before, but basically we get the first character ID1, it has two matches, so I'll actually take these values and put them into two rows. And for the inventory part, I will simply copy these two rows to complete my match. Then we have Legolas. There is one match here, so I will take the left side and I will take, so I'm looking for ID2, so I will take this row over here. That's all we have. And then we have Gimli, and he also has one match, so I'll take it here and the resulting column. And then finally, Frodo has no match, so I will not add him to my result. This is exactly what we've done before. So now that we have this new table, we can proceed with our next join, which is with items. Okay, so the resulting table will be the result of our first join combined with items. And to show you that we've already computed this, and now it's one table, I have added round brackets. Now the rules for joining are just the same. So take all of the columns in the left side table and then take all of the columns in the right side table. And now we have the resulting structure of our table. And then let us go through every row. So let us look at the first row. What does the join condition say? Item ID needs to be in the ID table of items. So I can see a match here. So I will simply take this row on the left side and the matching row on the right side and add it here. Second row, the item ID is 4. Do I have a match? Yes, I can see that I have a match. So I will paste the row on the left and the matching row on the right. Third column, item ID 2. Do I have a match? No, I don't. So I don't need to do anything. And in the final row, item ID 101, I don't see a match, so I don't have to do anything. And so this is my final result. In short, multiple join works just like a normal join. Combine the first two tables, get the resulting table, and then keep doing this until you run out of joins. Now, there's another special case of join, which is the self-join. And this is something that people who are getting started with SQL tend to find confusing. But I want to show you that there's nothing confusing about it, because really it's just a regular join that works just like all the other joins that we've seen. There's nothing actually special about it. So we can see here the characters table. And you might remember that for each character, we have a column of mentor ID. Now, in a lot of cases, this column has value null, so it means that there's nothing there. But in some cases, there is a value there. And what this means is that this particular character, so we are looking at number 3, that is Saruman, this particular character has a mentor. And who is this mentor? All we know is that their ID is 6. And it turns out that the ID in this column is referring to the ID in the characters table. So to find out who 6 is, I just have to look who has an ID of 6, and I can see that it is Gandalf. So by eyeballing it, I know that Saruman has a mentor, and that mentor is Gandalf. And then Elrond also has the same mentor, which is Gandalf. So I can solve this by eyeballing the table, but how can I get a table that shows for each character who has a mentor who their mentor is? It turns out that I have to take the characters table and join it on the characters table on itself. So let's see how that works in practice. So let me start a new query here on the right. And so my goal here is to list every character in the table and then to also show their mentor if they have one. So I will of course have to get the characters table for this, and the first time I take this table, it is simply to list all of the characters, right? So to remind myself of that, I can give it a label which is chars. Now, as you know, each character has a mentor ID value, but to find out what is the name of this mentor, I actually need to look it up in the characters table. So to do this, I will join on another instance of the characters table, right? This is another, let's say, copy of the same data. But now I'm going to use it for a different purpose. I will not use it to list my characters. I will use it to get the name of the mentor. So I will call this mentors to reflect this use. Now, what is the logical connection between these two copies of the characters table? Each character in my list of characters has a mentor ID field, and I want to match this on the ID field of my mentors table. So this is the logical connection that I'm looking for. And I can now add a select star to quickly complete my query and see the results over here. So the resulting table has all of the columns of the left table and all of the columns of the right table, which means that the columns of the characters table will be repeated twice in the result, as you can see here. But on the left, I simply have my list of characters. Okay, so the first one is Saruman. And then on the right, I have the data about their mentor. So Saruman has a mentor ID of 6, and then here starts the data about the mentor. He has ID of 6, and his name is Gandalf. So you can see here that our self-join has worked as intended. But this is actually a bit messy. We don't need all of these columns. So let us now select only the columns that we need. So from my list of characters, I want the name. And then from the corresponding mentor, I also want the name. And I will label these columns so that they make sense to whoever is looking at my data. So I will call this character name, and I will call this mentor name. And when I run this query, you can see that quite simply, we get what we wanted. We have the list of all our characters, at least the ones who have a mentor. And for each character, we can see the name of their mentor. So a self-join works just like any other join, and the key to avoiding confusion is to realize that you are joining on two different copies of the same data, okay? You're not actually joining on the same exact table. So one copy of fantasy characters we call characters and we use for a purpose, and then a second copy we call mentors and we use for another purpose. And when you realize this, you see that you are simply joining two tables and all the rules that you've learned about normal joins apply. It just so happens that in this case, the two tables are identical because you're getting the data from the same source. And to drive the point home, let us quickly simulate this in our trusty spreadsheet. And so as you can see here, I have the query that I've run in BigQuery, and we're now going to simulate it. So the important thing to see here is that we're not actually joining one table to itself, although that's what it looks like. We're actually joining two tables which just happen to look the same, okay? And so one is called chars and one is called mentors based on the label that we've given them. But then once we join them, the rules are just the same as we've seen until now. So to create the structure of the resulting table, take all the columns from the left and then take all the columns from the right. And then go row by row and look for matches based on the condition. Now, the condition is that mentor ID in chars needs to be in the ID column of mentors. So first row, Aragorn has mentor 2. Is this in the ID column? Yes, I can see a match here. So let me take all the values from here and all the values from the matching rows, paste them together. Are there any other matches? No. Second row, we're looking for mentor ID 4. Do we have a match? Yes, I can see it here. So let me take all of the values from the left and all of the values from the matching row on the right. Now we have two more rows, but as you can see, in both cases, mentor ID is null, which means that they have no mentor. And basically, for the purposes of the join, we can ignore these rows. We are not going to find a match in these rows. In fact, as an aside, even if there was a character whose ID was null, we wouldn't match with mentor ID null on a character whose ID was null, because in SQL, in a sense, null does not equal null, because null is not a specific value, but it represents the absence of data. So in short, when mentor ID is null, we can be sure that in this case, there will be no match and the row will not appear in the join. Now that we have our result, we simply need to select the columns that we want. And so the first one is name, which comes from the chars table, which is this one over here. And the second one is name that comes from the mentors table, which is this one over here. And here is our result. So that's how a self-join works. So until now, we have seen join conditions, which are pretty strict and straightforward, right? So there's a column in the left table and there's a column in the right table and they represent the same thing. And then you look for an exact match between those two columns, and typically they're an ID number, right? So one table has the item ID, the other table also has the item ID, and then you look for an exact match, and if there's an exact match, you include the row in the join, otherwise not. That's pretty straightforward, but what I want to show you here is that the join is actually much more flexible and powerful than that. And you don't always need, two columns that represent the exact same thing or an exact match in order to write a joining condition. In fact, you can create your own, complex conditions and combinations that decide how to join two tables. And for this, you can simply use the Boolean algebra magic that we've learned about in this course and that we've been using, for example, when working on the where filter. So let us see how this works in practice. Now, I've tried to come up with an example that will illustrate this. So let's say that we have a game, a board game or video game or whatever, and we have our characters and we have our items, okay? And in our game, a character cannot simply use all of the items in the world, okay? There is a limit to which items a character can use. And the limit is based on the following rule. Let me write it here as a comment and then we will use it in our logic. So a character can use any item for which the power level is equal or greater than the character's experience divided by 100. Okay, so this is just a rule that exists in our game. And now let us say that we wanted to get a list of all characters and the items that they can use. Okay, and this is clearly a case where we would need a join. So let us actually write this query. I will start by getting my data from fantasy.characters, and I will call this C as a shorthand, and I will need to join on the items table, right? And what is the condition of the join? The condition of the join is that the character's experience divided by 100 is greater or equal than the item's power level. And I forgot here to add a shorthand I for the items table. So this is the condition that reflects our rule. And out of this table that I've created, I would like to see the character's name and the character's experience divided by 100. And then I would like to see the item's name and the item's power to make sure that my join is working as intended. So let us run this and look at the result. So this looks a bit weird because we haven't given a label to this column, but basically I can see that I have Gandalf and his experience divided by 100 is 100, and he can wear the item Excalibur that has a power of 100, which satisfies our condition. Let me actually order by character name so that I can see in one place all of the items that a character can wear. So we can see that Aragorn is first and his experience divided by 100 is 90, and then this is the same in all of these rows that we see right now, but then we see all of the items that Aragorn is allowed to use and we see their power, and in each case you will see that their power does not exceed this value on the left. So the condition that we wrote works as intended. So as you can see, what we have here is a Boolean expression, just like the ones we've seen before, which is a logical statement that eventually, if you run it, it evaluates to either true or false. And all of the rules that we've seen for Boolean expressions apply here as well. For example, I can decide that this rule over here does not apply to mages because mages are special. And then I can say that if a character is mage, then I want them to be able to use all of the items. Well, how can I do this in this query? Can you pause the video and figure it out? So what I can do is to simply expand my Boolean expression by adding an OR, right? And what I want to test for is that character class equals mage. So let me check for a second that I have class and I have mage, so this should work. And if I run this, going through the result, I will not do it, but you can do it yourself and verify for yourself that if a character is a mage, you will find out that they can use all of the items. And this, of course, is just a Boolean expression in which you have two statements connected by an OR. So if any of these is true, if at least one of these two is true, then the whole statement will evaluate to true, and so the row will match. If you have trouble seeing this, then go back to the video on the Boolean algebra, and everything is explained in there. So this is just what we did before when we simulated the join in the spreadsheet. You can imagine taking the left side table, which is characters, and then going row by row, and then for the first row, you check all of the rows in the right side table, which is items, all of the rows that have a match. But this time, you won't check if the ID corresponds. You will actually run this expression to see whether there is a match. And when this expression evaluates as true, you consider that to be a match and you include the row in the join. However, if this condition does not evaluate to true, it's not a match, and so the row is not included in the join. So this is simply a generalization from the exact match, which shows you that you can use any conditions in order to join two tables. Now, I've been pretending that there is only one type of join in SQL, but that is actually not true. There are a few different types of join that we need to know. So let us see what they are and how they work. Now, this is the query that we wrote before, and this is exactly how we've written it before. And as you can see, we've simply specified join. But it turns out that what we were doing all the time was something called inner join, okay? And now that I've written it explicitly, you can see that if I rerun the query, I will get exactly the same results. And this is because the inner join is by far the most common type of join that you find in SQL. And so in many styles of SQL, such as the one used by BigQuery, they allow you to skip this specification and they allow you to simply write join, and then it is considered as an inner join. So when you want to do an inner join, you have the choice whether to specify it explicitly or to simply write join. But what I want to show you now is another type of join called left join, okay? And to see how that works, I want to show you how we can simulate this query in the spreadsheet. So as you can see, this is very similar to what we've done before. I have the query that I want to simulate, and notice the left join, and then I have my two tables. Now, what is the purpose of the left join? In the previous examples, which were featuring the inner join, we've seen that when we combine two tables with an inner join, the resulting table will only have rows that have a match in both tables, okay? So what we did is that we went through every row in the characters table, and if it had a match in the inventory table, we kept that row. But if there was no match, we completely discarded that row. But what if we wanted, in our resulting table, to see all of the characters, to make sure that our list of characters was complete, regardless of whether they had a match in the inventory table? This is what left join is for. Left join exists so that we can keep all of the rows in the left table, whether they have a match or not. So let us see that in practice, okay? So we need to do a left join between characters and inventory. So first of all, I need to determine the structure of the resulting table. And to do this, I will take all of the columns from the left table and all of the columns from the right table. Nothing new there. Next step, let us go row by row in the left table and look for matches. So we have Aragorn, and he actually has two matches. By now we've remembered this, so these two rows have a match in character ID with the ID of characters. So I will take these two rows and add them to my resulting table. Next is Legolas, and I see a match here. So I will take the rows where Legolas matches and put it here. It's only one row actually. Gimli has also a single match, so I will create the row over here. And so this is the match for Gimli. And of course, I can ensure that I'm doing things correctly by looking at this ID column and this character ID column over here, and they have to be identical, right? If they're not, then I've made a mistake. And finally, we come to Frodo. Now, Frodo, you will see, does not have a match in this table. So before, we basically discarded this row because it had no match. Right now, though, we are dealing with a left join. That means that all of the rows in the characters table need to be included. So I don't have a choice. I need to take this row and include it and add it here. And now the question is, what values will I put in here? Well, I cannot put any value from the inventory table because I don't have a match. So the only thing that I can do is to put nulls in here. Nulls, of course, represent the absence of data. So they're perfect for this use case. And that basically completes the sourcing part of our left join. Now, you may have noticed that there is an extra row here in inventory which does not have a match, right? It is referring to character ID 10, but there is no character ID 10. So here, the Frodo row also did not have a match, but we included it. So should we include this row as well? The answer is no. Why not? Because this is a left join, okay? So left join means that we include all of the rows in the left table, even if they don't have a match. But we do not include rows in the right table when they do not have a match, okay? This is why it's a left join. So, but if you're still confused about this, don't worry, because it will become clearer once we see the other types of join. And of course, for the sake of completeness, I can actually finish the query by selecting my columns, which would be the character ID and the character name and the item ID and the item quantity. And this is my final result. And in the case of Frodo, we have null values, which tells us that this row found no match in the right table, which in this case means that Frodo does not have any items. Now that you understand the left join, you can also easily understand the right join. It is simply the symmetrical operation to the left join, right? So whether you do characters left join inventory or you do inventory right join characters, the result will be identical. It's just a symmetrical operation, right? This is why I wrote here that table A left join B equals table B right join A. So hopefully that's pretty intuitive. But of course, if I did characters right join inventory, then the results would be reversed, because I would have to keep all of the rows of inventory, regardless of whether they have a match or not, and only keep rows in characters which have a match. So if you experiment for yourself on the data, you will easily convince yourself of this result. Let us now see the left join in practice. So remember the query from before, where we take each character and then we see their mentor. This is the code exactly as we've written it before. And so now you know that this is an inner join, because when you don't specify what type of join you want, SQL assumes it's an inner join. At least that's what the SQL in BigQuery does. And you can see that if I write inner join, I think I have a typo there. The result is absolutely identical. And in this case, we're only including characters who have a mentor, right? We are missing out on characters who don't have a mentor, meaning that mentor ID is null. because in the inner join, there is no match, and so they are discarded. But what would happen if I went here and instead turned this into a left join? What I expect to happen is that I will keep all of my characters, so all of the rows from the left side table, regardless of whether they have a match or not, regardless of whether they have a mentor or not. And so let us run this and let us see that this is in fact the case. I now have a row for each of my characters, and I have a row for Gandalf, even though Gandalf does not have a mentor, and so I have a null value in here. So the left join allows me to keep all of the rows of the left table. Now, we've seen the inner join, the left join, and the right join, which are really the same thing, just symmetrical to each other. And finally, I want to show you the full outer join. This is the last type of join that I want to show you. Now you will see that a full outer join is like a combination of all of the joins that we've seen until now. So a full outer join gives us all of the rows that have a match in the two tables, plus all of the rows in the left table that don't have a match with the right table, plus all of the rows in the right table that don't have a match in the left table. So let us see how that works in practice. What I have here is our usual query, but now, as you can see, I have specified a full outer join. So let us now simulate this join between the two tables. Now the first step, as usual, is to take all of the columns from the left table and all of the columns from the right table to get the structure of the resulting table. And now I will go row by row in the left table. So as usual, we have Aragorn, and you know what? I'm already going to copy it here because even if there's not a match, I still have to keep this row because this is a full outer join and I'm basically not discarding any row. Now that I've copied it, is there a match? Well, I already know from the previous examples that there are two rows in the inventory table that match because they have character ID 1. So I'm just gonna take them and copy them over here. And in the second row, I will need to replicate these values. Perfect. Let me move on to Legolas. And again, I can already paste it because there's no way that I'm going to discard this row. But of course we know that Legolas has a match. And moving quickly, because we've already seen this, Gimli has a match as well. And now we come to Frodo. Now, Frodo, again, I can already copy it because I'm keeping all the rows. But Frodo does not have a match. So just like before with the left join, I'm going to keep this row, but I'm going to add null values in the columns that come from the inventory table. So now I've been through all of the rows in the left table, but I'm not done yet with my join. Because in a full outer join, I have to also include all of the rows from the right table. So now the question is, are there any rows in the inventory table that I have not considered yet? And for this, I can check the inventory ID from my result, 1, 2, 3, 4, and compare it with the ID from my table, 1, 2, 3, 4, 5, and then I realize that I have not included row number 5 because it was not selected by any match. But since this is a full outer join, I will add this row over here. I will copy it. And of course, it has no correspondent in the left table. So what do? Once again, I will insert null values. And that completes the first phase of my full outer join. The last phase is always the same, right? Pick the columns that are listed in the select. So you have the ID, the name, item ID, and quantity. And this completes my full outer join. So remember how I said that a full outer join is like an inner join plus a left join plus a right join? Here is a visualization that demonstrates. Now, in the result, the green rows are the rows in which you have a match on the left table and the right table, right? And these rows correspond to the inner join. And if you run an inner join, this will be the only rows that are returned, right? Now, the purple row is including a row that is present in the left table, but does not have any match in the right table. So if you were to run a left join, what would the result be? A left join would include all of the green rows because they have a match. And additionally, they would also include the purple row because in the left join, you keep all of the rows from the left. If, on the other hand, you were to run a right join and you wouldn't like swap the names of the tables or anything, right? You would do characters, right join, inventory. You would get, of course, all of the green rows because they are a match. Additionally, you would get the blue row at the end because this row is present in the right table, even though there's no match. And in the right join, we want to keep all the rows that are in the right table. And finally, in a full outer join, you will include all of these rows, right? So first of all of the rows that have a match, and then all of the rows in the left table, even though they don't have a match, and finally, all of the rows in the right table, even though they don't have a match. And these are the 3 or 4 types of join that you need to know and that you will find useful in solving your problems. Now, here's yet another way to think about joins in SQL and to visualize joins, which you might find helpful. So one way to think about SQL tables is that a table is a set of rows and that joins correspond to different ways of combining sets. And you might remember this from school. This is a Venn diagram. It represents the relation between two sets and the elements that are inside these two sets. So you can take set A to be our left table, containing all of the rows from the left table, and set B to be our right table with all of the rows from the right table. And in the middle here, you can see that there is an intersection between the sets. This intersection represents the rows that have a match. So these would be the rows that I have colored green in our example over here. So what will happen if I want to see only the rows that are a match, only the rows that belong in both tables? Let me select this now, and you can see that this corresponds to an inner join because I only want to get the rows that have a match. Then what would happen if I wanted to include all of the rows in the left table, regardless of whether they have a match or not? To what type of join does that correspond? I will select it here, and you can see that that corresponds to a left join. The left join produces a complete set of records from table A with the matching records in table B. If there is no match, the right side will contain null. Likewise, if I wanted to keep all of the rows in table B, including the ones that match with A, I would of course get a right join, which is just symmetrical to a left join. Finally, what would I have to do to include all of the rows from both tables, regardless of whether they have a match or not? If I do this, then I will get a full outer join. So this is just one way to visualize what we've already seen. There is one more thing you can actually realize from this tool, which is in some cases you might want to get all of the records that are in A except those that match in B. So all of the records that A does not have in common with B. And you can see how you can actually do this. This is actually a left join with an added filter where the B key is null. So what does that mean? The meaning will be clear if I go back to our example for the left join. You can see that this is our result for the left join, and because Frodo had no match in the right table, the ID column over here is null. So if I take this table and I apply a filter where inventory ID is null, I will only get this result over here, and this is exactly the one row in the left table that does not have a match in the right table. So this is more of a special case. You don't actually see this a lot in practice, but I wanted to show it briefly to you in case you try it and get curious about it. Likewise, the last thing that you can do, you could get all of the rows from A and B that do not have a match. So the set of records unique to table A and table B, and this is actually very similar. You do a full outer join and you check that either key is null. So either inventory ID is null or character ID is null. And if you apply that filter, you will get these two rows, which is the set of rows that are in A and only in A, plus the rows that are in B and only in B. Once again, I've honestly never used this in practice. I'm just telling you for the sake of completeness in case you get curious about it. Now, a brief but very important note on how SQL organizes data. So you might remember from the start of the course that I've told you that in a way, SQL tables are quite similar to spreadsheet tables, but there are two fundamental differences. One difference is that each SQL table has a fixed schema, meaning we always know what the columns are and what type of data they contain. And we've seen how this works extensively. The second thing was that SQL tables are actually connected with each other, which makes SQL very powerful. And now we are finally in a position to understand just exactly how SQL tables can be connected with each other. And this will allow you to understand how SQL represents data. So I came here to dbdiagram.io, which is a very nice website for building representations of SQL data. And this is this type of chart of representation that we see here is also known as ERD, as you can see me writing here, which is stands for Entity Relationship Diagram. And it's basically a diagram that shows you how your data is organized in your SQL system. And so you can see a representation of each table. This is the example that's shown on the website. And so you have three tables here: users, follows, and posts. And then for each table, you can see the schema, right? You can see that the users table has 4 columns. One is the user ID, which is an integer. The other is the username, which is varchar. This is another way of saying string. So this is a piece of text. Role is also a piece of text. And then you have a timestamp that shows when the user was created. And the important thing to notice here is that these tables are actually, they don't exist in isolation, but they are connected with each other. They are connected through these arrows that you see here. And what do these arrows represent? Well, let's look at the follows table, okay? So each row of this table is a fact, shows that one user follows another. And so in each row you see the ID of the user who follows and the ID of the user who is followed, as well as the time when this event happened. And what are these arrows telling us? They're telling us that the IDs in this table are the same thing as the user ID column in this table, which means that you can join the follows table with the users table to get the information about the two users that are here, the user who is following and the user who is followed. So, like we've seen before, a table has a column which is the same thing as another table's column, which means that you can join them to combine their data. And this is how in SQL several tables are connected with each other. They are connected by logical correspondences that allow you to join those tables and combine their data. Likewise, you have the posts table, and each row represents a post, and each post has a user ID. And what this arrow is telling you is that you can join on the user table using this ID to get all the information you need about the user who has created this post. Now, of course, as we have seen, you are not limited to joining the tables along these lines. You can actually join these tables on whatever condition you can think of. But this is a guarantee of consistency between these tables that comes from how the data was distributed. And it's a guarantee, it's a promise that you can get the data you need by joining on these specific columns. And that is really all you need to know in order to get started with joins and use them to explore your data and solve SQL problems. To conclude this section, I want to go back to our diagram and to remind you that from and join are really one and the same. They are the way for you to get the data that you need in order to answer your question. And so when the data is in one table alone, you can get away with just using the from and then specifying the name of the table. But often your data will be distributed in many different tables. So you can look at the ERD diagram, such as this one, if you have it, to figure out how your data works. And then once you decided which tables you want to combine, you can write a from which combines with a join, and so create a new table which is a combination of two or more tables, and then all of the other operations that you've learned will run on top of that table. We are finally ready for an in-depth discussion of grouping and aggregations in SQL. And why is this important? Well, as you can see, I have asked ChatGPT to show me some typical business questions that can be answered by data aggregation. So let's see what we have here. What's the total revenue by quarter? How many units did each product sell last month? What is the average customer spend per transaction? Which region has the highest number of sales? Now, as you can see, these are some of the most common and fundamental business questions that you would be asking when you do analytics. And this is why grouping and aggregation are so important when we talk about SQL. Now let's open our data once again in the spreadsheet and see what we might achieve through aggregation. So I have copied here 4 columns from my characters table: guild, class, level, and experience. And I'm going to be asking a few questions. The first question, which you can see here, is what are the level measures by class? So what does this mean? Well, earlier in the course, we looked at aggregations. And we call them simple aggregations because we were running them over the whole table. So you might remember that if I select the values for level here, I will get a few different aggregations in the lower right of my screen. So what you can see here is that I have a count of 15, which means that there are 15 rows for level, and that the maximum level is 40, the minimum is 11, and then I have an average level of 21.3 more or less, And if you sum all the levels, you get 319. So this is already some useful information. But now I would like to take it a step further, and I would like to know these aggregate values within each class. So for example, what is the maximum level for warriors? And what is the maximum level for hobbits? Are they different? How do they compare? This is where aggregation comes into play. So let us do just that now. Let us find the maximum level within each class. And let us see how we might achieve this. Now, to make things quicker, I'm going to sort the data to fit my purpose. So I will select the range over here and then go to Data, Sort Range, and then in the advanced options, I will say that I want to sort by column B because that's my class. And now, as you can see, the data is ordered by class, and I can see the different values for each class. Next, I will take all the different values for class and separate them just like this. So first I have archer, then I have hobbit, then I have mage, and finally I have warrior. So here they are, they're all have their own spot right now. Finally, I just need to compress each of these ranges so that each of them covers only one row. So for archer, I will take the value of the class archer, and then I will have to compress these numbers to a single number. And to do that, I will use the max function. This is the aggregation function that we are using. And quite intuitively, this function will look at the list of values, will pick the biggest one, and it will reduce everything to the biggest value. And you can also see it here in this tooltip over here. Doing the same for hobbit, compress all of the values to a single value, and then compress all of the numbers to a single number by applying an aggregation function. So I've gone ahead and done the same for mage and warrior, and all that's left to do is to take this and bring all these rows together, and this is my result. This is doing what I have asked for. I was looking to find the maximum level within each class. So I have taken all the unique values of class and then all the values of level within each class. I have compressed them to a single number by taking the maximum. And so here I have a nice summary which shows me what the maximum level is for each class. And I can see that mages are much more powerful than everyone, and that hobbits are much more weaker according to this measure. I've learned something new about my data. Now, crucially, and this is very important, in my results, I have class, which is a grouping field, and then level, which is an aggregate field. Okay, so what exactly do I mean by this? Now, class is a grouping field because it divides my data in several groups. So based on the value of class, I have divided my data as you see here. So archer has 3 values, hobbit has 4 values, and so on. Level is an aggregate field because it was obtained by taking a list of several values. So here we have 3, here we have 4, and in the wild we could have 1,000 or 100,000 or millions. It doesn't matter. It's a list of multiple values. And then I've taken these values and compressed them down to one value. I have aggregated them down to one value. And this is why level is an aggregate field. And whenever you work with groups and aggregations, you always have this division, okay? You have some fields that you use for grouping, for subdividing your data. And then you have some fields on which you run aggregations. And aggregations, such as, for example, looking at a list of value and taking the maximum value, or the average, or the minimum, and so on. Aggregations are what allow you to understand the differences between groups. So after aggregating, you can say, oh, well, the mages are certainly much more powerful than the hobbits, and so on. And if you work with dashboards like Tableau or other analytical tools, you will see that another way to refer to these terms is by calling the grouping fields dimensions and the aggregate fields measures, okay? So I'm just leaving it here. You can say grouping field and aggregate field, or you can talk about dimensions and measures, and they typically refer to the same type of idea. Now, let's see how I can achieve the same result in SQL. So I will start a new query here, and I want to get data from fantasy.characters. And after I've sourced this table, I want to define my groups. Okay, so I will use group by, which is my new clause. And then here I will have to specify the grouping field. I will have to specify the group that I want to use in order to subdivide the data. And that group is class in this case. After that, I will want to define the columns that I want to see in my result. So I will say select, and first of all, I want to see the class, and then I want to see the maximum level within each class. So if I run this, you will see that I get exactly the same result that I have in Google Sheets. So we have seen this before. Max is an aggregation function. It takes a list of values and then compresses them down to a single value, right? Except that before we were running it at the level of the whole table, right? So if I select this query alone and run it, what do you expect to see? I expect to see a single value because it has looked at all the levels in the table and it has simply selected the biggest one. It has reduced all of them to a single value. However, if I run it after defining a group by, then this will run not on the whole table at once, it will run within each group identified by my grouping field and will compute the maximum within that group. And so the result of this will be that I can see the maximum level for each group. Now I'm going to delete this, and I don't need to limit myself to a single aggregation. I can write as many aggregations as I wish. So I will put this down here and I'll actually give it a label so that it makes sense. And then I will write a bunch of other aggregations such as count star, which basically is the number of values within that class. I can also look at the minimum level. I can also look at the average level. So let's run this and make sure that it works. So as you can see, we have our unique values for class as usual. And then for each class, we can compute as many aggregated values as we want. So we have the maximum level, the minimum level, and we didn't give a label to this, so we can call it average level. And then number of values, n values, is not referring to level in itself. It's a more general aggregation, which is simply counting how many examples I have of each class, right? So I know I have 4 mages, 3 archers, 4 hobbits, and 4 warriors by looking at this value over here. And here's another thing. I am absolutely not limited to the level column. As you can see, I also have the experience column, which is also an integer, and the health column, which is a floating point number. So I can get the maximum health and I can get the minimum experience. And it all works all the same. All the aggregations are computed within each class. But one thing I need to be really careful of is the match between the type of aggregation that I want to run and the data type of the field on which I plan to run it. So all of these that we show here, they're number columns, right? Either integers or floats. What would happen if I ran the average aggregation on the name column, which is a string? What do you expect to happen? You can already see that this is an error. Why? No matching signature for aggregate function average for the type string. So it's saying this function does not accept the type string. It accepts integer, float, and all types of number columns. But if you ask me to find the average between a bunch of strings, I have no idea how to do that. So I can add as many aggregations as I want within my grouping, but the aggregations need to make sense. But these expressions can be as complex as I want them to be. So instead of taking the average of the name, which is a string and doesn't make sense, I could actually run another function instead of this, inside of this, which is length. And what I expect this to do is that for each name, it will count how long that name is. And then after I've done all these counts, I can aggregate them. I could take the average for them. And what I get back is the average name length within each class. Doesn't sound really helpful as a thing to calculate, but this is just to show you that these expressions can get quite complex. Now, whatever system you're working with, it will have a documentation in some place which lists all the aggregate functions that you have at your disposal. So here is that page for BigQuery, and as you can see, here we have our aggregate functions, and if you go through the list, you will see some of the ones that I've shown you, such as count, max, min, and some others that I haven't shown you in this example, such as sum, so summing up all the values, any value, which simply picks one value. I think it happens at random, and array ag, which actually builds a list out of those values, and so on. So when you need to do an analysis, you can start by asking yourself, how do I want to subdivide the data? What are the different groups that I want to find in the data? And then after that, you can ask yourself, what type of aggregations do I need within each group? What do I want to know about each group? And then you can go here and try to find the aggregate function that works best. And once you think you found it, you can go to the documentation for that function and you can read the description. So returns the average of non-null values in an aggregated group. And then you can see what type of argument is supported. For example, average supports any numeric input type, right? So any data type that represents a number, as well as interval, which represents a space of time. Now, in the previous example, we have used a single grouping field, right? So if we go back here, we have our grouping field, which is class, and we only use this one field to subdivide the data. But you can actually use multiple grouping fields. So let's see how that works. What I have here is my items table, and for each item we have an item type and a rarity type. And then for each item we know the power. So what would happen if we wanted to see the average power by item type and rarity combination? One reason we might want to see this is that we might ask ourselves, is within every item type, is it always true that if you go from common to rare to legendary, the power increases? Is this true for all item types or only for certain item types? Let us go and find out. So what I'm going to do now is that I'm going to use two fields to subdivide my data. I'm going to use item type and rarity. And to do this, as a first step, I will sort the data so that it makes it convenient for me. So I will go here and I will say sort range, advanced, ranged sorting option. And first of all, I want to sort by column A, which is item type. And then I want to add another sort column, which will be column B. And you can see that my data has been sorted. Next, I'm going to take each unique combination of the values of my two grouping fields, okay? So the first combination is armor common. So I'm going to take this here, and then I'm going to write down all the values that come within this combination. So in this case, we only have one value, which is 40. Next, I have armor legendary. And within this combination, I only have one value, which is 90. Next, I have armor rare. So for armor rare, I actually have two values. So I'm going to write them here. Next, we have potion and common. For this, we actually have three values. So I'm going to write them here. So I've gone ahead and I've done it for each combination. And you can see that each unique combination of item type and rarity, I've now copied the relevant values. And now I need to get the average power within these combinations. So I will take the first one, put it over here, and then I will take the average of the values. This is quite easy because there's a single value, so I'll simply write 40. Next, I will take the armor legendary combination, and once again, I have a single value. For armor rare, I have two values, so I will actually press equal and write average to call the spreadsheet function, and then select the two values in here to compute the average. And here we have it. And I can go on like this, potion common, get the average within these values. Potion legendary is a single value. So I've gone ahead and completed this, and this gives me the result of my query. Here I have all the different combinations for the values of, what were they? Item type and rarity. And within each combination, the average power. So to answer my question, is it that within each item type, the power grows with the level of rarity? Where for armor, it goes from 40 to 74 to 90. So yes. For potion, we don't have a rare potion, but basically it also grows from common to legendary. And in weapon, we have 74, 87, and 98. So I would say yes, within each item type, power grows with the level of rarity. So what are these three fields in the context of my grouping? Well, item type is grouping field, and rarity is also a grouping field. And the average power within each group is an aggregate field, right? So I am now using two grouping fields to subdivide my data, and then I'm computing this aggregation within those groups. So let us now figure out how to write this in SQL. It's actually quite similar to what we've seen before. We have to take our data from the items table, and then we want to group by, and here I have to list my grouping fields, okay? So as I've said, I have two grouping fields. They are item type and rarity. So this defines my groups. And then in the select part, I will want to see my grouping fields. And then within each group, I will want to see the average of power, I believe we used. Yes, so I will get the average of power. And here are our results, just like in the sheets. Now, as a tiny detail, you may notice that power here is colored in blue. And the reason for this is that power is actually a BigQuery function. So if you do power of 2, 3, you should get 8 because it calculates the 2 to the power of 3. So it can be confusing when power is the name of a column because BigQuery might think it's a function, but there's an easy way to remedy this. You can just use backticks, and that's your way of telling BigQuery, hey, don't get confused. This is not the name of a function. This is actually the name of a column. And as you can see, it also works and it doesn't create issues. And just like before, we could add as many aggregations as we wanted. And for example, we could take the sum of power, also on other fields, not just on power. And everything would be computed within the groups defined by the two grouping fields that I have chosen, as expected. Now, let us see where group by fits in the logical order of SQL operations. So, as you know, a SQL query starts with from and join. This is where we source the data. This is where we take the data that we need. And as we learned in the join section, we could either just specify a single table in the from clause, or we could specify a join of 2 or more tables. Either way, the result is the same. We have assembled the table where our data lives, and we're going to run our pipeline on that data. We're going to run all the next operations on that data. Next, the where clause comes into play, which we can use in order to filter out rows that we don't need. And then finally, our group by executes. So the group by is going to work on the data that we have sourced, minus the rows that we have excluded. And then the group by is going to fundamentally alter the structure of our table. Because as you have seen in our examples, the group by basically compresses down our values or squishes them, as I wrote here, because in the grouping field, you will get a single row for each distinct value. And then in the aggregate field, you will get an aggregate value within each class. Okay, so if I use a group by, it's going to alter the structure of my table. After doing the group by, I can compute my aggregations like you've seen in our examples. So I can compute minimum, maximum, average, sum, count, and all of that. And of course, I need to do this after I have applied my grouping. And after that, after I've computed my aggregations, I can select them, right? So I can choose which columns to see, and this will include the grouping fields and the aggregated fields. We shall see this more in detail in a second. And then finally, there's all the other operations that we have seen in this course. And this is where group by and aggregations fit in our order of SQL operations. Now, I want to show you an error that's extremely common when starting to work with group by. And if you understand this error, I promise you, you will avoid a lot of headaches when solving SQL problems. So I have my items table here again, and you can see the preview on the right. And I have a simple SQL query. Okay, so take the items table, group by item type, and then show me the item type and the average level of power within that item type. So far, so good. But what if I wanted to see what I'm showing you here in the comments? What if I wanted to see each specific item, the name of that item, the type of that item, and then the average power by the type of that item, right? So let's look at the first item, chainmail armor. This is an armor type of item, and we know that the average power for armors is 69.5. So I would like to see this row. And then let's take elven bow. Now, elven bow is a weapon. As you can see here, the average power for weapons is 85.58. And so I would like to see that. Now, stop for a second and think, how might I achieve this? How might I modify my SQL query to achieve this? Oh, and there is an error in the column name over here because I actually wanted to say name. But let's see how to do it in the SQL query. So you might be tempted to simply go to your query and add the name field in order to reproduce what you see here. And if I do this and I run it, you will see that I get an error. Select expression references column name, which is neither grouped nor aggregated. Understanding this error is what I want to achieve now, because it's very important. So can you try to figure out on your own why this query is failing and what exactly this error message means? So I'm going to go back to my spreadsheet and get a copy of my items table. And as you can see, I have copied the query that doesn't work over here. So let us now go ahead and reproduce this query. So I have to take the items table, here it is, and then I have to group by item type. And as you can see, I've already sorted by item type to facilitate our work. And then for each item, we want to select the item type, so that would be armor, and we want to select the average power. So to find that, I can run a spreadsheet function like this. It's called average, and get the power over here. And then I am asked to get the name. So if I take the name for armor and put it here, this is what I have to add. And here you can already see the problem that we are facing. For this particular class, armor, there is a mismatch in the number of rows that each column is providing. Because as an effect of group by item type, now there is only one row in which item type is armor. And as an effect of applying average to power within the armor group, now there is only one row of power corresponding to the armor group. But then when it comes to name, it's neither present in a group by, nor is it present in an aggregate function. And that means that in the case of name, we still have 4 values. 4 values instead of 1. And this mismatch is an issue. SQL cannot accept it because SQL doesn't know how to combine columns which have different numbers of rows. In a way, it's like SQL is telling us, look, you've told me to group the data by item type, and I did. So I found all the rows that correspond to armor. And then you told me to take the average of the power level for those rows, and I did. But then you asked me for name. Now, the item type armor has 4 names in it. What am I supposed to do with them? How am I supposed to combine them? How am I supposed to squish them into a single value? You haven't explained how to do that, so I cannot do it. And this takes us to a fundamental rule of SQL, something I like to call the law of grouping. And the law of grouping is actually quite simple, but essential. It tells you what type of columns you can select after you've run a group by. And there are basically 2 types of columns that you can select after running a group by. One is grouping fields. So those are the columns that appear after the group by clause. Those are the columns you are using to group the data. And 2, aggregations of other fields. Okay, so those are fields that go inside a max function, a min function, a sum function, a count function, and so on. Now, those are the only 2 types of columns that you can select. If you try to select any other column, you will get an error. And the reason you will get an error is illustrated here. After a group by, each value in the grouping fields is repeated exactly once, and then for that value, the aggregation makes sure that there's only one corresponding value in the aggregated field. In this case, there's only one average power number within each item type. However, any other field, if it's not a grouping field and you haven't run an aggregation on it, you're going to get all of its values, and then there's gonna be a mismatch. So the law of grouping is made to prevent this issue. Now, if we go back to our SQL, hopefully you understand now better why this error is happening. And in fact, this error message makes a lot more sense after you've heard about the law of grouping. You are referencing a column, name, which is neither grouped nor aggregated. So how could we change this code so that we can include the column name without triggering an error? Well, we have 2 options. Either we turn it into a grouping field or we turn it into an aggregation. So let's try turning it into an aggregation. Let's say, for example, that I said min of name. What do you expect would happen in that case? So if I run this, you will see that I have my grouping by item type. I have the average power within each item type. And then I have one name. And so when you run min on a sequence of text values, what it does is that it gives you the first value in alphabetical order. So we are in fact seeing the first name in alphabetical order within each item type. So we've overcome the error, but this field is actually not very useful. We don't really care to see what's the first name in alphabetical order within each type. But at least our aggregation is making sure that there's only one value of name for each item type, and so the golden rule of grouping is respected and we don't get that error anymore. The second alternative is to take name and add it as a grouping field, which simply means putting it after item type in here. Now, what do you expect to happen if I run this query? So these results, as they show here, are a bit misleading because there's actually the name column is hidden. So I will also add it here. And as you can see, I can now refer the name column in select without an aggregation. Why? Because it is a grouping field, okay? And what do we see here in the results? Well, we've seen what happens when you group by multiple columns, that the unique combinations of these columns end up subdividing the data. So in fact, our values for average power are not divided by item type anymore. We don't have the average power for armor, potion, and weapon anymore. We have the average power for an item that's type armor, and it's called chainmail armor. And that is in fact, there's only one row that does that and has power 70. Likewise, we have the average power for any item called Cloak of Invisibility, which is of item type armor. And again, there's only one example of that. So we've overcome our error by adding name as a grouping field, but we have lost the original group division by item type, and we have subdivided the data to the point that it doesn't make sense anymore. So, as you surely have noticed by now, we made the error disappear by including name, but we haven't actually achieved our original objective, which was to show the name of each item, the item type, and then the average power within that item type. Well, to be honest, my original objective was to teach you to spot this error and understand the law of grouping, but now you might rightfully ask, how do I actually achieve this? And the answer, unfortunately, is that you cannot achieve this with group by, not in a direct, simple way. And this is a limitation of group by, which is a very powerful feature, but it doesn't satisfy all the requirements of aggregating data. The good news, however, is that this can be easily achieved with another feature called window functions. Now, window functions are the object of another section of this course, so I'm not going to go into depth now, but I will write the window function for you just to demonstrate that it can be done easily with that feature. So I'm going to go down here and write a new query. I'm going to take the items table and I'm going to select the name and the item type, and then I'm going to get the average of power, and again I'm going to use backticks so BigQuery doesn't get confused with the function that has the same name, and then I'm going to say take the average of power over partition by item type. So this is like saying average of power based on this item type. And I will call this average power by type. And if I select this and run the query, you will see that I get what I need. I have a chainmail armor, it's armor, and the average power for an armor is 69.5. So this is how we can achieve the original objective. Unfortunately, not with grouping, but with window functions. Now, I want to show you how you can filter on aggregated values after a group by. So what I have here is a basic group by query. Go to the fantasy characters table, group it by class, and then show me the class, and within each class, the average of the experience for all the characters in that class. And you can see the results here. Now, what if I wanted to only keep those classes where the average experience is at least 7,000? How could I go and do that? One instinct you might have is to add a where filter, right? For example, I could say where average experience is greater than or equal to 7,000. And if I run this, I get an error. Unrecognized name, average experience. The where filter doesn't work here. Maybe it's a labeling problem? What if I actually add the logic instead of the label? So what if I say where average of experience is bigger or equal to 7,000? Well, an aggregate function is actually not allowed in the where clause. So this also doesn't work. What's happening here? Now, if we look at the order of SQL operations, we can see that the where clause runs right after sourcing the data. And according to our rules over here, an operation can only use data produced before it and doesn't know about data produced after it. So the where operation cannot have any way of knowing about aggregations which are computed later after it runs and after running the group by. And this is why it is not allowed to use aggregations inside the where filter. Luckily, SQL provides us with a having operation which works just like the where filter, except it works on aggregations. And it works on aggregations because it happens after the group by and after the aggregations. So to summarize, you can source the table and then drop rows before grouping. This is what the where filter is for. And then you can do your grouping and compute your aggregations. And after that, you have another chance to drop rows based on a filter that runs on your aggregations. So let us see how that works in practice. Now, instead of saying where average experience, actually, let me just show you what we had before. This is our actual result, and we want to keep only those rows where average experience is at least 7,000. So after group by, I will write having, and then I will say average experience greater than or equal to 7,000. Let me remove this part here, run the query, and you can see that we get what we need. And you might be thinking, well, why do I have to write down the function again? Can't I just use the label that I've assigned? Well, let's try it and see if it still works. And the answer is that yes, this works in BigQuery. However, you should be aware that BigQuery is an especially user-friendly and fun to use product. In many databases, however, this is actually not allowed, in the sense that the database will not be kind enough to recognize your label in the having operation. Instead, you will have to actually repeat the logic as I am doing now. And this is why I write it like this, because I want you to be aware of this limitation. Another thing that you might not realize immediately is that you can also filter by aggregated columns which you are not selecting. So let's say that I wanted to group by class, and get the average experience for each class, but only keep classes with a high enough average level. I am perfectly able to do that. I just have to write having average level greater than or equal to 20. And after I run this, you will see that instead of 4 values, I actually get 3 values. So I've lost 1 value. And average level is not shown in the results, but I can of course show it. And you will realize that out of the values that have stayed, they all respect this condition. They all have at least 20 of average level. So in having, you are free to write filters on aggregated values regardless of the columns that you are selecting. So to summarize once more, you get the data that you need, you drop rows that are not needed, you can then group by if you want, subdivide the data, and then compute aggregations within those groups. If you've done that, you have the option to now filter on the result of those aggregations. And then finally, you can pick which columns you want to see and then apply all the other operations that we have seen in the course. We are now ready to learn about window function, a very powerful tool in SQL. Now, window functions allow us to do computations and aggregations on multiple rows. In that sense, they are similar to what we have seen with aggregations and group by. The fundamental difference between grouping and window function is that grouping is fundamentally altering the structure of the table, right? Because if I go here and I take this items table and I group by item type, right now I'm looking at about 20 rows, right? But if I were to group, the resulting table would have 3 rows only, because there are only 3 types of items. So that would significantly compress the structure of my table. And in fact, we have seen with the basic law of grouping that after you apply a group by, you have to work around this fundamental alteration in the structure of a table, right? Because here you can see that the items table has 20 rows. But how many rows do you expect it to have after you group by item type? I would expect it to have 3 rows because there's only 3 types of items. And so my table is being compressed, my table is changing its structure, and the basic law of grouping teaches you how to work with that. It tells you that if you want to group by item type, you can't just select power as is, because your table will have 3 rows, but you have 20 values of power. So you have to instead select an aggregation on power so that you can compress those values to a single value for each item type. And if you want to select name, you also cannot select name as is. You also have to apply some sort of aggregation. For example, you could put the names into a list, an array, or so on. But window functions are different. Window functions allow us to do aggregations, allow us to work on multiple values, without, however, altering the structure of the table, without changing the number of rows of the table. So let us see how this works in practice. Now, imagine that I wanted to get the sum of all the power values for my items. So what is the total power for all of my items? So you should already be aware of how to do this in SQL to just get that sum, right? I can do this by getting my fantasy items table and then selecting the sum over the power. So if I take this query and paste it in BigQuery, I will get exactly that. And this now is a typical aggregation, right? The sum aggregation has taken 20 different values of power and it has compressed them down to one value. And it has done the same to my table. It's taken 20 different rows to my table and it has squished them, it has compressed them down to one row. And this is how aggregations work, as we've seen in the course. But what if I wanted to show the total power without altering the structure of the table? What if I wanted to show the total power on every row? In other words, I can take the sum of all the values of power, and this is the same number that we've seen in BigQuery, and I can paste it over here, and hopefully I can now expand it. And this is exactly what I meant. What if I can take that number and put it on every row? And why would I want to do this? Well, there's several things that I can do with this setup, right? For example, I could go here for Phoenix Feather, which is power 100, and I could say, take this 100 and divide it by the total power in this row, and then turn this into a percentage. And now I have this 6.5 approximately percentage. And thanks to this, I can say, hey, look, the Phoenix Feather covers about 6 or 7% of all the power that is in my items, of all the power that is in my game. And that might be useful information. A more mundane concern could be that this is your budget, so this is the stuff that you're spending on, and instead of power you have the price of everything, and then you get the total sum, right, which is maybe what you spent in a month, and then you want to know, going at the movies, what percent of your budget it covered, and so on. Now I will delete this value because we're not going to use it, and let us see what we need to write to obtain this result in SQL. So once again, we go to the fantasy items table, and I'm gonna move it a bit down, and then we select the sum power, just like before, except that now I'm going to add this over, open round bracket, and close round bracket. And this is enough to obtain this result. Well, to be precise, when I write this in BigQuery, I will want to see a few columns as well. So I will want to see the name, item type, and power. And here I will need a comma at the end, as well as the sum power over. And I will also want to give a label to this, just like I have in the spreadsheet. Now this is the query that will reproduce what you see here in the spreadsheet. So how this works is that the over keyword is signaling to SQL that you want to use a window function. And this means that you will get an aggregation, you will do a calculation, but you're not going to alter the structure of the table. You are simply going to take the value and put it in each row. This is what the over keyword signals to SQL. Now, because this is a window function, we also need to define a window. What exactly is a window? A window is the part of the table that each row is able to see. Now, we will understand what this means much more in detail by the end of this lecture, so don't worry about it. But for now, I want to show you that this is the place where we usually specify the window inside these brackets after the over, but we have nothing here. And what this means is that our window for each row is the entire table. So that's pretty simple, right? Each row sees the entire table. So to understand how the window function is working, we always have to think row by row, because the results can always be different on different rows. So let us go row by row and figure out how this window function is working. So now we have the first row, and what is the window in this case? Meaning, what part of the table does this row see? Well, the answer is that this row sees all of the table. Given that it sees all of the table, it has to do the sum of power. And so it will take this thing, compute a sum over it, put it in the cell. Now that was the first row. Moving on to the second row. Now, what's the window here? What part of the table does this row see? Once again, it sees all of the table. Given that it sees all of the table, it takes power, computes sum over it, gets the result, and puts it in the cell. Now, I hope you can see that the result has to be identical in every cell, in every row, in other words, because every row sees the same thing and every row computes the same thing, and this is why every row in here gets the same value. And this is probably the simplest possible use of a window function. So let us now take this code and bring it to BigQuery and make sure that it runs as intended. And like I said in the lecture on grouping, you will see that power is blue because BigQuery is getting confused with its functions. So always best practice to put it into backticks to be very explicit that you are referring to a column. But basically what you see here is exactly what we have in our sheet. And now, of course, we have this new field which shows me the total of power on every row. And like I said, we can use this for several purposes. For example, I can decide to show for each item what percentage of total power it covers, right? That's what I did before in the sheet. So to do this, I can take the power and I can divide by this window expression, which will give me the total power. Not sure what happened there, but let me copy paste here. And I can call this percent total power. Now this is actually just a division, so if I want to see the percentage, I will have to also multiply by 100, but we know how to do this. And once I look at this, we can see that when we have power 100, we have almost 6.5% of the total power. So this is the same thing that we did before. And this goes to show that you can use these fields for your calculations. And like I said, if this was your budget, you could use this to calculate what percentage of your total budget is covered by each item. It's a pretty handy thing to know. Now, why do I have to take this to repeat all of this logic over here? Why can't I just say, give me power divided by some power? Well, as you know from other parts of the course, the select part is not aware of these aliases, it's not aware of these labels that we are providing. So when I try to do this, it won't recognize the label. So unfortunately, if I want to show both, I have to repeat the logic. And of course, I'm not limited to just taking the sum, right? What I have here is an aggregation function, just like the ones we've seen with simple aggregations and grouping and aggregations. So instead of sum, I could use something like average, using the backticks, over, right? I need to remember to add the over, otherwise it won't work because it won't know it's a window function. And I can give it a label. And now for each row, I will see the same value, which is the average of power over the whole dataset. And you can basically use any aggregation function that you need. It will work all the same. Few more backticks to put in here just to be precise. But the result is what we expect. Now let us proceed with our explorations. So I would like now to see the total power for each row, but now I'm not interested in the total power of the dataset. I'm interested in the total power by item type. Okay, so if my item is an armor, I want to see the total power of all armors. If my item is a potion, I want to see the total power of all potions, and so on. Because I want to compare items within their category, I don't want to compare every item with every item. So how can I achieve this in the spreadsheet? Well, let us start with the first row. So I need to check what item type I have. And conveniently, I've sorted this so we can be quicker. Now we have an armor. So I want to see the total power for armor. So what I can do is to get the sum function and be careful to select only rows where the item type is armor. And this is what I get. And then the next step would be to simply copy this value and then fill in all of the rows which are armor, because for all of the rows, but again, you have to be careful because the spreadsheet wants to complete the pattern, but what I want is the exact same number. And then all of the rows that have item type armor will have this value because I'm looking within the item type. Now I will do it for potion. So here I need to get the sum of power for all items that are potions, 239, and then make sure to copy the exact same value and to extend it to all potions. And next we have weapons. So sum of all power by weapon, which is here, and copy it and copy it. And then let's see if it tries to complete the pattern. It does. So I'm just going to go ahead and paste it. And now make this a bit nicer. And now I have what I wanted to get. Each row is showing the total power within the items that are the same as the one that we see in the row. Now, how can I write this in SQL? So let me go ahead and write it here. Now, two parts of this query will be the same because we want to get the items table and see these columns, but we need to change how we write the window function. So once again, I want to get the sum of power, and I will need now to define a specific window. Now remember, the window defines what each row sees. So what do I want each row to see when it takes the sum of power? For example, what do I want the first row to see when it takes the sum of power? I want it to see only rows which have the item type armor. Or in other words, all the rows with the same item type. And I can achieve this in the window function by writing partition by item type, by adding a partition. Defining the window as a partition by item type means that each row will look at its item type and then will partition the table so that it only sees rows which have the same item type. So this row over here will see only these 4 rows, and then you will take the sum of power and then you will put it in the cell. And for this, the second, third, and fourth row, the result will be the same because they will each see this part of the table. When we come to potion, so this row over here will say, hey, what is my item type? It's potion. Okay, then now I will only look at rows that have item type potion, and so this will be the window for these 4 rows. And then in those rows, I'm going to take power and I'm going to sum it. And finally, when we come to these rows over here, so starting with this row, it will look at its item type and say, okay, I have item type weapon. Let me look at all the rows that share the same item type. And so its window will look like this. So let me color it properly, its window will look like this, and then it will take the sum of these values of power that fit in the window and put it in the cell. Second cell sees the same window, sums over these values of power, puts it in the cell. And this is how we get the required result. This is how we use partitioning in window functions. So let's go now to BigQuery and make sure that this actually works. And when I run this, I didn't put a label, but you can see that I'm basically getting the same result. When I have a weapon, I see a certain value. When I have a potion, I see another one. And when I have an armor, I see the third value. So now for each item, I am seeing the total power, not over the whole table, but within the item type. Now, next task, find the cumulative sum of power, which is this column over here. What is a cumulative sum? It's the sum of the powers of this item plus all of the items that are less powerful. So to do this in the spreadsheet, I will first want to reorder my data because I want to see it simply in order of power. So I will actually take this whole range and I will go to data, sort range, advanced options, and I will say that the data has a header row so that I can see the names of the columns. And then I will order by power, ascending. So as you can see, my records have now been sorted in direction of ascending power. Now, how do I compute the cumulative sum of power? In the first row, all we have is 30, so the sum will be 30. In the second row, I have 40 in this row plus 30 before, so I will have 70. When it comes here, I have 50 in this row, and then the sum up to now was actually 70, which I can see by looking at these two cells, or I can see more simply by looking at the last cell. So 50 plus 70 will be 120. And proceeding like this, I could compute the cumulative power over the whole column. Now, for your reference, I have figured out the correct Google Sheets formula that will allow you to compute the cumulative sum of power for our example. And I went ahead and computed it so that we have it for all our data. Now, this is the formula right here, and I'm not going to go in depth into it because this is not a course on spreadsheets, but I will show you the formula just in case you're curious. So the SUMIF function will take the sum over a range but it will only consider values that satisfy a certain logical condition. So the first argument is the range that we want to sum over, and this is the power. And the criterion, so what needs to be true for a value to be considered, is that this value is lesser than or equal to the level of power in this row. So what this formula is saying is take the level of power in this row and then take all the values of power which are lesser or equal and then sum them up. This is exactly what our window function does. And so our formula reproduces this. Now, if you go and look what's the way to do a cumulative sum in Google Sheets, or what's the way to do a running total, there are other solutions, but they do come with some pitfalls. They do come with some corner cases. So this is a formula that's actually reproducing the behavior of SQL. Now let us go back to actually SQL and see how we would write this. So I'm going to take the fantasy items table and I'm still going to select the columns. And now I have to write my window function. Now the aggregation is just the same. So take the sum of power, and now I have to define my window. Now my window is not defined now by a partition, but it is defined by an ordering. Order by power. And when I say order by power in a window function, what's implicit in this is the keyword ask for ascending. So this means that the window will order power from the smallest to the biggest. And I can choose to write this keyword or not, because just like in order by in SQL, when you don't specify it, the default value is ascending from smallest to biggest. So how does this window work? Let's start with the first row, and let's say we need to fill in this value. So I'm going to look at my power level. It is 30. And then the window says that I can only see rows where the power level is equal or smaller. And what are the rows where the power level is equal or smaller to 30? They're these rows over here. So effectively, this is the only part of the table that this window sees on the first row. And then take the sum over power. So sum over 30 is 30. Move on to the second row. The power level is 40. The window says I only see rows where the power level is smaller or equal. And this includes these two rows over here. Now take the sum of power over here, you get 70, put it in the cell. Third row, I have power level 50. I'm only seeing these rows. So take the sum of power over this, it's 120, put it in the cell. And I can continue like this until I get to the highest value in my dataset. It's 100. Never mind that it's not the last row, because both of the last two rows, they have the highest value. And when you look at this, when you come to this row and you look at 100 and you say, what's the window? What rows can I see? I can see all rows where power is 100 or less. And that basically includes all of the table, right? It includes all of the table. So when you take the sum of power, you will get the total sum. And in fact, you can see that in this case, the cumulative power is equal to the total power that we computed before, just as we would expect. So this is easy to see here because we have ordered our data conveniently, but it works in any case. And so what the order by does in a window function is that it makes sure that each row only sees rows which come before it, given your ordering. So if I want to order from the smallest power to the biggest power, each row will only see rows that come before it in this ordering, so they have the same level of power or lower, but they don't have a higher level of power. So let us now take it to BigQuery and make sure it works as intended. And I will add an ordering by power. And here I will see the same thing that I've shown you in the spreadsheet. I notice now that some numbers are different, that these two items have 90 instead of 100, but never mind that, the logic is the same and the numbers make sense. Now I'm also able to change the direction of the ordering, right? So let's say that I take this field and copy it just the same, except that instead of ordering by power ascending, I order by power descending. So what do you expect to see in this case? Let's take a look. Now what I see here is that each item is going to look at its level of power, and then it's only going to consider items that are just as powerful or more powerful, right? So it's the exact same logic, but it's reversed. So when you look at the weakest item, potion, it has 30, and so it is looking at all the items because there's no weaker item. And so it finds the total level of power in our dataset. But if you go to the strongest item, like Excalibur, it has a power level of 100, and there's only 2 items in the whole dataset that have this power level, itself and the Phoenix feather. So if you sum the power over these, you get 200. So you can see it's the exact same logic, but now each row only sees items that have the same level of power or higher. So when you order inside a window function, you can decide the direction of this ordering by using descending or ascending. Or if you are a lazy programmer, you can omit the ascending keyword and it will work just the same because that's the default. And finally, we want to compute the cumulative sum of power by type. And you might notice that it is in a way the combination of these two requirements. So let us see how to do that. Now, the first thing I want to do is to sort our data in order to help us. So I'm going to get this whole thing and I'm going to say sort range. I'm going to need the advanced options. I have a heading row. And so first of all, I want to order by type. And then within each type, I want to order by power. And this is our data now. Now, for each item, I want to show the cumulative sum of power, just like I did here, except that now I only want to do it within the same item type. So if we look at armor, it's already sorted, right? So I have power 40, and this is the smallest one, so I will just put 40 over here. Next, I have this item with power 70. It's still armor, has power 70, and so I'm going to look at these two values and sum them up. Now I have 78, so I will take this plus 78, which is the sum of these three values. And finally, I have 90, which is the sum of those values. And now I'm done with armor, right? I'm beginning with a new item type. So I have to start all over again. I'm looking at potions now. So we start with 30, that is the smallest value. Then we move to 50. So this is now seeing 30 and 50, which is 80. Add 60 to 80, that is 140. And finally, we want to add 99 plus 140, which is another way of saying that we want to add these values, all the values for potion. So this is what we want, cumulative sum of power within item type. So we do it within the item type, and then when we find a new type, we start over. So to calculate it for weapon, I could copy my function from here, paste it in weapon, and then I would need to modify it, right? I would need the range to only include weapon. So that's from C10. So go here, C10 is the first one. And the value that I want to look at here would have to be C10 as well, because I want to start by looking at the power level for the first weapon. And for some reason it's purple. However, it should be correct. It should always be the sum of the previous value. So we start with 65, then we have 65 plus 75, 66, 75, 65, and so on. So this is our result. It's cumulative power within the item type. And to write this in SQL, I will take my previous query over here. And now when we define the window, we can simply combine what we've done before. We can combine the partition by with the order by. And you need to write them in the following order. first the partition and then the order. So I will partition by item type, and I will order by power, ascending. And this will achieve the required result. So for each row in this field, the window will be defined as follows. First, partition by item type, right? So first of all, you can only see rows which have the same item type as you have. But then within this partition, you have to keep only rows where the power is equal or smaller than what you have. So in the case of the first item, you only get this row. Likewise, in the case of the first potion item, you only get this row. If you look at the second armor item, again, it partitions, right? So it looks at all the items which have armor, but then it has to discard those that have a bigger power than itself. So it will be looking at these two rows. And if, for example, we look at the last row over here, so this row will say, oh, okay, I'm a weapon, so I can only see those that are weapon. And then I can only see those that have a level of power that's equal or smaller than mine. And that checks out. Those are all the rows. And in fact, the sum over here is equal to the sum of power by type, which is what we would expect. So once again, let us verify that this works in BigQuery. And I will actually want to order by item type and power, just so I have the same ordering as in my sheet. And I should be able to see that within armor, you have this like growing cumulative sum. And then once the item changes, it starts all over, right? It starts again at the first value, it grows, it accumulates, and then we're done with potions, and then we have weapons, and then again it starts, and then it grows, and it goes all the way to include the total sum of all powers in the weapon item type. So here's a summary of all the variants of windows that we've seen. We have seen 4 variants. Now, in all of those, for clarity, we've kept the aggregation identical, right? We're doing sum over the power field. But of course, you know that you can use any aggregate function here on any column which is compatible with that aggregate function. And then we have defined 4 different windows. The first one is the simplest one. There's actually nothing in the definition. We just say over. And this means that it will just look at all the table. So every row will see the whole table, and so every row will show you the total of power for the whole table. Simple as that. The second window is introducing a partition by item type. And what this means in practice is that each row will look at its own item type and then only consider rows which share the same exact item type. And so within those rows, it will calculate the sum of power. Third window, we have an ordering field. So what this means is that each row is going to look at its level of power because we are ordering by power. And then it's going to only see rows where the power level is equal or smaller. And the reason why we're looking in this direction is that when we order by power is implicitly understood that we want to order by power ascending. If instead we ordered by power descending, it would be the same, just in the opposite direction. Each row would look at its level of power and then only consider rows where power is equal or bigger. And then finally, we have a combination of these two, right? We have a window where we use both a partition and an order. And so what this means is that each row is going to look at its item type and discard all of the rows which don't have the same item type. But then within the rows that remain, it's going to apply that ordering. It's going to only consider rows which have the same level of power or lesser. So it's simply a combination of these two conditions. And this is the gist of how window functions work. First thing to remember, window functions provide aggregation, but they don't change the structure of the table. They just insert a specific value at each row, but after applying a window function, the number of rows in your table is the same. Second thing to remember is that in the window definition, you get to define what each row is able to see when computing the aggregation. So when you are thinking about window function, you should be asking yourself, what part of the table does each row see? What's the perspective that each row has? And there are two dimensions on which you can work in order to define these windows. One is the partition dimension and the other is the ordering dimension. The partition dimension cuts up the table based on the value of a column. So you will only keep rows that have the same value. The order dimension cuts up the table based on the ordering of a field. And then depending on ascending or descending, depending on the direction that you choose, you can look at rows that are after you in the ordering, or you can look at rows that are before you in the ordering. And you can pick either of these, right? Either partitioning or ordering, or you can combine them. And by using this, you can define all of the windows that you might need to get your data. Now, as a quick extension of this, I want to show you that you're not limited to defining windows on single fields, on single columns. You can list as many columns as you want. So in this example, I'm going to the fantasy characters table. I'm getting a few columns, and then I'm defining an aggregation on a window function. So I'm taking the level field and I'm summing it up, and then I'm partitioning by two fields actually, by guild and is alive. So what do you expect to happen if I do this? This is actually the exact same logic as grouping by multiple fields, which we've seen in the group by. Now the data is not going to be divided by guild and is not going to be divided by whether the character is alive or not, but by all the mutual combinations between these fields. Okay, so Mirkwood and true is one combination, and so the people in here are going to fit together, right? So in fact, we have two characters here, 22 and 26, and their sum is 48. So you can see here that they both get 48 for sum of level. And likewise, when you look at Shirefolk true, these three, they all end up in the same group. And so they all share the same sum of level, which is 35. But Shirefolk false, this is another group, and they're actually alone, right? It's 12, and then the sum is 12. So again, when you partition by multiple fields, the data is divided in groups that are obtained by all the combinations between the values that these fields can have. And if you experiment a bit by yourself, you should have an easier time to convince yourself of this. Likewise, the same idea applies to the order part of a window. We have until now, for simplicity, ordered by one field. To be honest, most times you will only need to order by one field, but sometimes you might want to order by different fields. So in this example, you can see that we are defining our ordering based on two fields, power and then weight. And then based on that ordering, we calculate the sum of power, and this is again a case of cumulative sum. However, now the ordering is different, and you will realize this if we go to the most powerful items in our data, these last two, which are both at 100. So if you remember, when we were ordering by power alone, these two fields had the same value in this window function, because when you order just by power, they are actually the same. They both have 100. But because now we're ordering by weight, and again, we're ordering by weight ascending, so from the smallest weight to the biggest weight, now the phoenix feather comes first, because although it has the same power as Excalibur, the phoenix feather is lighter. And because it comes first, it has a different value for this aggregation. And of course, we have the power to say ascending or descending on each of the fields by which we order. So if I wanted to reverse this, I could simply write descending after the weight, and be careful that in this case, descending is only referring to weight, it's not referring to power. So this is just as if I've wrote this, right? So this one can be omitted because it's ascending by default, but I would write both to be clear. And now if I run this, you will see that our result is reversed, right? Excalibur comes first because we have weight descending, so it's heavier. And then last we have the phoenix feather, which is lighter. And again, understanding this theoretically is one thing, but I do encourage you to experiment with this, with your data, with exercises, and then you will be able to internalize it. And now we are back to our schema for the logical order of SQL operations, and it is finally complete again because we've seen all of the components that we can use to assemble our SQL query. And now the question is, where do window functions fit into this? Well, as you can see, we have placed them right here. So what happens is that, again, you get your data, and then the where filter runs, dropping rows which you don't need. And then you have a choice whether to do a group by, right? Now, if you do a group by, you're going to change the structure of your table. It's not going to have the same number of rows. It's going to have a number of rows that depends of the unique values of your grouping field or the unique combinations of values of your fields if you have used more than one. If you group, you will probably want to compute some aggregations, and then you may want to filter on those aggregations, meaning dropping rows based on the values of those aggregations. And here is where window functions come into play. It is on this result that window functions work. So if you haven't done a group by, then window functions will work on your data after the where filter runs. If you have done a group by, window functions will work on the result of your aggregation. And then after applying the window function, you can select which columns you want to show, give them labels, and then all the other parts run, right? So you can choose to drop duplicates from your result, meaning duplicate rows which have the same value on every column. You can stack together different tables, right? You can put them on top of each other. And then finally, when you have your result, you can apply some ordering, and also you can cut the result. You can limit it so you only show a few rows. And this is where window functions fit into the big scheme of things. And there are some other implications of this ordering. One interesting one is that if you have computed aggregations, such as the sum of a value within a class, you can actually use those aggregations in the window function. So you can sort of do an aggregation of an aggregation. But this is, in my opinion, an advanced topic, and it doesn't fit into this fundamentals course. It may fit someday in a later, more advanced course. I want to show you another type of window functions which are very commonly used and very useful in SQL challenges and SQL interviews. And these are numbering functions. Numbering functions are functions that we use in order to number the rows in our data according to our needs. And there are several numbering functions, but the three most important ones are, without any doubt, row number, dense rank, and rank. So let's see how they work in practice. Now what I have here is a part of my inventory table. I'm basically showing you the item ID and the value of each number. And conveniently, I have ordered our rows by value ascending, okay? And now we're going to number our rows according to the value by using these window functions. Now, I've already written the SQL query that I want to reproduce. So I'm going to the fantasy inventory table, and then I'm selecting the item ID and the item value as you see here. And then I'm using three window functions. So the syntax is the same as what we've seen in the previous exercise, except that now I'm not using an aggregation function over a field like I did before when I was doing sum of power and so on, but I'm using another type of function. This is a numbering function, okay? So these functions over here, they don't actually take a parameter. As you can see that there's nothing between these round brackets because I don't need to provide it an argument or a parameter. All I need to do is to call the function. But what's really important here is to define the correct window. And as you can see in the three examples here, the windows are all the same. I am simply ordering my rows by value ascending, which means that when it's going to compute the window function, every row will look at its own value and then say, okay, I'm only going to see rows where the value is the same or smaller. I'm not going to be able to visualize rows where the value is bigger than mine. And this is what the window does. So the first row over here will only see value of 30. The second row will see these. The third row will see these, and so on up until the last row, which will see itself and all the other rows as well. Now let us start with row number. So row number is going to use this ordering over here in order to number my rows. And it's as simple as saying, putting 1 in the first row, 2 in the second one, 3, 4, and so on. So if I extend this pattern, I'm going to get a number for every row. And that's it. That's all that row number does. It assigns a unique integer number to every row based on the ordering that's defined by the window function. And you might think, oh, big deal. Why do I need this? Don't I already have like row numbers over here in the spreadsheet? Well, in SQL problems, you often need to order things based on different values, and row number allows you to do this. You can also have many different orderings coexisting in the same table based on different conditions, and that can come in handy, as you will discover if you do SQL problems. Now let's move on to ranking. So first of all, we have dense rank, okay? And ranking is another way of counting, but is slightly different. Sometimes you just want to count things, you know, sometimes like we did here in row number, like, I don't know, you are a dog sitter and you're given 20 dogs and you getting confused between all their names, and then you assign a unique number to every dog so that you can identify them. And you can sort them by, I don't know, by age or by how much you're getting paid to dog sit them. Sometimes, on the other hand, you want to rank things, like when choosing which product to buy or expressing the results of a race, right? And the difference between ranking and counting can be seen when you have the same value, right? So when you want to simply number, like we did here, when you want to simply assign a different number to each element, and two things have the same value, then you don't really care, right? You need to sort of arbitrarily decide that, okay, one of them will be number 2 and one of them will be number 3. But you cannot do the same for ranking. If two students in a classroom get the best score, you can't just randomly choose that one of them is number 1 and the other is number 2. They have to both be number 1, right? And if two people finish a race at the same time and it's the best time, you can't say that one won the race and the other didn't, that because one is number 1, the other is arbitrarily number 2. They both have to be number 1, right? They have to share that rank. And this is where ranking differs. So let's go in here and apply our rank. Now we are ordering by value ascending, which means that the smallest value will have rank number 1. And so 30 has rank number 1. Now we go to the second row. And again, remember, window functions, that you always have to think row by row. You have to think what each row sees and what each row decides. So again, the row is going to order by value. So it's only going to see these values over here, and it has to decide its rank. So this row says, oh, I'm not actually number 1 because there is a value which is smaller than me. So that means I have to be number 2. And then we get to the third row. And this row is seeing all the values that come before it, right? They're equal or smaller. And now it's saying, oh, I'm not number 1 because there's something smaller, but then the value 50, which this guy has, is rank 2, and I have the same value, number 50. We arrived in the same spot, so I must have the same rank. Okay, and this is the difference between row number and rank, that identical values get the same rank, but they don't get the same row number. And now we come to this row, which is 60. So it's going to look back and it's going to say, oh, from what I see, 30 is the smallest one, so it has a rank of 1. And then you have 50 and 50. They both share a rank of 2, but I am bigger, so I need a new rank. And so what am I going to pick now as a new rank? Well, I'm going to pick 3 because it's the next number in the sequence. Then the next one is going to pick 4. The next one is going to pick 5. And then we have 6. And then it proceeds in the following way. So I'll do it quickly now. So 7, 8, 9, 10, 11. And again, careful here, we're sharing the same value. So they are both 11. Next we can proceed to 12, 13. Again, the same value, right? So they have to share the 13th spot. 14, so 14 for 1700, and then 14 again, and then 15, and then 16. And this is what we expect to see when we compute the dense rank. And finally, we come to rank. Now, rank is very similar to dense rank, but there is one important difference. So let's do this again. Smallest value has rank number 1, like before. And then we have 50, which has rank number 2. And then 50 is once more sharing rank number 2. And now we move from 50 to 60, so we need a new rank. But instead of 3, we put 4 over here. Why do we put 4? Because the previous rank covered 2 rows, and it sort of ate the 3. It sort of expanded to ate the 3. So based on the rules of simply rank, we have to lose the 3 and put 4 over here. So this is just another way of managing ranking, and you will notice that it conveys another piece of information compared to dense rank, because not only I see that this row over here has a different rank than the previous row, but I can also see how many members were covered by the previous ranks. I can see that in the previous ranks, they must have involved 3 members because I am at 4 already. And this piece of information was not available for dense rank. So I will continue over here, and so I have a new value, which is rank 5, and then I have rank 6, rank 7, rank 8, rank 9, rank 10, rank 11. Now I have rank 12, and again I have to share the rank 12 because 2 identical values. But now, because 12 has eaten up 2 spots, I can't use the 13 anymore. The second 12 has like eaten the 13, and so I need to jump straight to 14. 15, 15 again, and now I have to jump to 17 because 15 had 2 spots. 17 again, and now I have to jump to 19, and then finally I have 20. So you can see that the final number is 20 for rank, just as with row number, because it's not only differentiating between ranks, but it's also counting for me how many elements have come before me, how many rows are contained in the previous ranks. I can tell that there's 19 rows in the previous ranks because of how rank works. Whereas with dense rank, we ended up using only 16, ended up being only up to 16. So we sort of lost information on how many records we have. And this might be one of the reasons why by default you have this method of ranking instead of this method of ranking, even though dense rank seems more intuitive when you are building the ranking yourself. So we can now take this query, and hopefully I've written it correctly, and go to BigQuery and try to run it. And as you can see, we have our items. They are sorted by value. And then we have our numbering functions. So row number should go from 1 to 20 without any surprises because it's just numbering the rows. Dense rank should have rank 1 for the first, and then these two should share the same rank because they both have 50, and then the next rank is 3. So just as I've shown you in the spreadsheet. Similarly here, you have 11, 11, and then 12. Rank instead starts off just the same. Smallest value has rank number 1, and the next 2 values have rank number 2. But then after using up 2 and 2, it's like you've used up the 3, so you jump straight to 4. And after doing 15 and 15, you jump straight to 17. After doing 17, 17, you jump straight to 19. And then the highest number here is 20, which tells you how many rows you're dealing with. Of course, what you see here are window functions. They work just the same as I've shown you. And so you could pick up rank and you could order by value descending, and then you will find the inverse of that rank in the sense that the highest value item will give you rank 1, and you will go from there. And the lowest value item will have sort of the biggest rank number. And rank is often used like this, you know, the thing that has the most of what we want, you know, the biggest salary, the biggest value, the most successful product. We rank it, we make it so that it's rank 1. It's like the first in our race. And then everyone else goes from there. And so we often have we order by something descending when we calculate the rank. And of course, because these numbering functions are window functions, they can also be combined with partition by if you want to cut the data into subgroups. So here's an example on the fantasy characters table. We are basically partitioning by class, meaning that each row only sees the other rows that share the same class. So archers only care about archers, warriors only care about warriors, and so forth. And then within the class, we are ordering by level descending. Okay, so the highest levels come first, and using these to rank the characters. Okay, so if I go here, then I can see that within the archers, the highest level archer has level 26, so they get the first rank. And then all the others is go down from there. And then we have our warriors. And the highest level warrior is 25, and they also get rank 1 because they are being ranked within warriors. So this is like when you have races and there are categories. This is like when you have a race and there are categories within the race. So there are like many people who arrive first because they arrive first in their category. It's not that everyone competes with everyone. And so on and so forth. You can see that each class of character has their own dedicated ranking. And you can check the BigQuery page on numbering function if you want to learn more about these functions. You can see here the ones we've talked about: rank, row number, and dense rank. There are a few more, but these are the ones that are most commonly used in SQL problems. And because I know that it can be a bit confusing to distinguish between row number, dense rank, and rank, here's a visualization that you might find useful. So let's say that we have a list of values, which are these ones, and we are ordering them in descending order. So you can see that there's quite some repetition in these values, and given this list of values, how would these different numbering functions work on them? Right, so here's row number. Row number is easy. It just assigns a unique number to each of them. So it doesn't matter that the values are sometimes the same. You sort of arbitrarily pick one to be 1, the other to be 2, and then you have 3, and then here you have 10, 10, 10, but it doesn't matter. You just want to order them, so you do 4, 5, 6, and then finally 7. Dense rank is actually cares about the values being the same. So 50 and 50, they both get 1. 40 gets 2. And then the 10s get 3. And then 5 gets 4. So easy. The rank just grows using all the integer numbers. Dense rank is also assigning rank 1 to 50 and 50. But it's also throwing away the 2 because there are 2 elements in here. Then the next one is getting rank 3 because the 2 has already been used. And then the next batch, 10, 10, 10, is getting rank 4, but it's also burning 5 and 6. And the next one then can only get rank 7. So these are the differences between row number, dense rank, and rank visualized. We have now reached the end of our journey through the SQL fundamentals. I hope you enjoyed it, and I hoped that you learned something new. You hopefully now have some understanding of the different components of SQL queries and the order in which they work and how they come together to allow us to do what we need with the data. Now, of course, learning the individual components and understanding how they work is only half the battle. The other half of the battle is, how do I put these pieces together? How do I use them to solve real problems? And in my opinion, the response to that is not more theory, but it's exercises. Go out there and do SQL challenges. Do SQL interviews, find exercises, or even better, find some data that you're interested in, upload it in BigQuery, and then try to analyze it with SQL. I should let you know that I have another playlist where I am solving 42 SQL exercises in PostgreSQL. And I think this can be really useful to get the other half of the course, which is doing exercises and knowing how to face real problems with SQL. And I really like this playlist because I'm using a free website, a website that doesn't require any sign up or any login. It just works. And you get a chance to go there and do all of these exercises that cover all the theory that we've seen in this course. And then after trying it yourself, you get to see me solving it and my thought process and my explanation. And I think it can be really useful if you want to deepen your SQL skills. But in terms of how do I put it all together, how do I combine all of this stuff, I do want to leave you with another resource that I have created, which is this table. And this table shows you the fundamental moves that you will need to do whenever you do any type of data analytics. And I believe that every sort of analytics that you might work on, no matter how simple or complicated, can ultimately be reduced to these few basic moves. And what are these moves? They should actually be quite familiar to you by now. So we have joining, and this is where we combine data from multiple tables based on some connections between columns. And in SQL, you can do that with the join. Then we have filtering. Filtering is when we pick certain rows and discard others. So, let's look only at customers that joined after 2022. Now, how do you do that in SQL? There are a few tools that you can use to do that. The most important one is the where filter. And the where filter comes in action right after you've loaded your data, and it decides which rows to keep, which rows to discard. Having does just the same, except that it works on aggregated fields. It works on fields that you've obtained after a group by. Qualify, we actually haven't seen it in this course because it's not a universal component of SQL. Certain systems have it, others don't. But qualify is basically also a filter, and it works on the result of window functions. And finally, you have distinct, which runs quite at the end of your query, and it's basically removing all duplicate rows. And then of course you have grouping and aggregation. And we've seen this in detail in the course. You subdivide the data on certain dimensions, and then you calculate aggregate values within those dimensions. Fundamental for analytics. How do we aggregate in SQL? We have the group by, we have the window functions, and for both of them we use aggregate functions such as sum, average, and so on. And then we have column transformations. So this is where you apply logic, arithmetic, to transform columns, combine column values, and take the data that you have in order to compute data that you need. And we do this where we write the select, right? We can write calculations that involve our columns. We have the case when, which allows us to have a sort of branching logic and decide what to do based on some conditions. And of course, we have a lot of functions that make our life easier by doing specific. Next, we have union. Union is pretty simple. Take tables that have the same columns and stack them together, meaning put their rows together and combine them. And finally, we have sorting, which can change how your data is sorted when you get the result of your analysis, and can be also used in window functions in order to number or rank our data. And these are really the fundamental elements of every analysis and every SQL problem that you will need to solve. So one way to face a problem, even if you are finding it difficult, is to come back to these fundamental components and try to think of how do you need to combine them in order to solve your problem. And how can you take your problem and break it down to simpler operations that involve these steps? Now, at the beginning of the course, I promised you that we would be solving a hard SQL challenge together at the end of the course. So here it is. Let us try now to solve this challenge, applying the concepts in this course. Now, as a quick disclaimer, I'm picking a hard challenge because it's sort of fun and it gives us a playground to showcase several concepts that we've seen in the course. And also because I would like to show you that even big, hard, scary challenges that are marked as hard and even have advanced in their name can be tackled by applying the basic concepts of SQL. However, I do not intend for you to jump into these hard challenges from the very start. It would be much better to start with basic exercises and do them step by step, and be sure that you are confident with the basic steps before you move on to more advanced steps. So if you have trouble approaching this problem or even understanding my solution, don't worry about it. Just go back to your exercises and start from the simple ones and then gradually build your way up. That being said, let's look at the challenge, Marketing Campaign Success Advanced on Strata Scratch. So first of all, we have one table that we will work on for this challenge, Marketing Campaign. So Marketing Campaign has a few columns and it actually looks like this. Okay, so there's a user ID, created at, product ID, quantity, price. Now, when I'm looking at the new table, the one question that I must ask to understand it is, what does each row represent? And just by looking at this table, I can have some hypotheses, but I'm actually not sure what each row represents. So I better go and read the text until I can get a sense of that. So let's scroll up and read. You have a table of in-app purchases by user. Okay, so this explains my table. What does each row represent? It represents an event that is a purchase. Okay, so it means that user ID 10 bought product ID 101 in a quantity of 3 at the price of 55, and created that tells me when this happened. So this happened 1st of January 2019. So great, now I understand my table and now I can see what the problem wants from me. Let's go on and read the question. So I have a table of in-app purchases by users. Users that make their first in-app purchase are placed in a marketing campaign where they see call to actions for more in-app purchases. Find the number of users that made additional purchases due to the success of the marketing campaign. The marketing campaign doesn't start until 1 day after the initial app purchase. So users that made one or multiple purchases on the first day do not count, nor do we count users that over time purchase only the products they purchased on the first day. All right, so that was a mouthful, okay? So this on the first run, it's actually a pretty complicated problem. So our next task now is to understand this text and to simplify it to the point that we can convert it into code, okay? And a good intermediate step before jumping into the code is to write some notes, and we can use the SQL commenting feature for that. So what I understand from this text is that users make purchases and we're interested in users that make additional purchases. We're interested in users who make additional purchases thanks to this marketing campaign. How do we define additional purchases? Additional purchase is defined as, and the fundamental sentence is this one: users that made one or multiple purchases on the first day do not count. So additional purchase happens after the first day, right? Nor do we count users that over time purchase only the products they purchased on the first day. So the other condition that we're interested in is that it involves a product that was not bought the first day. And finally, what we want is the number of users. So get the number of these users. That should be a good start for us to begin writing the code. So let us look at the marketing campaign table again, and I remind you that each row represents a purchase. So what do we need to find first in this table? So we want to compare purchases that happen on the first day with purchases that happen the following day. So we need a way to count days. And what do we mean first day and following days? Do we mean the first day that the shop was open? No, we actually mean the first day that the user ordered, right? Because the user signs up, does the first order, and then after that, the marketing campaign starts. So we're interested in numbering days for each user such that we know what purchases happened on the first day, what purchases happened on the second day, third day, and so on. And what can we use to run a numbering by user? We can use a window function with a numbering function, right? So I can go to my marketing campaign table and I can select the user ID and the date in which they bought something and the product ID for now. Now I said that I need a window function. So let me start and define the window. Now I want to count the days within each user. So I will actually need to partition by user ID so that each row only looks at the rows that correspond to that same user. And then there is an ordering, right? There is a sequence from the first day in which the user bought something to the second and the third and so on. So my window will also need an ordering. And what column in my table can provide an ordering? It is created at. And then what counting function do I need to use here? Well, the way to choose is to say, what happens when the same user made two different purchases on the same date? What do I want my function to output? Do I want it to output two different numbers as a simple count, or do I want it to output the same number? And the answer is that I want it to output the same number because all of the purchases that happened on day one need to be marked as day one, and all the purchases that happened on day two need to be marked as day two, and so on. And so the numbering function that allows us to achieve this is rank. And if you remember, ranking works just like ranking the winners of a race. Everyone who shares the same spot gets the same number, right? And this is what we want to achieve here. So let us see what this looks like now, and let us order by user ID and created at. Let us now see our purchases. Now, user 10 started buying stuff on this day. They bought one product and the rank is 1. Let us actually give a better name to this column so that it's not just rank. And we can call it user day. All right. So this user ID 10 had first user day on this date and they bought one product. Then at a later date, they had their second user day and they bought another product, and then they had a third. Now, user 14 started buying on this date. This was their first user day. They bought product 109. And then the same day, they bought product 107, and this is also marked as user day 1. So this is what we want. And then at a later day, they bought another product, and this is marked as user day 3. Remember, with rank, you can go from 1, 1 to 3 because the spot marked as 1 has eaten the spot marked as 2. That's not an issue in this problem, so we are happy with this. Now, if we go back to our notes, we see that we are interested in users who made additional purchases, and additional means that it happens after the first day. And how can we identify purchases that happened after the first day? Well, there's a simple solution for this. We can simply filter out rows that have a user day 1, right? All of the rows where the user day is 1 represent purchases that the user made on their first day. So we can discard these and keep only purchases that happened on the following days. Now, I don't really have a way to filter on this window function because, as you recall from the order of SQL operation, the window function happens here and the where filter happens before that. So the where filter cannot be aware of what happens in the window function, and the having also happens before it. So I need a different solution to filter on this field. What I need to do is to use a common table expression so that I can break this query in 2 steps. So I'm going to wrap this logic into a table called T1, or I can call it purchases for it to be more meaningful. And if I do select star from purchases, you will see that the result does not change. But what I can do now is to use the where filter and make sure that the user day is bigger than 1. And if I look here, you will see that I have all purchases which happened after the user's first day. But there is yet one last requirement that I have to deal with, which is that the purchase must happen after the first day and it must involve a product that the user didn't buy on the first day. So how can I comply with this requirement? Now, for all of the rows that represent a purchase, I need to drop the rows that involve a product ID that the user bought the first day. So if I find out that user 10 bought product 119 on day 1, this purchase does not count. I'm not interested in it. So how can I achieve this in code? I'm already getting all the purchases that didn't happen on day 1, and then I want another condition. So I will say and product ID not in, and here I will say products that this user bought on day 1, right? It makes sense. So this is all the filters I need to complete my problem. Show me all the purchases that happened not on day 1, and also make sure that the user didn't buy this product on day 1. So what I need to do is to add a subquery in here. And before I do that, let me give an alias to this table so that I don't get confused when I call it again in the subquery. So this first version of purchases that we're using, we could call it next days because we're only looking at purchases that happen after the first day. Whereas in the subquery, we want to look at purchases, but we're interested in the ones that actually happened on day 1. So we could call this first day. And we can use a where filter to say that first day user day needs to be equal to 1. So this is a way that we can use to look at the purchases that happened on the first day. Now, when we make this list, we need to make sure that we are looking at the same user, right? And to do that, we can say, and first day user ID needs to be the same as next day's user ID. And this ensures that we're looking at the same user and we're not getting confused between users. And finally, what do we need from the list of first day purchases? We need the list of products. So let me first see if the query runs. So it runs, there's no mistakes. And now let us review the logic of this query. We have purchases, which is basically a list of purchases with the added value that we know if it happened on day 1, on day 2, on day 3, and so on. And then we are getting all of these purchases, the ones that happened after day one. And we are also getting the list of products that this user bought on day one. And we are making sure to exclude those products from our final list. And this is a correlated subquery because it is a specific SQL query that provides different results for every row, that must run for every row. Because in the first row, we need to get the list of products that user ID 10 has bought on day one and make sure that this product is not in it. And then when we go to another row, such as this one, we need to get the list of all products that user 13 bought on day one and make sure that 118 is not in those products. So this is why it's a correlated subquery. And the final step in our problem is to get the number of these users. So instead of selecting star and getting all of the columns, I can say count distinct user ID. And if I run this, I get 23. Checking, and this is indeed the right solution. So this is one way to solve the problem, and hopefully it's not too confusing, but if it is, don't worry, it is after all an advanced problem. If you go to solution here, I do think, however, that my solution is a bit clearer than what StrataScratch provides. This is actually a bit of a weird solution, but that's ultimately up to you to decide. And I am grateful to StrataScratch for providing problems that I can solve for free, such as this one. Welcome to PostgreSQL Exercises, the website that we will use to exercise our SQL skills. Now, I am not the author of this website. I'm not the author of these exercises. The author is Alistair Owens, and he has generously created this website for anyone to use, and it's free. You don't even need to sign up. You can go here right away and start working on it. I believe it is a truly awesome website. In fact, the best at what it does, and I'm truly grateful to Alistair for making this available to all. The way the website works is pretty simple. You have a few categories of exercises here, and you can select a session, and once you select a session, you have a list of exercises. You can click on an exercise, and then here in the exercise view you have a question that you need to solve, and you see a representation of your three tables. We're going to go into this shortly, and then you see your expected results. And here in this text box over here, you can write your answer and then hit run to see if it's the correct one. The results will appear in this lower quadrant over here. And if you get stuck, you can ask for a hint. Here there are also a few keyboard shortcuts that you can use. And then after you submit your answer, or if you are completely stuck, you can go here and see the answers and discussion. And that's basically all there is to it. Now let's have a brief look at the data and see what that's about. And the data is the same for all exercises. And what we have here is the data about a newly opened country club. And we have three tables here. Members represents the members of the country club. So we have their surname and first name, their address, their telephone, and the date at which they joined, and so on. And then we have the bookings. So whenever a member makes a booking into a facility, that event is stored into this table. And then finally, we have a table of facilities where we have information about each facility. And in there we have some tennis courts, some badminton courts, massage rooms, and so on. Now, as you may know, this is a standard way of representing how data is stored in a SQL system. So you have the tables, and for each table you see the columns, and for each column you see the name and then the data type, right? So the data type is the type of data that is allowed into this column. And as you know, each column has a single data type, and you are not allowed to mix multiple data types within each column. So we have a few different data types here, and they have the Postgres name. So in Postgres, an integer is a whole number, like 1, 2, 3, and a numeric is actually a floating point number, such as 2.5 or 3.2. Character varying is the same as string. It represents a piece of text. And if you wonder about this number in round brackets, 200, it represents the maximum limit of characters that you can put into this piece of text. So you cannot have a surname that's bigger than 200 characters. And then you have a timestamp, which represents a specific point in time. And this is actually all the data types that we have here. And finally, you can see that the tables are connected. So in the bookings table, every entry, every row of this table represents an event where a certain facility ID was booked by a certain member ID at a certain time for a certain number of slots. And the facility ID is the same as the facility ID field in facilities, and the mem ID field is the same as the mem ID or member ID field in members. Therefore, the bookings table is connecting to both of these tables, and these logical connections will allow us to use joins in order to build queries that work on all of these three tables together, and we shall see in detail how that works. Finally, we have an interesting arrow over here which represents a self relation, meaning that the members table has a relation to itself. And if you look here, this is actually very similar to the example that I have shown in my mental models course. For each member, we can have a recommended by field, which is the ID of another member, the member who recommended them into the club. And this basically means that you can join the members table to itself in order to get at the same time information about a specific member and about the member who recommended them, and we shall see that in the exercises. And clearly the exercises run on PostgreSQL, and Postgres is one of the most popular open source SQL systems out there. PostgreSQL is a specific dialect of SQL which has some minor differences from other dialects such as MySQL or Google SQL that is used by BigQuery, but it is mostly the same as all the others. If you've learned SQL with another dialect, you're gonna be just fine. PostgreSQL does have a couple of quirks that you should be aware about, but I will address them specifically as we solve these exercises. Now, if you want to rock these exercises, I recommend keeping in mind the logical order of SQL operations. And this is a chart that I have introduced and explained extensively in my mental models course, where we actually start with this chart being mostly empty, and then we add one element at a time, making sure that we understand it in detail. So I won't go in depth on this chart now, but in short, this chart represents the logical order of SQL operations. These are all the components that we can assemble to build our SQL queries. They're like our Lego building blocks for SQL, and these components, when they're assembled, they run in a specific order, right? So the chart represents this order. It goes from top to bottom. So first you have from, then you have where, and then you have all the others. And there are two very important rules: that each operation can only use data produced above it, and an operation doesn't know anything about data produced below it. So if you can keep this in mind and keep this chart as a reference, It will greatly help you with the exercises. And as I solve the exercises, you will see that I put a lot of emphasis on coming back to this order and actually thinking in this order in order to write effective queries. Let us now jump in and get started with our basic exercises. So I will jump into the first exercise, which is retrieve everything from a table. So here I have my question, and how can I get all the information I need from the facilities table? And as you know, all my data is represented here, so I can check here to see where I can find the data that I need. Now, as I write my query, I aim to always start with the from part. Why start with the from part? First of all, it is the first component that runs in the logical order. So again, if I go back to my chart over here, I can see that the from component is the first. And that makes sense, right? Because before I do any work, I need to get my data. So I need to tell SQL where my data is. So in this case, the data is in the facilities table. Next, I need to retrieve all the information from this table. So that means I'm not going to drop any rows, and I'm going to select all the columns. And so I can simply write select star. And if I hit run, I get the result that I need. Here in this quadrant, I can see my result, and it fits the expected results. Now the star is a shortcut for saying, give me all of the columns of this table. So I could have listed each column in turn, but instead I took a shortcut and used a star. Retrieve specific columns from a table. I want to print a list of all the facilities and their cost to members. So as always, let's start with the from part. Where is the data that we need? It's in the facilities table again. And now the question is actually not super clear, but luckily I can check the expected results. So what I need are two columns from this table, which is name and member cost. So to get those two columns, I can write select name member cost. Hit run, and I get the result that I need. So if I write select star, I'm gonna get all the columns of the table, but if I write the name of specific columns separated by comma, I will get only those columns specifically. Control which rows are retrieved. We need a list of facilities that charge a fee to members. So we know that we're going to work with the facilities table, and now we need to keep certain rows and drop others. We need to keep only the rows that charge a fee to members. So what component can we use in order to do this? If I go back to my components chart, I can see that right after from, we have the where component. And the where component is used to drop rows that we don't need, right? So after getting the facilities table, I can say where member cost is bigger than 0, meaning that they charge a fee to members. And finally, I can get all of the columns from this. Control which rows are retrieved, part 2. So like before, we want a list of facilities that charge a fee to members, but our filtering condition is now a bit more complex because we need that fee to be less than 1/50th of the monthly maintenance cost. So I copied over the code from the last exercise. We're getting the data from our facilities list, and we're filtering for those where the member cost is bigger than 0. And now we need to add a new condition, which is that that fee, which is member cost, is less than 1/50th of the monthly maintenance cost. So I can take monthly maintenance over here and divide it by 50, and I have my condition. Now, when I have multiple logical conditions in the where, I need to link them with the logical operator so SQL can figure out how to combine them, because the final result of all my conditions needs to be a single value, which is either true or false, right? So let's see how to do this. In my mental models course, I introduced the Boolean operators and how they work. So you can go there for more detail, but can you figure out which logical operator do we need here to chain these two conditions? As suggested in the question, the operator that I need is AND, so I can put it here. And what AND does is that both of these conditions need to be true for the whole expression to evaluate to true and for the row to be kept. So only the rows where both of these conditions are true will be kept, and all other rows will be discarded. Now, to complete my exercise, I just need to select a few specific columns because we don't want to return all the columns here. And I think that I will cheat a bit by copying them from the expected results and putting them here. But normally you would look at the table schema and figure out which columns you need. And that completes our exercise. Basic string searches produce a list of all facilities with the word tennis in their name. So where is the data we need? It's in the CD facilities table. Next question, do I need all the rows from this table or do I need to filter out some rows? Well, I only want facilities with the word tennis in their name, so clearly I need a filter, therefore I need to use the where statement. How can I write the where statement? I need to check the name and I need to keep only facilities which have tennis in their name. So I can use the like statement here to say that the facility needs to have tennis in its name, but what these wildcards signify is that we don't care what precedes tennis and what follows tennis. It could be 0 or more characters before it and after it. We just care to check that they have tennis in their name. And finally, we need to select all the columns from these facilities. And that's our result. Beware, like I said before, of your use of the quotes. So what you have here is a string. It's a piece of text that allows you to do your match. Therefore, you need single quotes. If you, as it's likely to happen, used double quotes, you would get an error here, and the error tells you that the column tennis does not exist because double quotes are used to represent column names and not pieces of text. So be careful with that. Matching against multiple possible values. Can we get the details of facilities with ID 1 and ID 5? So where is my data is in the facilities table. And do I need all the rows from this table or only certain ones? I need only certain rows because I want those that have ID 1 and ID 5. So I need to use a where statement. Now, what are my conditions here? Their ID, actually facility ID equals 1 and facility ID equals 5. So I have my two logical conditions. Now, what operator do I need to use in order to chain them? I need to use the OR operator, right? Because only one of these needs to be true in order for the whole expression to evaluate to true. And in fact, only one of them can be true because it's impossible for the ID of a facility to be equal to 1 and 5 at the same time. Therefore, the AND operator would not work, and what we need is the OR operator. And finally, we need to get all the data, meaning all the columns about this facility, so I will use select star. The problem is now solved, but now let's imagine that tomorrow we need this query again and we need to include another ID, ID 10. So what we can do is put or facility ID equals 10. But this is becoming a bit unwieldy, right? Because imagine having a list of 10 IDs and then writing or every time, and it's not very scalable as an approach. So as an alternative, we can say facility ID in and then list the values like 1 and 5. So if I take this and make it into my condition, I will again get the same result. I will get the solution, but this is a more elegant approach, and it's also more scalable because it's much easier to come back and insert other IDs inside this list. So this is a preferred solution in this case. And logically, what in is doing is looking at the facility ID for each row and then checking whether that ID is included in this list. If it is, it returns true, therefore it keeps the row. If it's not, returns false, therefore it drops the row. And we shall see a bit later that the in notation is also powerful, because in this case we have a static list of IDs. We know that we want IDs 1 and 5, but in more advanced use cases, instead of a static list, we could provide another query, a SQL query or a subquery, that would dynamically retrieve a certain list, and then we could use that in our query. So we shall see that in later exercises. Classify results into buckets. Produce a list of facilities and label them cheap or expensive based on their monthly maintenance. So we want to get our facilities. Do we need a filter? Do we need to drop certain rows? No, we actually don't. We want to get all facilities and then we want to label them. And we need to select the name of the facility, and then here we need to provide the label. So what SQL statement can we use to provide a text label according to the value of a certain column? What we need here is a case statement which implements conditional logic, which implements a branching, right? It's similar to the if-else statements in other programming languages, because if the monthly maintenance cost is more than 100, then it's expensive. Otherwise, it's cheap. So this calls for a case statement. Now, I always start with case and end with end, and I always write these at the beginning so I don't forget them. And then for each condition, I write when and what is the condition that I'm interested in. Monthly maintenance being above 100. That's my first condition. What do I do in that case? I output a piece of text which says expensive. And remember, single quotes for text. Next, I could write the next condition explicitly, but actually, if it's not 100, then it's less than 100. So all I need here is an else. And in that case, I need to output a piece of text which says cheap. And finally, I have a new column and I can give it a label. I can call it cost. And I get my result. So whenever you need to put values into buckets or you need to label values according to certain rules, that's usually when you need a case statement. Working with dates. Let's get a list of members who joined after the start of September 2012. So looking at these tables, where is our data? It's in the members table. So I will start writing this. And now, do I need to filter this table? Yes, I only want to keep members that joined after a certain time. And now, how can I run the condition on this table? I can say where join date is bigger than 2012 September 01. So luckily in SQL and in Postgres, filtering on dates is quite intuitive. Even though here we have a timestamp that represents a specific moment in time up to the second, we can say bigger or equal, actually, because we also want to include those who joined on the first day. We can write bigger or equal and just specify the date, and SQL will fill in the rest of the remaining values and the filter will work. And next we want to get a few columns for these members. So I will copy paste here, select, and this solves our query. Removing duplicates and ordering results. We want an ordered list of the first 10 surnames in the members table, and the list must not contain duplicates. So let's start by getting our table, which is the members table. Now we want to see the surnames. So if I write this, I will see that there are surnames which are shared by members, so there are actually duplicates here. So what can we do in SQL in order to remove duplicates? We have seen in the mental models course that we have the distinct keyword, and the distinct is going to remove all duplicate rows based on the columns that we have selected. So if I run this again, I will not see any duplicates anymore. Now the list needs to be ordered alphabetically, as I see here in the expected results, and we can do that with the order by statement. And when you use order by on a piece of text, the default behavior is that the text is ordered alphabetically. And if I were to use descending, then it would be ordered in reverse alphabetical order. However, that's not what I need. I need it in alphabetical order. So now I see that they are ordered. And finally, I want the first 10 surnames. So how can I return the first 10 rows of my result? I can do that with the limit statement. So if I say limit 10, I will get the first 10 surnames. And since I have ordered alphabetically, I will get the first 10 surnames in alphabetical order. And this is my result. Now, going back to our map over here, we have the from, which gets a table. We have a where, which drops rows that we don't need from that table. And then all the way down here, we have the select, which gets the columns that we need. And then we have the distinct, right? And the distinct needs to know which columns we need because it drops duplicates based on these columns. So in this example over here, we're only taking a single column, surname, so the distinct is going to drop duplicate surnames. And then at the end of it all, when all the processing is done, we can order our results. And then finally, once our results are ordered, we can do a limit to limit the number of rows that we return. So I hope this makes sense. Combining results from multiple queries. So let's get a combined list of all surnames and all facility names. So where are the surnames? They're in CD members. And from CD members, I can select surname, right? And this will give me the list of all surnames. And where are the facility names? There are in CD facilities, and I could say select name from CD facilities, and I would get a list of all the facilities. Now we have two distinct queries, and they both produce a list or a column of text values, and we want to combine them. What does it mean? We want to stack them on top of each other, right? And how does that work? Well, if I just say run query like this, I will get an error because I have two distinct queries here and they're not connected in any way. But when I have two queries or more defining tables and I want to stack them on top of each other, I can use the union statement, right? And if I do union here, I will get what I want because all the surnames will be stacked vertically with all the names, and I will get a unique list containing both of these columns. Now, as I mentioned in the mental models course, typically when you have just union, it means union distinct, and actually other systems like BigQuery don't allow you to write just union, they want you to specify union distinct. And what this actually does is that after stacking together these two tables, it removes all duplicate rows. And the alternative to this is union all, which does not do this. It actually keeps all the rows. And as you know, we have some duplicate surnames and then we get them here and it doesn't fit with our result. But if you write just union, it will be union distinct and you won't have any duplicates. And if you look at our map for the logical order of SQL operations, we are getting the data from a certain table and filtering it and then doing all sorts of operations and on this data. And then we are selecting the columns that we need, and then we can remove the duplicates from this one table. And then what comes next is that we could combine this table with other tables, right? We can tell SQL that we want to stack this table on top of another table. So this is where the union comes into play. And only after we have combined all the tables, only after we have stacked them all up on top of each other, we can order the results and limit the results. Also remember, and I showed this in detail in the mental models course, when I combine two or more tables with a union, what I need is for them to have the exact same number of columns, and all of the columns need to have the same data type. So in this case, both tables have one column, and this column is a text, so the union works. But if I were to add another column here, and it's an integer column, it would not work because the union query must have the same number of columns, right? I will get an error. However, if I were to add an integer column in the second position in both tables, they would work again because again, I have the same number of columns and they have the same data type. Simple aggregation, I need the sign up date of my last member. So I need to work with the members table, and we have a field here which is join date, and I need to get the latest value of this date, the time when a member last joined, right? So how can I do that? I can take my join date field and run an aggregation on top of it. What is the correct aggregation in this case? It is max, because when it comes to dates, max will take the latest date, whereas min will take the earliest date. And I can label this as latest and get the result I need. Now, how aggregations work? They are functions that look like this. You write the name of the function, and then in round brackets you provide the arguments. The first argument is always the column on which to run the aggregation, and what the aggregation does is that it takes a list of values, could be 10, 100, a million, 10 million, it doesn't matter. It takes a long list of values and it compresses this list to a single value. It does like we've seen in this case, taking all of the dates and then returning the latest date. Now to place this in our map, we get the data from the table, we filter it, and then sometimes we do a grouping, which we shall see later in the exercises. But whether we do grouping or not, here we have aggregations. And if we haven't done any grouping, the aggregation works at the level of all the rows. So in the absence of grouping, as in this case, the aggregation will look at all the rows in my table, except for the rows that I filtered away. But otherwise it will look at all the rows and then it will compress them into a single value. More aggregation. We need the first and last name of the last member who signed up, not just the date. So in the previous exercise, we saw that we can say select max join date from members, and we would get the last join date, the date when the last member signed up, right? So given that I want the first and the last name, you might think that you can say first name and surname in here, but this actually doesn't work. This gives an error. The error is that the column first name must appear in the group by clause or be used in an aggregate function. Now, the meaning behind this error and how to avoid it is described in detail in the mental models course in the group by section. But the short version of it is that what you're doing here is that with this aggregation, you're compressing join date to a single value, but you're doing no such compression or aggregation for first name and surname. And so SQL is left with the instruction to return something like this. And as you can see, here we have a single value, but for these columns, we have multiple values. And this does not work in SQL because you need all columns to have the same number of values. And so it throws an error. And what we really need to do here is to take this maximum join date and use it in a where filter, because we only want to keep that row which corresponds to the latest join date. So we can take the members table and get the row where join date is equal to the max join date. And from that, select the name and the surname. Unfortunately, this also doesn't work. So what we saw in the course is that you're not allowed to use aggregations inside where. So you cannot use max inside where. And the reason why is actually pretty clear, because aggregations happen at this stage in the process, and aggregations need to know whether a group by has occurred or not. They need to know whether they have to happen over all the rows in the table or only within the groups defined by the group by. And when we are at the where stage, the group by hasn't happened yet, so we don't know at which level to execute the aggregations. And because of this, we are not allowed to do aggregations inside the where statement. So how can we solve the problem now? Well, a sort of cheating solution would be if we knew the exact value of join date, we could place it here and then our filter would work. We're not using an aggregation, and we could put join date in here to display it as well, and that would work. However, this is a bit cheating, right? Because the maximum join date is actually a dynamic value. It will change with time. So we don't want to hard code it. We want to actually compute it. But because this is not allowed, what we actually need is a subquery. And the subquery is a SQL query that runs within a query to return a certain result. And we can have a subquery by opening round brackets here and writing a query. And in this query, we need to go to the members table and select the maximum join date. And this is our actual solution. So in this execution, you can imagine that SQL will go here inside the subquery, run this, get the maximum join date, place it in the filter, keep only the row for the latest member who has joined, and then retrieve what we need about this member. Let us now move to the joins and subqueries exercises. The first exercise, retrieve the start times of members' bookings. Now, we can see that the information we need is spread out into tables because we want the start time for bookings, and that information is in the bookings table. But we want to filter to only get members named David Farrell. And the name of the member is contained in the members table. So because of that, we will need a join. So if we briefly look at the map for the order of SQL operations, we can see here that from and join are really the same step. And how this works is that in the from statement, sometimes all my data is in one table and then I just provide the name of that table. But sometimes I need to combine 2 or more different tables in order to get my data, and in that case I would use the join. But everything in SQL works with tables, right? So when I take 2 or more tables and combine them together, at the end all I get is just another table. And this is why from and join are actually the same component, and they are the same step. So as usual, let us start with the from part, and we need to take the bookings table and we need to join it on the members table. And I can give an alias to each table to make my life easier. So I will call this book and I will call this mem. And then I need to specify the logical condition for joining this table. And the logical condition is that the mem ID column in the bookings table is really the same thing as the mem ID column in the members table. Concretely, you can imagine SQL going row by row in the bookings table and looking at the mem ID and then checking whether this mem ID is present in the members table. And if it's present, it combines the row, the current row from bookings with the matching row from members, does this with all the matching rows, and then drops rows which don't have a match. And we saw that in detail in the mental models course, so I'm not going to go in depth into it. Now that we have our table, which is comes from the join of members and bookings, we can properly filter it. And what we want is that the first name column is David in the column which comes from the members table, right? So mem.firstname is indicating the parent table and then the column name. And the surname is equal to Farrell. And remember, single quotes when using pieces of text. This is a where filter. You have 2 logical conditions, and then we use the operator AND because both of them need to be true. So now we have filtered our data, and finally we need to select the start times. And that's our query. Now remember that when we use join in a query, what's implied is that we are using inner join, and there are several types of join, but inner join is the most common, so it's the default one. And what inner join means is that it's going to return from the 2 tables that we're joining, is going to return only the rows that have a match, and all the rows that don't have a match are going to be dropped. So if there's a row in bookings and it has a mem ID that doesn't exist in the members table, that row will be dropped. And conversely, if there's a row in the members table and it has a mem ID that is not referenced in the bookings table, that row will also be dropped. And that's an inner join. Work out the start times of bookings for tennis courts. So we need to get the facilities that are actually tennis courts, and then for each of the facility we'll have several bookings, and we need to get the start time for those bookings, and it will be in a specific date. So we know that we need the data from these 2 tables because the name of the facility is here, but the data about the bookings is here. So I will go from CD facilities, join CD bookings on. What are the fields that we can join on logically? Now let me first give an alias to these tables. So I will call this fax, and this I will call book. And now what I need to see is that the facility ID matches on both sides. Now we can work on our filters. So first of all, I only want to look at tennis courts. And if you look at the result here, it means that in the name of the facility, we want to see tennis. And so we can filter on string patterns, on text patterns by using the like command. So I can take facilities name and get it like tennis, and the percentage signs are wildcards, which means that tennis could be preceded and followed by 0 or more characters. We don't care. We just want to get those strings that have tennis in them. But that's not enough as a condition. We also need the booking to have happened on a specific date. So I will put an AND here. So AND is the operator we need because we're providing two logical conditions and they both need to be true. So AND is what we need. And then I can take the start time from the bookings table and say that it should be equal to the date provided in the instructions, because I want the booking to have happened in this particular date. However, this will not work. So I can actually complete the query and show you that it will not work, because here we get 0 results. So can you figure out why this command here did not work? Now I'm going to write a few comments here, and this is how you write them, and they are just pieces of text. They're not actually executed as code, and I'll just use them to show you what's going on. So the value for start time looks like this. So this is a timestamp and it's showing a specific point in time. But the date that we are providing for the comparison looks like this. So as you can see, we have something that is less granular because we're not showing all of this data about hour, minute, and second. Now, in order to compare these two things which are different, SQL automatically fills in this date over here. And what it does is that since there's nothing there, it puts zeros in there. And now that it has made this extension, it's going to actually compare them. So when you look at this comparison over here between these two elements, this comparison is false because the hour is different. Now when we write this filter command over here, SQL is looking at every single start time and then comparing it with this value over here, which is the very first moment of that date. But there's no start time that is exactly like this one. So basically this is always false, and thus we get 0 rows in our result. So what is the solution to this? When we take a start time from the data, before comparing it, we can put it into the date function. And if I take my example here, if I put it into the date function, it's going to drop that extra information about hour, minute, and second, and it's only going to keep the information about the date. So once I do this, if I pass it to the date function before comparing it to my reference date, now this one is going to become the result, which is this one, and then I'm going to compare it with my reference date, and then this is going to be true. So all this to say that before we compare start time with our reference date, we need to reduce its granularity and we need to reduce it to its date. So if I run the query now, I will actually get my start times. And after this, I just need to add the name. And finally, I need to order by time. So I need to order by book start time. There is still a small error here, so sometimes you just have to look at what you get and what's expected. And if you notice here, we are returning data about the table tennis facility, but we're actually just interested in tennis court. So what are we missing here? The string filter is not precise enough, and we need to change this into tennis court. And now we get our results. Produce a list of all members who have recommended another member. Now, if we look at the members table, we have all this data about each member, and then we know if they were recommended by another member. And recommended by is the ID of the member who has recommended them. And because of this, the members table, like we said, has a relation to itself because one of its columns references its ID column. So let's see how to put this in practice. So to be clear, I simply want a list of members who appear to have recommended another member. So if I wanted just the IDs of these people, my task would be much simpler, right? I would go to the members table and then I could select recommended by, and then I will put a distinct in here to avoid repetitions. And what I would get here is the IDs of all members who have recommended another member. However, the problem does not want this because the problem wants the first name and surname of these people. So in order to get the first name and the surname of these people, I need to plug this ID back into the members table and get the data there. So for example, if I went to the members table and I selected everything where the mem ID is 11, then I would get the data for this first member. But now I need to do this for all members. So what I will have to do is to take the members table and join it to itself. And the first time I take the table, I'm looking at the members, quite simply. But the second time I take the members table, I'm looking at data about the recommenders of the members. So I will call this second instance Rex. So both of these, they come from the same table, but they're now two separate instances. And what is the logic to join these two tables? The members table has this recommended by field, and we take the ID from recommended by and we plug it back into the table, into memID, to get the data about the recommenders. And now we can go into the recommenders, which we got by plugging that ID, and get their first name and surname. I want to avoid repetition because a member may have been recommending multiple members, but I want to avoid repetition. So I will put a distinct to make sure that I don't get any repeated rows at the end. And then finally, I can order by surname and first name. And I get my result. So I encourage you to play with this and experiment a bit until it is clear. And in my mental models course, I go into depth into the self-join and do a visualization in Google Sheets that also makes it much clearer. Produce a list of all members along with their recommender. Now, if we look at the members table, we have a few columns and then we have the recommended by column. And sometimes we have the ID of another member who recommended this member. It can be repeated because the same member may have recommended multiple people. And then sometimes this is empty. And when this is empty, we have a null in here, which is the value that SQL uses to represent absence of data. Now, let us count the rows in members. So you might know that to count the rows of a table, we can do a simple aggregation, which is count star, and we get 31. And let's just make a note of this, that members has 31 rows, because in the result, we want a list of all members. So we must ensure that we return 31 rows in our results. Now I'm gonna delete this select. And as before, I want to go for each member and check the ID they have here in recommended by, and then plug this back into the table into memID so I can get the data about the recommender as well. And I can do that with a self join. So let me take members and join on itself. And the first time I will call it mems, and the second time I will call it recs. And the logic for joining is that in mems, recommended by is the same, is connected to recs memID. So this is taking the ID in the recommended by field and plugging it back into memID to get the data about the recommender. Now, what do I want from this? I want to get the first name of the member and the last name, surname, and then the first name and last name of the recommender. Surname. Great. So it's starting to look like the right result, but how many rows do we think we have here? And in order to count the rows, I can do select count star from, and then if I simply take this table, if I simply take this query and enclose it in brackets, now this becomes a subquery. So I can, the subquery must have an alias, so I can give it an alias like this, and I get 22. So how this works is that first SQL will compute the content of the subquery, which is the table that we saw before, and then it will, we need to assign it an alias, otherwise it doesn't work. This changes a bit by system, but in Postgres you need to do this. So we call it simply T1, and then we run a count star on this table to get the number of rows. And we see that the result has 22 rows. And this is an issue because we saw before that members has 31 rows and that we want to return all of the members. Therefore, our result should also have 31 rows. So can you figure out why are we missing some rows here? Now the issue here is that we are using an inner join. So remember, when we don't specify the type of join, it's an inner join. And what does an inner join do? It keeps only rows that have matches. So we saw before that in members, sometimes this field is empty. It has a null value because, maybe the member wasn't recommended by anyone. Maybe they just applied themselves. And what happens when we use this in an inner join and it has a null value? The row for that member will be dropped because obviously it cannot have a match with memID because null cannot match with anything, with any ID. And so that row is dropped and we lose it. However, that's not what we want to do. Therefore, instead of an inner join, we need to use a left join here. The left join will look at the left table, so the table that is left of the join command, and it will make sure to keep all the rows in that table, even the rows that don't have a match. In the rows that don't have a match, it will not drop them, it will just put a null in the values that correspond to the right table. And if I run the count again, I will get 31. So now I'm keeping all the members and I have the number of rows that I need. So now I can get rid of all of these because I know I have the right amount of rows, and I can get my selection over here. And it would actually help if we could make this a bit more ordered and assign aliases to the columns. So I will follow the expected results here and call this mem first name, mem surname, rec first name, rec surname. Now we have the proper labels, and you can see here that we always have the name of the member, but some member weren't recommended by anyone, and therefore for the first and last name of the recommender, we simply have null values, and this is what the left join does. The last step here is to order, and we want to order by the last name and the first name of each member. And we finally get our result. So typically you use inner joins, which is the default join, because you're only interested in the rows from both tables that actually have a match. But sometimes you want to keep all the data about one table, and then you would put that table on the left side and do a left join, as we did in this case. Produce a list of all members who have used a tennis court. Now, for this problem, we need to combine data from all our tables, because we need to look at the members, and we need to look at their bookings, and we need to check what's the name of the facility for their bookings. So as always, let us start with the from part, and let us start by joining together all of these tables. CD facilities on facility ID, and then I want to also join on members, and that is my join. So we can always join 2 or more tables. In this case, we're joining 3 tables, and how this works is that the first join creates a new table, and then this new table is joined with the next one over here, and this is how multiple joins are managed. Now I have my table, which is the join of all of these tables, and we're only interested in members who have used the tennis court. If a member has made no bookings, we're not interested in that member, and so it's okay to have a join and not a left join. And for each booking, we want to see the name of the facility, and if there was a booking who didn't have the name of the facility, we wouldn't be interested in that booking anyway. And so this join here also can be an inner join and doesn't need to be a left join. This is how you can think about whether to have a join or a left join. Now we want the booking to include a tennis court, so we can filter on this table, and we will look at the name of the facility and make sure that it has tennis court in it with the like operator. And now that we have filtered, we can get the first name and the surname of the member, and we can get the facility name. So here we have a starting result. Now in the expected result, we have merged the first name and the surname into a single string, and in SQL you can do this with a concatenation operator, which is basically taking 2 strings and putting them together into one string. Now if I do this here, I will get something like this, and so this looks a bit weird, and what I want to do here is to add an empty space in between and again concatenate it, and now the names will look fine. I also want to label this as member and this other column as facility to match the expected results. Next, I need to ensure that there is no duplicate data. So at the end of it all, I will want to have distinct in order to remove duplicate rows. And then I want to order the final result by member name and facility name. So order by member and then facility. And this will work because the order by coming second to last, coming at the end of our logical order of SQL operations. Over here, the order by is aware of the alias, is aware of the label that I have put on the columns. And here I get the results that I needed. Not a lot happening here, to be honest. It's just that we're joining 3 tables instead of 2, but it still works just like any other join. And then concatenating the strings, filtering according to the facility name, and then removing duplicate rows, and finally ordering. Produce a list of costly bookings. So we want to see all bookings that occurred in this particular day, and we want to see how much they cost the member, and we want to keep the bookings that cost more than $30. So clearly, in this case, we also need the information from all tables, because if you look at the expected results, we want the name of the member, which is in the members table, the name of the facility, which is in the facilities table, and the cost for which we will need the bookings table. So we need to start with a join of these 3 tables, and since we did it already in the last exercise, I have copied the code for that join. So if you want more detail on this, go and check the last exercise, as well as I have copied the code to get the first name of the member by concatenating strings and the name of the facility. Now we need to calculate the cost of each booking. So how does it work looking at our data? So we have here a list of bookings, and a booking is defined as a number of slots, and a slot is a 30-minute usage of that facility. And then we also have memID, which tells us whether the member is a guest or not. I mean, whether the person is a guest or a member. Because if MID is 0, then that person is a guest, otherwise that person is a member. And then I also know the facility that this person booked. And if I go and look at the facility, it has 2 different prices, right? One price is for members, the other price is for guests, and the price applies to the slots. So we have all of the ingredients that we need for the cost in our join, right? And to convince ourselves of that, let us actually select them here. So in booking, I can see facility ID, member ID, and then slots. And then in facility, I can see the member cost, the guest cost, and I guess that's all I need really to calculate the cost. And as you can see, after the join, I'm in a really good position because for each row, I do have all of these values placed on each row. So now I just have to figure out how to combine all of these values in order to get the cost. Now, the way that I can get the cost is that I can look at the number of slots, and then I need to multiply this by the right cost, which is either member cost or guest cost. And how do I know which of these to pick? It depends on the memID. If the memID is 0, then I will use the guest cost. Otherwise, I will use the member cost. So let me go back to my code here. And after this, I can say, I want to take the slots and I want to multiply it by either member cost or guest cost. Now, how can I put some logic in here that will choose either member cost or guest cost based on the ID of this person? What can I use in order to make this choice? Whenever I have such a choice to make, I need to use a case statement. So I can start with the case statement here, and I will already write the end of it so that I don't forget it. And then in the case statement, what do I need to check for? I need to check that the member ID is 0. In that case, I will use the guest cost. And in all other cases, I will use the member cost. So I'm taking slots and then I'm using this case when to decide by which column I'm going to multiply it. And this is actually my cost. Now let's take a look at this. And so I get this error that the column reference memID is ambiguous. So can you figure out why I got this error? What's happening is that I have joined multiple tables and the memID column appears twice now in my join. And so I cannot refer to it just by name because SQL doesn't know which column I want. So I have to reference the parent of the column every time I use it. So here I will say that it comes from the bookings table. And now I get my result. So if I see here, then I can see that I have successfully calculated my cost. And let's look at the first row. First, it's the mem ID is not 0, therefore it's a member. And here the member cost is 0, meaning that this facility is free for members. So regardless of the slots, the cost will be 0. And let's look at one who is a guest. So this one is clearly a guest, and they have taken one slot, and the member cost is 0, but so it's free for members, but it costs 5 per slot for guests. So the total cost is 5. So based on this sanity check, the cost looks good. Now I need to actually filter my table because we should consider only bookings that occurred in a certain day. So after creating my new table and joining, I can write a where filter to drop the rows that I don't need. And I can say, this is the time column that I'm interested in. The start time needs to be equal to this date over here. And we have seen before that this will not work because start time is a timestamp. It also shows hour, minute and seconds, whereas here is just a date. So this comparison will fail. And so before I do the comparison, I need to take this and reduce it to a date so that I'm comparing apples to apples on the time. Check that that didn't break anything. Now we should have significantly fewer rows. So now what we need to do is to only keep rows that have a cost which is higher than 30. So can I go here and say and cost bigger than 30? No, I cannot do it. Column cost does not exist, right? Typical mistake. But if you look at the logical order of SQL operations, first you have the sourcing of the data, then you have the where filter, and then all of the logic by which we calculate the cost happens here, and the label cost happens here as well. So we cannot filter on this column, on the column cost, because the where component has no idea about the column cost. So this will not work. But what we can do is to take all of the logic we've done until now and wrap it in round brackets, and then introduce a common table expression and call this T1. So I will say with T1 as, and then I can from T1, and now I can use my filter, right? So cost bigger than 30, I can select star from this table. And I'm starting to get somewhere because the cost has been successfully filtered. Now I have a lot of columns that I don't want in my final result that I use to help me reason about the cost. So I want to keep member, and I want to keep the facility, but I don't want to keep any of these. Great. Now, as a final step, I need to order by cost descending, and there's actually a issue that I have because I copy pasted code from the previous exercise. I kept a distinct, and you have to be very careful with this, especially if you copy paste code. Anyway, for learning, it would be best to write it always from scratch. But the distinct will remove rows that are duplicate and can actually cause an issue. Now I remove the distinct and I get the solution that I want. And if you look here, we have, if you look at the last two rows, you can see that they're absolutely identical. And so the distinct would remove them. But there are two bookings that happen to be just the same in our data. And we want to keep them, we don't want to delete them. So having distinct was a mistake in this case. To summarize what we did here, first we joined all the tables so we could have all the columns that we needed side by side. And then we filtered on the date, pretty straightforward. And then we took the first name and surname and concatenated them together, as well as the facility name. And then we computed the cost. And to compute the cost, we got the number of slots and we used a case when to multiply this by either the guest cost or the member cost according to the member's ID. And at the end, we wrapped everything in a common table expression so that we could filter on this newly computed value of cost and keep only those bookings that had a cost higher than 30. Now, I am aware that the question said not to use any subqueries. Technically, I didn't because this is a common table expression. But if you look at the author solution, it is slightly different than ours. So here they did basically the same thing that we did to compute the cost, except that in the case when they inserted the whole expression, which is fine, works just the same. The difference is that in this case, they added a lot of logic in the where filter so that they could use a where filter in the first query. So clearly they didn't use any columns that were added at the stage of the select. They didn't use cost, for example, because like we said, that wouldn't be possible. So what they did is that they added the date filter over here. And then in this case, they added a logical expression. And in this logical expression, either one of these two needed to be true for us to keep the row. Either the memID is 0, meaning that it's a guest, and so the calculation based on guest cost ends up being bigger than 30. Or the memID is not 0, which means it's a member, and then this calculation based on the member cost ends up being bigger than 30. So this works. I personally think that there's quite some repetition of the cost calculation, both by putting it in the where filter and by putting it inside the case when. And so I think that the solution we have here is a bit cleaner because we're only calculating cost once in this case, and then we're simply referencing it thanks to the common table expression. So if you look at the mental models course, you will see that I warmly recommend not repeating logic in the code and using common table expressions as often as possible, because I think that they made the code clearer and simpler to understand. Produce a list of all members and their recommender without any joins. Now we have already solved this problem, and we have solved it with a self join. As you remember, we take the members table and join it on itself so that we can get this recommended by ID and plug it into members ID and then see the names of both the member and their recommender side by side. But here we are challenged to do it without a join. So let us go to the members table and let us select the first name and the surname. Now we actually want to concatenate these two into a single string and call this member. Now, how can we get data about the recommender without a self-join? Typically, when you have to combine data, you'll always have a choice between a join and a subquery, right? So what we can do is to have a subquery here, which looks at the recommended by ID from this table and goes back to the members table and gets the data that we need. So let's see how that would look. Let us give an alias to this table and call it mems. And now we need to go back to this table inside the subquery and we can call it recs. And we want to select again the first name and surname like we're doing here. And how are we able to identify the right row inside this subquery? We can use a where filter, and we want the recs mem ID to be equal to the mems recommended by value. And once we get this value, we can call this recommender. And now we want to avoid duplicates. So after our outer select, we can say distinct, which will remove any duplicates from the result. And then we want to sort, I guess, by member and recommender. And here we get our result. So replacing a join with a subquery. So we go row by row in members, and then we take the recommended by ID, and then we query the members table again inside the subquery, and we use the where filter to plug in that recommended by and find the row where the mem ID is equal to it. And then getting first name and surname, we get the data about the recommender. And that's how we can do it. In the mental models course, we discuss the subqueries, and in this particular case, we talk about a correlated subquery. Why is this a correlated subquery? Because you can imagine that the query that is in here, it runs again for every row. Because for every row, I have a different value of recommended by, and I need to plug this value into the members table to get the data about the recommender. So this is a correlated subquery because it runs every time, and it is different for every row of the members table. Produce a list of costly bookings using a subquery. So this is the exact exercise that we did before. And as you will remember, we actually ignored the instructions a bit, and we did use not a subquery, but a common table expression. And by reference, this is the code that we used. And this code works with that exercise as well. And we get the result. So you can go back to that exercise to see the logic behind this code and why this works. And if we look at the author's solution, they are actually using a subquery instead of a common table expression. So they have an outer query, which is select member facility cost from, and then instead of the from, instead of telling the name of the table, they have all of this logic here in this subquery, which they call bookings. And finally, they add a filter and order. Now, this is technically correct, it works, but I'm not a fan of writing queries like this. I prefer writing them like this as a common table expression, and I explain this in detail in my mental models course. The reason I prefer this is because it doesn't break queries apart. So in my case, this is one query and this is another query, and it's pretty easy and simple to read. However, in this case, you will start reading this query and then it is broken in two by another query. And when people do this, sometimes they go even further and here when you have the from, instead of a table, you have yet another subquery. It gets really complicated. So because of these two approaches are equivalent, I definitely recommend going for a common table expression every time and avoiding subqueries unless they are really compact and you can fit them in one row. Let us now get started with aggregation exercises, and the first problem, count the number of facilities. So I can go to the facilities table, and then when I want to count the number of rows in a table, and here every row is a facility, I can use the count star aggregation, and we get the count of facilities. So what we see here is a global aggregation, and when you run an aggregation without having done any grouping, it runs on the whole table. Therefore, it will take all the rows of this table, no matter how many, compress them into one number, which is determined by the aggregation function. In this case, we have a count, and it returns a total of 9 rows. So in our map, aggregation happens right here. So we sourced the table, we filtered it if needed, and then we might do a grouping, which we didn't do in this case. But whether we do it or not, aggregations happen here. And if grouping didn't happen, the aggregation is at the level of the whole table. Count the number of expensive facilities. This is similar to the previous exercise. We can go to the facilities table, but here we can add a filtering because we're only interested in facilities that have guest cost greater than or equal to 10. And now once again, I can get my aggregation count star to count the number of rows of this resulting table. Looking again at our map, why does this work? Because with the from, we're sourcing the table, and immediately after the where runs and it drops unneeded rows. And then we can decide whether to group by or not, and in this case, we're not doing it. But then the aggregations run. So by the time the aggregations run, I've already dropped the rows in the where. And this is why, in this case, after dropping some rows, the aggregation only sees 6 rows, which is what we want. Count the number of recommendations each member makes. So in the members table, we have a field which is recommended by, and here is the ID of the member who recommended the member that this row is about. So now we want to get all these recommended by values and count how many times they appear. So I can go to my members table, and what I need to do here is to group by recommended by. So what this will do is that it will take all the unique values of this column recommended by, and then it will allow me to do an aggregation on all of the rows in which those values occur. So now I can go here to select and call this column again. And if I run this query, I get all the unique values of recommended by without any repetitions. And now I can run an aggregation like count star. What this will do is that for recommended by value 11, it will run this aggregation on all the rows in which recommended by is 11. And the aggregation in this case is count star, which means that it will return the number of rows in which 11 appears, which in the result happens to be 1. And so on for all the values. What I also want to do is to order by recommended by to match the expected results. Now what we get here is almost correct. We see all the unique values of this column, and we see the number of times that it appears in our data. But there's one discrepancy, which is this last row over here. So in this last row, you cannot see anything, which means that it's a null value. So it's a value that represents absence of data. And why does this occur? if you look at the original recommended by column, there is a bunch of null values in this column because there's a bunch of members that have null in recommended by. So maybe we don't know who recommended them, or maybe they weren't recommended, they just applied independently. When you group by, you take all the unique values of the recommended by column, and that includes the null value. The null value defines a group of its own. And the count works as expected because we can see that there are 9 members for whom we don't have the recommended by value. But the solution does not want to see this because we only want to see the number of recommendations each member has made. So we actually need to drop this row. Therefore, how can I drop this row? Well, it's as simple as going to after the from and putting a simple filter and saying recommended by is not null. And this will drop all of the rows in which that value is null, therefore it won't appear in the grouping, and now our results are correct. Remember, when you're checking whether a value is null or not, you need to use the is null or is not null. You cannot actually do equal or not equal because null is not an actual value. It's just a notation for the absence of a value. So you cannot say that something is equal or not equal to null. You have to say that it is not null. Let's list the total slots booked per facility. Now, first question, where is the information that I need? The number of slots booked is in the CD bookings, and there I also have the facility ID, so I can work with that table. And now, how can I get the total slots for each facility? I can group by facility ID, and then I can select that facility ID. And within each unique facility ID, what type of aggregation might I want to do? In every booking, we have a certain number of slots, right? And so we want to find all the bookings for a certain facility ID and then sum all the slots that are being booked. So I can write sum of slots over here. And then I want to name this column total slots, looking at the expected results. But this will actually not work because it's two separate words. So I actually need to use quotes for this. And remember, I have to use double quotes because it's a column name. So it's always double quotes for the column name and single quotes for pieces of text. And finally, I need to order by facility ID. And I get the results. So for facility ID 0, we looked at all the rows where facility ID was 0. And we squished all of this to a single value, which is the unique facility ID. And then we looked at all the slots that were occurring in these rows, and then we compressed them, we squished them to a single value as well, using the sum aggregation, so summing them all up. And then we get the sum of the total slots. List the total slots booked per facility in a given month. So this is similar to the previous problem, except that we are now isolating a specific time period. And so let us think about how we can select bookings that happened in the month of September 2012. Now we can go to the bookings table and select the start time column. And to help our exercise, I will order by start time descending, and I will limit our results to 20. And you can see here that start time is a timestamp column and it goes down to the second because we have year, month, day, hour, minutes, second. So how can we check whether any of these dates corresponds to September 2012? We could add a logical check here. We could say that start time needs to be greater than or equal to 2012 September 1st, and it needs to be strictly smaller than 2012 October 1st. And this will actually work. As an alternative, there is a nice function that we could use, which is the following: date trunc month start time. Let's see what that looks like. So what do you think this function does? Like the name suggests, it truncates the date to a specific granularity that we choose here. And so all of the months are reduced to the very first moment of the month in which they occur. So it is sort of cutting that date and removing some information and reducing the granularity. I could of course have other values here, such as day, and then every timestamp here would be reduced to its day. But I actually want to use month. And now that I have this, I can set an equality and I can say that I want this to be equal to September 2012. And this will actually work, and I also think it's nicer than the range that we showed before. Now I've taken the code for the previous exercise and copied it here because it's actually pretty similar, except that now after we get bookings, we need to insert a filter to isolate our time range. And actually we can use this logical condition directly. I'll delete all the rest. And now what I need to do is to change the ordering, and I actually need to order by the total slots here. And I get my result. To summarize, I get the bookings table, and then I take the start time timestamp and I truncate it because I'm only interested in the month of that time, and then I make sure that the month is the one I actually need. And then I'm grouping by facility ID, and then I'm getting the facility ID, and within each of those groups I'm summing all the slots, and finally I'm ordering by this column. List the total slots booked per facility per month in the year 2012. So again, our data is in bookings, and now we want to see how can we isolate the time period of the year 2012 for this table. Now once again, I am looking at the start time column from bookings to see how we can extract the year. So in the previous exercise, we saw the date trunc function, and we could apply it here as well. So we could say date trunc start time, year from start time, right? Because we will want to see it at the year resolution. And then we would get something like this. And then we could check that this is equal to 2012 0101. And this would actually work, but there's actually a better way to do it. What we could do here is that we could say extract year from start time. And when we look at here, we got an integer that actually represents the year. And it will be easy now to just say equal to 2012 and make that test. So if we look at what happened here, extract is a different function than datetime because extract is getting the year and outputting it as an integer, whereas datetime is still outputting a timestamp or a date, just with lower granularity. So you have to use one or another according to your needs. Now to proceed with our query, we can get CD bookings and add a filter here and insert this expression in the filter, and we want the year to be 2012. So this will take care of isolating our desired time period. Next, we want to check the total slots within groups defined by facility ID and month. So we want the total for each facility for each month, as you can see here in the respected results, such that we can say that for facility ID 0 in the month of July in the year 2012, we booked 270 slots. So let's see how we can do that. This basically means that we have to group by multiple values, right? And facility ID is easy, we have it. However, we do not have the month. So how can we extract the month from the start time over here? Well, we can use the extract function, right? Which we just saw. So if we write it like this and we put month here, this function will look at the month and then will output the month as an actual integer. And the thing is that I can group by the names of columns, but I can also group by transformations on columns. It works just as well. SQL will compute this expression over here, and then it will get the value, and then we'll group by that value. Now, when it comes to getting the columns, what I usually do is that when I group by, I want to see the columns in which I grouped. So I just copy what I had here and I add it to my query. And then what aggregation do I want to do within the groups defined by these two columns? I have seen it in the previous exercise. I want to sum over the slots and get the total slots. I also want to take this column over here and rename it as month. And now I have to order by ID and month. And we get the data that we needed. So what did we learn with this exercise? We learned to use the extract function to get a number out of a date, and we use that. We have used grouping by multiple columns, which simply defines a group as the combination of the unique values of two or more columns. That's what multiple grouping does. We have also seen that not only you can group by providing a column name, but you can also group by a logical operation. And you should then reference that same operation in the select statement so that you can get the value that was obtained. Find the count of members who have made at least one booking. So where is the data that we need? It's in the bookings table. And for every booking, we have the ID of the member who has made the booking. So I can select this column, and clearly I can run a count on this column, and the count will return the number of non-null values. However, this count, as you can see, is quite inflated. What's happening here is that a single member can make any number of bookings, and now we're basically counting all the bookings in here. But if I put distinct in here, then I'm only going to count the unique values of memID in my bookings table. And this gives me the total number of members who have made at least one booking. So count will get you the count of non-null values, and count distinct will get you the count of unique non-null values. List the facilities with more than 1,000 slots booked. So what do we need to do here? We need to look at each facility and how many slots they each booked. So where is the data for this? As you can see, again, the data is in the bookings table. Now I don't need to do any filter, so I don't need the where statement. but I need to count the total slots within each facility. So I need a group by. And I can group by the facility ID. And once I do that, I can select the facility ID. And to get the total slots, I can simply do sum of slots. And I can call this total slots. It's double quotes for a column name. Now I need to add the filter. I want to keep those that have sum of slots bigger than 1000. And I cannot do it in a where statement, right? So if I were to write this in a where statement, I would get that aggregate functions are not allowed in where. And if I look at my map, we have been through this again. The where runs first, right after we source the data, whereas aggregations happen later. So the where cannot be aware of any aggregations that I've done. For this purpose, we actually have the having component. So the having component works just like where. It's a filter. It drops rows based on logical conditions. The difference is that having runs after the aggregations and it works on the aggregations. So I get the data, do my first filtering, then do the grouping, compute an aggregation, and then I can filter it again based on the result of the aggregation. So I can now go to my query and take this and put having instead of where and place it after the group by. And we get our result. And all we need to do is to order by facility ID. And we get our result. Find the total revenue of each facility. So we want a list of facilities by name along with their total revenue. First question, as always, where is my data? So if I want facilities name, it's in the facilities table. But to calculate the revenue, I need to know about the bookings. So I'll actually need to join on both of these tables. So I will write from cd bookings book join cd facilities facts on facility ID. Next, I will want the total revenue of the facilities, but I don't even have the revenue yet. So my first priority should be to compute the revenue. Let us first select the facility name, and here I will now need to add the revenue. So to do that, I will need to have something like cost times slots, and that determines the revenue of each booking. However, I don't have a single value for cost. I have two values, member cost and guest cost. And as you remember from previous exercises, I need to choose every time which of them to apply. And the way that I can choose is by looking at the member ID. And if it's 0, then I need to use the guest cost. Otherwise, I need to use the member cost. So what can we use now in order to choose between these two variants for each booking? We can use the case statement for this. So I will say case and then immediately close it with end. And I will say when book memid equals 0, then fax guest cost. I always need to reference the parent table after a join to avoid confusion. Else fax member cost. So this will allow me to get the cost dynamically. It allows me to choose between two columns. And I can multiply this by slots and get the revenue. Now, if I run this, I get this result, which is the name of the facility and the revenue. But I need to ask myself, at what level am I working here? In other words, what does each row represent? Well, I haven't grouped yet, so each row here represents a single booking. Having joined bookings and facilities and not having grouped anything, we are still at the level of this table where every row represents a single booking. So to find the total revenue for each facility, I now need to do an aggregation. I need to group by facility name and then sum all the revenue. I can actually do this within the same query by saying group by facility name. And if I run this, I will now get an error. Can you figure out why I'm getting this error now? So I have grouped by facility name, and then I'm selecting by facility name, and that works well because now this column has been squished, has been compressed to show only the unique names for each facility. However, I am then adding another column, which is revenue, which I have not compressed in any way. Therefore, this column has a different number of rows than this column. And the general rule of grouping is that after I group by one or more columns, I can select by the columns that are in the grouping and aggregations, right? So nothing else is allowed. So fax name is good because it's in the grouping. Revenue is not good because it's not in the grouping and it's not an aggregation. And to solve this, I can simply turn it into an aggregation by doing sum over here. And when I run this, this actually works. And now all I need to do is to sort by revenue. So if I say order by revenue, I will get the result that I need. So there's a few things going on here, but I can understand it by looking at my map. Now, what I'm doing is that I'm first sourcing the data, and I'm actually joining two tables in order to create a new table where my data is. Then I'm grouping by a column, which is the facility name. So this compresses the column to all the unique facility name. And next I run the aggregation, right? So the aggregation can be a sum over an existing column, but as we saw in the mental models course, the aggregation can also be a sum over a calculation. I can actually run logic in there. It's very flexible. So if I had a revenue column here, I would just say sum revenue as revenue and it would be simpler. But I need to put some logic in there. And this logic involves choosing whether to get guest cost or member cost. But I'm perfectly able to put that logic inside the sum. And so SQL will first evaluate this logic for each row, and then it will sum up all the results and it will give me revenue. Finally, after computing that aggregation, I select the columns that I need, and then I do an order by at the end. Find facilities with a total revenue of less than 1,000. So the question is pretty clear, but wait a second. We calculated the total revenue by facility in the previous exercise. So we can probably just adapt that code. Here's the code from the previous exercise, so check that out if you want to know how I wrote this. And if I run this code, I do indeed get the total revenue for each facility. And now I just need to keep those with a revenue less than 1,000. So how can I do that? It's a filter, right? I need to filter on this revenue column. I cannot use a where filter because this revenue is an aggregation and it was computed after the group by after the where. So the where wouldn't be aware of that column. But as we have seen, there is a keyword, there is a statement called having, which does the same job as where. It filters based on logical conditions. However, it works on aggregations. So I could say having revenue smaller than 1,000. Unfortunately, this doesn't work. Can you figure out why this doesn't work? In our query, we do a grouping and then we compute an aggregation. And then we give it a label. And then we try to run a having filter on this label. If you look now at our map for the logical order of SQL operations, this is where the group by happens. This is where we compute our aggregation. And this is where having runs. And now having is trying to use the alias that comes at this step. But according to our rules, having does not know of the alias that's assigned at this step because it hasn't happened yet. Now, as the discussion for this exercise says, there are in fact database systems that try to make your life easier by allowing you to use labels in having, but that's not the case with Postgres. So we need a slightly different solution here. Note that if I repeated all of my logic in here, instead of using the label, it would work. So if I do this, I will get my result. I just need to order by revenue. And you see that I get the correct result. Why does it work when I put the whole logic in there instead of using the label? Once again, the logic happens here, and so the having is aware of this logic having happened. But the having is just not aware of the alias. However, I do not recommend repeating logic like this in your queries because it increases the chances of errors and it also makes them less elegant, less readable. So the simpler solution we can do here is to take this original query and put it in round brackets and then create a virtual table using a common table expression here and call this, all of this, T1. And then we can treat T1 like any other table. So I can say from T1 select everything where revenue is smaller than 1,000 and then order by revenue. Remove all this and we get the correct answer. To summarize, you can use having to filter on the result of aggregations. Unfortunately, in Postgres, you cannot use the labels that you assign to aggregations in having. So if it's a really small aggregation, like if it's select sum revenue and then all of the rest, then it's fine to say sum revenue smaller than 1,000. There's a small repetition, but it's not an issue. However, if your aggregation is more complex, as in this case, you don't really want to repeat it, and then you're forced to add an extra step to your query, which you can do with a common table expression. Output the facility ID that has the highest number of slots booked. So, first of all, we need to get the number of slots booked by facility. And we've actually done it before, but let's do it again. Where is our data? The data is in the bookings table. And we don't need to filter this table, but we do need to group by the facility ID. And then once we do this, we can select the facility ID. This will isolate all the unique values of this column. And within each unique value, we can sum the number of slots and call this total slots. And if we do this, we get the total slots for each facility. Now to get the top one, the quickest solution really would be to order by total slots and then limit the result to 1. However, this would give me the one with the smallest number of slots, because order is ascending by default. So I need to turn this into descending, and here I would get my solution. But given that this is a simple solution and it solved our exercise, can you imagine a situation in which this query would not achieve what we wanted it to? Let us say that there were multiple facilities that had the top number of total slots. So the top number of slots in our dataset is 1404, that's all good. But let's say that there were two facilities that had this top number, and we wanted to see both of them for our business purposes. What would happen here is that limit 1, so everything else would work correctly and the ordering would work correctly, but inevitably in the ordering, one of them would get the first spot and the other would get the second spot. And limit 1 is always cutting the output to a single row. Therefore, in this query, we would only ever see one facility ID, even if there were more that had the same number of top slots. So how can we solve this? Clearly, instead of combining order by and limit, we need to figure out a filter. We need to filter our table such that only the facilities with the top number of slots are returned. But we cannot really get the maximum of some slots in this query, because if I tried to do having some slots equals maximum of some slots, I would be told that aggregate function calls cannot be nested. And if I go back to my map, I can see that having can only run after all the aggregations have completed. But what we're trying to do here is to add a new aggregation inside having, and that basically doesn't work. So the simplest solution here is to just wrap all of this into a common table expression and then get this table that we've just defined and then select star where the total slots is equal to the maximum number of slots, which we know to be 1404. However, we cannot hard code the maximum number of slots because for one, we might not know what it is, and second, it will change with time, so this won't work when the data changes. So what's the alternative to hard coding this? We actually need some logic here to get the maximum value, and we can put that logic inside the subquery. And the subquery will go back to my table T1, and it will actually find the maximum of total slots from T1. So first this query will run, it will get the maximum, and then the filter will check for that maximum. And then I will get the required result. And this won't break if there are many facilities that share the same top spot. Because we're using a filter, all of them will be returned. So this is a perfectly good solution. For your information, you can also solve this with a window function, and which is a sort of row level aggregation that doesn't change the structure of the data. We've seen it in detail in the mental models course. So what I can do here is to use a window function to get the maximum value over the sum of slots. And then I will say over to make it clear that this is a window function, but I won't put anything in the window definition because I just want to look at my whole data set here. And I can label these max slots. And if I look at the data here, you can see that I will get the maximum for every row. And then to get the correct result, I can add a simple filter here saying that total slots should be equal to max slots. And I will only want to return facility ID and total slots. So this also solves the problem. What's interesting to note here, for the sake of understanding window functions more deeply, is that the aggregation function for this window clause works over an aggregation as well. So here we sum the total slots over each facility, and then the window function gets the maximum of all of those value. And this is quite a powerful feature. And if I look at my map over here, I can see that it makes perfect sense, because here is where we group by facility ID, and here is where we compute the aggregation, and then the window comes later, so the window is aware of the aggregation and the window can work on that. So a few different solutions here, and overall a really interesting exercise. List the total slots booked per facility per month, part 2. So this is a bit of a complex query, but the easiest way to get it is to look at the expected results. So what we see here is a facility ID, and then within each month of the year 2012, we get the total number of slots. And at the end of it, we have a null value here, and for facility 0, and what we get is the sum of all slots booked in 2012. And then the same pattern repeats with every facility. We have the total within each month, and then finally we have the total for that facility in the year. So there's 2 levels of aggregations here, and then if I go at the end, there's a 3rd level of aggregation, which is the total for all facilities within that year. So there are 3 levels of aggregation here. By increasing granularity, it's total over the year, then total by facility over the year, and then finally total by facility by month within that year. So this is a bit breaking the mold of what SQL usually does, in the sense that SQL is not designed to return a single result with multiple levels of aggregation, so we will need to be a bit creative around that. But let us start now with the lowest level of granularity. Let's get this part right, facility ID and month, and then we'll build on top of that. So the table that I need is in the bookings table. And first question, do I need to filter this table? Yes, because I'm only interested in the year 2012. So we have seen that we can use the extract function to get the year out of a timestamp, which would be start time. And we can use this function in a where filter. And what this function will do is that it will go to that timestamp, and then we'll get an integer out of it. It will get a number. And then we can check that this is the year that we're interested in. And let's do a quick sanity check to make sure this worked. So I will get some bookings here, and they will all be in the year 2012. Next, I need to define my grouping, right? So I will need to group by facility ID, but then I will also need to group by month. However, I don't actually have a column named month in this table, so I need to calculate it. I can calculate it once again with the extract function, so I can say extract month from start time, and once again this will go to the start time and spit out a integer, which for this first row would be 7. And as you know, in the group by I can select a column, but I can also select an operation over a column, which works just as well. Now after grouping, I cannot do select star anymore, but I want to see the columns that I have grouped by. And so let us do a quick sanity check on that. It looks pretty good. I get the facility ID and the month. and I can actually label this month. And next, I simply need to take the sum over the slots within each facility and within each month. And when I look at this, I have my first level of granularity, and you can see that the first row corresponds to the expected result. Now I need to add the next level of granularity, which is the total within each facility. So can you think of how can I add that next level of granularity to my results? The key insight is to look at this expected results table and to see it as multiple tables stacked on top of each other. One table is the one that we have here, and this is total by facility month. A second table that we will need is the total by facility, and then the third table that we will need is the overall total, which you could see here at the bottom. And how can we stack multiple tables on top of each other? With a union statement, right? Union will stack all the rows from my tables on top of each other. So now let us compute the table which has the total by facility, and I will actually copy paste what I have here, and I just need to remove a level of grouping, right? So if I do this, I will not group by month anymore, and I will not group by month anymore. And once I do this, I get an error. Union query must have the same number of columns. So do you understand this error here? So I will write a bit to show you what's happening. So how does it work when we union two tables? Let's say the first table in our case is facility ID, month, and then slots. And then the second table, if you look here, it's facility ID and then slots. Now when you union these two tables, SQL assumes that you have the same number of columns and that the ordering is also identical. So here we are failing because the first table has 3 columns and the second table has only 2. And not only we are failing because there's a numbers mismatch, but we are also mixing the values of month and slots. Now this might work because they're both integers, so SQL won't necessarily complain about this, but it is logically wrong. So what we need to do is to make sure that when we're unioning these two tables, we have the same number of columns and the same ordering as well. But how can we do this given that the second table does indeed have 1 column less, it does have less information? So what I can do is to put null over here. So what happens if I do select null? This will create a column of constant value, which is a column of all nulls. And then the structure will become like this. Now when I union, first of all, I'm going to have the same number of columns, so I'm not going to see this error again that we have here. And second, in the facility ID is going to be mixed with the facility ID, slots is going to be mixed with slots, which is all good. And then month is going to be mixed with null, which is what we want, because in some cases we will have the actual month, and in some cases we won't have anything. So I have added null over here, and I am unioning the tables. And if I run the query, I can see that I don't get any error anymore, and this is what I want. So I can tell that this row is coming from the second table because it has null in the value of month. And so it's showing the total slots for facility 0 in every month. Whereas this row came from the upper table because it's showing the sum of slots for a facility within a certain month. So this achieves the desired result. Next, we want to compute the last level of granularity, which is the total. So once again, I will select my query over here, and I don't even need to group by anymore, right? Because it's the total number of slots over the whole year. So I can simply say sum of slots as slots and remove the grouping. Next, I can add the union as well, so that I can keep stacking these tables. And if I run this, I get the same error as before. So going back to our little text over here, we are now adding a third table, and this table only has slots. And of course, I cannot, this doesn't work because there's a mismatch in the number of columns. And so the solution here is to also add a null column here and a null column here. And so I have the same number of columns, and slots gets combined with slots, and everything else gets filled with null values. And I can do it here, making sure that the ordering is correct. So I will select null, null, and then sum of slots. And if I run this query, I can see that the result works. The final step is to add ordering sorted by ID and month. So at the end of all of these unions, I can say order by facility ID month. And I finally get my result. So this is now the combination of three different tables stacked on top of each other that show different levels of granularity. And as you can see here in the schema, we added null columns to two of these tables just to make sure that they have the same number of columns and that they can stack up correctly. And now if we look again at the whole query, we can see that there are actually three select statements in this query, meaning three tables, which are calculated and then finally stacked with union. And all of them, they do some pretty straightforward aggregation. The first one aggregates by facility ID and month after extracting the month. The second one simply aggregates by facility ID. And the third one gets the sum of slots over the whole data without any grouping. And then we are adding the null constant columns here to make the column count match. And it's also worth it to see this in our map of the SQL operations. So here you can see that this order is actually repeating for every table. So for each of our three tables, we are getting our data, and then we are running a filter to keep the year 2012. And then we do a grouping and compute an aggregation and select the columns that we need, adding null columns when necessary. And then it repeats all over, right? So for the second table, again, the same process. For the third table, the same process, except that in the third table, we don't group by. And then when all three tables are done, the union runs. The union runs and stacks them all up together. And now instead of three tables, I only have one table. And after the union has run, now I can finally order my table and return the result. List the total hours booked per named facility. So we want to get the facility ID and the facility name and the total hours that they've been booked, keeping in mind that what we have here are number of slots for each booking, and a slot represents 30 minutes of booking. Now to get my data, I will need both the bookings table and the facilities table, because I need both the information on the bookings and the facility name. So I will get the bookings table and the facilities table. And join them together. Next, I don't really need to filter on anything, but I need to group by facility. So I will group by facility ID, and then I also need to group by facility name, otherwise I won't be able to use this in the select part. And now I can select these two columns. And to get the total hours, I will need to get the sum of the slots, so I can get the total number of slots within each facility. And I will need to divide this by 2, right? So let's see what that looks like. Now, superficially, this looks correct, but there's actually a pitfall in here. And to realize the pitfall, I will take some slots as well before dividing it by 2. And you can see it already in the first row. 911 divided by 2 is not quite 455. So what is happening here? The thing is that in Postgres, when you take an integer number, such as some slots, the sum of the slots is an integer number, and you divide by another integer, Postgres assumes that you are doing integer division, and since you are dividing two integers, it returns an integer as well. So that means that that the solution is not exact if you are thinking in floating point numbers. And the solution for this is that at least one of the two numbers needs to be a floating point number. And so we can turn 2 into 2.0. And if I run this, I now get the correct result. So it's important to be careful with integer division in Postgres. It is a potential pitfall. Now, what I need to do is to reduce the number of zeros after the comma. So I need some sort of rounding. And for this, I can use the round function, which looks like this. And this is a typical function in SQL. And how it works is that it takes two arguments. The first argument is a column. And actually, this is the column, right? This whole operation. And then the second argument is how many figures do you want to see after the zero? After the comma, sorry. So now I can clean this up a bit. Label this as total hours. And then I will need to order by facility ID. And I get my result. So nothing crazy in here really. We source our data from a join, which is this part over here. And then we group by two columns. We select those columns and then we sum over the slots, divide, making sure to not have integer division. So we use one of the numbers becomes a floating point number, and we round the result of this column. List each member's first booking after September 1st, 2012. So in order to get our data, where does our data live? We need the data about the member, and we also need data about their bookings. So the data is actually in the members and bookings table. So I will quickly join on these tables. And we now have our data. Do we need a filter on our data? Yes, because we only want to look after September 1st, 2012. So we can say where start time is bigger than, and it should be enough to just provide the date like this. Now in the result, we need the member's surname and first name and their memory ID. And then we need to see the first booking in our data. meaning the earliest time. So again, we have an aggregation here. So in order to implement this aggregation, I need to group by all of these columns that I want to call. So surname, first name, and member ID. Now that I have grouped by these columns, I can select them. So now I have grouped by each member, and now I have all the dates for all their bookings after September 1st, 2012. And now, how can I look at all these dates and get the earliest date? What type of aggregation do I need to use? I can use the mean aggregation, which will look at all of the dates and then compress them to a single date, which is the smallest date. And I can call this start time. Finally, I need to order by member ID. And I get the result that I needed. So this is actually quite straightforward. I get my data by joining two tables. I make sure I only have the data that I need by filtering on the time period. And then I group by all the information that I want to see for each member. And then within each member, I use mean to get the smallest date, meaning the earliest date. Now I wanted to give you a bit of an insight into the subtleties of how SQL compares timestamps and dates, because the results here can be a bit surprising. So I wrote 3 logical expressions here for you, and your job is to try to guess if either of these 3 expressions will be true or false. So take a look at them and try to answer that. As you can see, what we have here is a timestamp that indicates the 1st of September, 8 o'clock. Whereas here we have simply the indication of the date, the 1st of September. And the values are the same in all 3, but my question is, are they equal? Is this greater or is this smaller? So what do you think? I think the intuitive answer is to say that in the first case, we have September 1st on one side, September 1st on the other. They're the same day, so this ought to be true. Whereas here, we have, again, the same day on both sides, so this is not strictly bigger than the other one, so this should be false. And it is also not strictly smaller, so this would be false as well. Now let's run the query and see what's actually happening. Right, so what we see here is that we thought this would be true, but it's actually false. We thought this would be false, but it's actually true. And this one is indeed false. So are you surprised by this result, or is it what you expected? If you are surprised, can you figure out what's going on here? Now, what is happening here is that you are running a comparison between 2 expressions which have a different level of granularity. The one on the left is showing you day, hour, minutes, seconds, and the one on the right is showing you the date only. In other words, the value on the left is a timestamp, whereas the value on the right is a date. So different levels of precision here. Now, to make the comparison work, SQL needs to convert one into the other. It needs to do something that is known technically as implicit type coercion. What does it mean? Type is the data type, right? So either timestamp or date. Type coercion is when you take a value and you convert it to a different type. And it's implicit because we haven't asked for it, and SQL has to do it on its own behind the scenes. And so how does SQL choose which one to convert into the other? The choice is based on, let's keep the one with the highest precision and convert the other. So we have the timestamp with the higher precision on the left, and we need to convert the date into the timestamp. This is how SQL is going to handle this situation. It's going to favor the one with the highest precision. Now, in order to convert a date to a timestamp, what SQL will do is that it will add all zeros here. So this will basically represent the very first second of the day of this September 1st, 2012. Now we can verify what I just showed you. I'm going to comment this line and I'm going to add another logical expression here, which is taking the timestamp representing all zeros here and then setting it equal to the date right here. So what do we expect to happen now? We have two different types. There will be a type coercion, and then SQL will take this value on the right and turn it into exactly this value on the left. Therefore, after I check whether they're equal, I should get true here. Turns out that this is true, but I need to add another step, which is to convert this to a timestamp. And after I do this, I get what I expected, which is that this comparison here is true. So what this notation does in Postgres is that it does the type coercion, taking this date and forcing it into a timestamp. And I'll be honest with you, I don't understand exactly why I need to do this here. I thought that this would work simply by taking this part over here, but I also need to somehow explicitly tell SQL that I want this to be a timestamp. Nonetheless, this is the insight that we needed here, and it allows us to understand why this comparison is actually false. Because we are comparing a timestamp for the very first second of September 1st with a timestamp that is the first second of the 8th hour of September 1st, and so it fails. And we can also see why on this line the left side is bigger than the right hand side, and this one did not actually fool us, so we're good with that. So, long story short, if you're just getting started, you might not know that SQL does this implicit type coercion in the background, and this dates comparison might leave you quite confused. Now, I've cleaned the code up a bit, and now the question is, what do we need to do with the code in order to match our initial intuition? So, what do we need to do such that this line is true and the second line is false, and this one is still false, so we don't have to worry about it? Well, since the implicit coercion turns the date into a timestamp, we actually want to do the opposite. We want to turn the timestamp into a date. So it will be enough to do the type coercion ourselves and transform this into dates. Like this. And when I run this new query, I get exactly what I expected. So now I'm comparing at the level of precision or granularity that I wanted. I'm only looking at the date. So I hope this wasn't too confusing. I hope it was a bit insightful and that you have a new appreciation for the complexities that can arise when you work with dates and timestamps in SQL. Produce a list of member names with each row containing the total member count. Let's look at the expected results. We have the first name and the surname for each member, and then every single row shows the total count of members. there are 31 members in our table. Now, if I want to get the total count of members, I can take the members table and then select the count. And this will give me 31, right? But I cannot add first name and surname to this. I will get an error because count star is an aggregation and it takes all the 31 rows and produces a single number, which is 31, while I'm not aggregating first name and surname. So the standard aggregation doesn't work here. I need an aggregation that doesn't change the structure of my table and that works at the level of the row. And to have an aggregation that works at the level of the row, I can use a window function. And the window function looks like having an aggregation followed by the keyword over and then the definition of the window. So if I do this, I get the count at the level of the row. And to respect the results, I need to change the order a bit here. And I get the result that I wanted. So a window function has these two main components, an aggregation and a window definition. In this case, the aggregation counts the number of rows and the window definition is empty, meaning that our window is the entire table. And so this aggregation will be computed over the entire table and then added to each row. There are far more details about window functions and how they work in my mental models course. Produce a numbered list of members ordered by their date of joining. So I will take the members table and I will select the first name and surname. And to produce a numbered list, I can use a window function with the row number aggregation. So I'll say row number over. So row number is a special aggregation that works only for window functions. And what it does is that it numbers the rows monotonically, giving a number to each, starting from 1 and going forward. And it never assigns the same number to 2 rows. And in the window, you need to define the ordering for the numbering. So what is the ordering in this case? It's defined by the join date. And by default, it's ascending. So that's good. And we can call this row number. And we get the results we wanted. And again, you can find a longer explanation for this with much more detail about window functions and row number in the mental models course. Output the facility ID that has the highest number of slots booked again. So we've already solved this problem in a few different ways. Let's see a new way to solve it. So we can go to our bookings table and we can group by facility ID, and then we can get the facility ID in our select, and then we could sum on slots to get the total slots booked for each facility. And since we're dealing with window functions, we can also rank facilities based on the total slots that they have booked. And this would look like rank over order by sum slots descending. And we can call this RK for rank. And if I order by sum slots descending, I should see that my rank works as intended. So we've seen this in the mental models course. You can think of rank as deciding the outcome of a race. So the person who did the most in this case gets rank 1, and then everyone else gets rank 2, 3, 4. But if there were two candidates that got the same score, the highest score, they would both get rank 1 because they would both have won the race, so to speak. And the rank here is defined over the window of the sum of slots descending. So that is what we need. And next, to get all the facilities that have the highest score, we could wrap this into a common table expression and then take that table and then select the facility ID, and we can label this column total. Then we will get total and filter for where ranking is equal to 1. And we get our result. Aside from how rank works, the other thing to note in this exercise is that we can define the window based on an aggregation. So in this case, we are ordering the elements of our window based on the sum of slots. And if we look at our map over here, we can see that we get the data, we have our group by, we have the aggregation, and then we have the window. So the window follows the aggregation, and so based on our rules, the window has access to the aggregation and it's able to use it. Rank members by rounded hours used. So the expected results are quite straightforward. We have the first name and the surname of each member. We have the total hours that they have used, and then we are ranking them based on that. So the information for this result, where is it? We can see that it's in the members and bookings tables. And so we will need to join on these two tables. Members mems, join bookings book on mem ID. And that's our join. Now we need to get the total hours, so we can group by our first name, and we also need to group by the surname because we will want to display it. And now we can select these two columns, and we need to compute the total hours. So how can we get that? For each member, we know the slots that they got at every booking. So we need to get all those slots, sum them up. And every slot represents a 30-minute interval, right? So to get the hours, we need to divide this value by 2. And remember, if I take an integer, like sum of slots, and divide by 2, which is also an integer, I'm going to have integer division. So I won't have the part after the comma in the result of the division, and that's not what I want. So instead of saying divide by 2, I will say divide by 2.0. So let's check how the data looks like. This is looking good now, but if we read the question, we want to round to the nearest 10 hours. So 19 should probably be 20. 115 should probably be 120 because I think that we round up when we have 15, and so on, as you can see here in the result. So how can we do this rounding? Well, we have a nifty round function, which as the first argument takes the column with all the values, and the second argument we can specify how do we want the rounding. And to round to the nearest 10, you can put -1 here. So actually, let's keep displaying the total hours as well as the rounded value to make sure that we're doing it correctly. So as you can see, we are indeed rounding to the nearest 10. So this is looking good. And to understand the reason why I used -1 here and how the rounding function works, I will have a small section about it when we're done with this exercise. But meanwhile, let's finish this exercise. So now I want to rank all of my rows based on this value here that I have computed. And since this is an aggregation, it will already be available to a window function, right? Because in the logical order of operations, aggregation happen here and then windows happen afterward, and they have access to the data from the aggregation. So it should be possible to transform this into a window function. So think for a moment of how we could do that. So a window function has its own aggregation, which in this case is a simple rank. And then we have the over part, which defines the window. And what do we want to put in our window? In this case, we want to order by, let's say, our rounded hours. And we want to order descending because we want the guest, the member with the highest hours, to have the best rank. But clearly we don't have a column called rounded hours. What we have here is this logic over here. So I will substitute this name with my actual logic. And I will get my actual rank. And now I can delete this column here that I was just looking at. And I can sort by rank, surname, first name. Small error here, I actually do need to show the hour as well. So I need to take this logic over here again and call these hours. And I finally get my result. So to summarize what we are doing in this exercise, we're getting our data by joining these two tables, and then we're grouping by the first name and the surname of the member, and then we are summing over the slots for each member, dividing by 2.0 to make sure we have an exact division, and using the rounding function to round down to the nearest hour. And so we get the hours. And we use the same logic inside a window function to have a ranking such that the members with most hours get rank of 1, and then the one with the second most hours get rank of 2, and so on, as you can see here in the result. And I am perfectly able to use this logic to define the ordering of my window, because window functions can use aggregations, as seen in the logical order of SQL operations here, because window functions occur after aggregations. And that's it. Then we just order by the required values and get our results. Now here's a brief overview of how rounding works in SQL. Now rounding is a function that takes a certain number and then returns an approximation of that number, which is usually easier to parse and easier to read. And you have the round function, and it works like this. The first argument is a value, and it can be a constant, as in this case, so we just have a number, or it can be a column, in which case it will apply the round function to every element of the column. And the second argument specifies how we want the rounding to occur. So here you can see the number from which we start, and the first rounding we apply has an argument of 2. So this means that we really just want to see two numbers after the decimal. So this is what the first rounding does, as you can see here. And we round down or up based on whether the values are equal or greater than 5, in which case we round up, or smaller than 5, in which case we round down. So in this first example, 2 is lesser than 5, so we just get rid of it. And then we have 8. 8 is greater than 5, so we have to round up. And so when we round up, this 79 becomes an 80. And this is how we get to this first round over here. Then we have round with an argument of 1, which leaves one place after the decimal. and which is this result over here. And then we have round without any argument, which is actually the same as providing an argument of 0, which means that we really just want to see the whole number. And then what's interesting to note is that the rounding function can be generalized to continue even after we got rid of all the decimal part by providing negative arguments. So round with an argument of -1 really means that I want to round this number to the nearest 10. So you can see here that from 48,292 we end up at 48,290, going to the nearest 10. Rounding with a value of -2 means going to the nearest 100. So 290, the nearest 100 is 300, right? So we have to round up. And so we get this. -3 means round to the nearest 1,000. So if you look at here, we have 48,300. And so the nearest 1,000 to that is 48,000. -4 means the nearest 10,000. So given that we have 48,000, the nearest 10,000 is 50,000. And finally, round -5 means round to the nearest 100,000. And given that we have 48,000, the nearest 100,000 is actually 0. And from now on, as we keep going negatively, we will always get 0 on this number. So this is how rounding works in brief. It's a pretty useful function. Not everyone knows that you can provide it negative arguments. Actually, I didn't know. And then when I did the first version of this course, commenter pointed it out. So shout out to him. Don't know if he wants me to say his name. But hopefully now you understand how rounding works and you can use it in your problems. Find the top 3 revenue generating facilities. So we want a list of the facilities that have the top 3 revenues, including ties. This is important. And if you look at the expected results, we simply have the facility name and a bit of a giveaway of what we will need to use, the rank of these facilities. So there's this other exercise that we did a while back, which is find the total revenue of each facility. And from this exercise, I have taken the code that allows us to get to this point where we see the name of the facility and the total revenue for that facility. And you can go back there to that exercise to see in detail how this code works. But in brief, we are joining the bookings and facilities tables, and we are grouping by facility name, and then we are getting that facility name. And then within each booking, we are computing the revenue by taking the slots and using a case when to choose whether to use guest cost or member cost. And so this is how we get the revenue for each single booking. And now, given that we grouped by facility, we can sum all of these revenues to get the total revenue of each facility. And this is how we get to this point. Given this partial result, all that's left to do now is to rank these facilities based on their revenue. So what I need here is a window function that will allow me to implement this ranking. And this window function would look something like this. I have a rank, and why is rank the right function even though they sort of gave it away? Because if you want the facilities who have the top revenues, including ties, you can think of it as a race. All facilities are racing to get to the top revenue. And then if 2 or 3 or 4 facilities get that top revenue, if there are more in the top position, you can't arbitrarily say, oh, you are first and they are second. You have to give them all the rank 1 because you have to tell them, recognize that they are all first. So these type of problems call for a ranking solution. So our window function would use rank as the aggregation, and then we need to define our window. And how do we define our window? We define the ordering for the ranking here. So we can say order by revenue descending, such that the highest revenue will get rank 1, the next highest will get rank 2, and so on. Now, this will not work because I don't have the revenue column, right? I do have something here that is labeled as revenue, but the ranking part will not be aware of this label. However, I do have the logic to compute the revenue. So I could take the logic right here and paste it over here. And I'll add a comma. Now, this is not the most elegant looking code, but let's see if it works. And we need to order by revenue descending to see it in action. And if I order by revenue descending, you can in fact see that the facility with the highest revenue gets rank 1, and then it goes down from there. So now I just need to clean this up a bit. First, I will remove the revenue column, and then I will remove the ordering. And what I need here for the result is to keep only the facilities that have rank of 3 or smaller, so ranks 1, 2, 3. And there's actually no way to do it in this query, so I actually have to wrap this query into a common table expression, and then take that table and say select star from T1 where rank is smaller or equal to 3, and I will need to order by rank ascending here, and I get the result I needed. So what happened here, we built upon the logic of getting the total revenue for each facility, and again we saw that in the previous exercise. And then what we did here is that we added a rank window function, and within this rank we order by this total revenue. So this might look a bit complex, but you have to remember that when we have many operations that are nested, you always start with the innermost operation and move your way up from there. So the innermost operation is a case when, which chooses between guest cost and member cost, and then multiplies it by slots. And this inner operation over here is calculating the revenue for each single booking. The next operation is an aggregation that takes that revenue for each single booking and sums these revenues up to get the total revenue by each facility. And finally, the outermost operation is taking the total revenue for each facility, and it's ordering them in descending order in order to figure out the ranking. And the reason all of this works, we can go back to our map of SQL operations. You can see here that after getting the table, the first thing that happens here is the group by and then the aggregations. And here is where we sum over the total of revenue. And after the aggregation is completed, we have the window function. So the window function has access to the aggregation and can use them when defining the window. And finally, after we get the ranking, we have no way of isolating only the first 3 ranks in this query, so we need to do it with a common table expression. And if you look here, back to our map, this makes sense because what components do we have in order to filter our table, in order to only keep certain rows? We have the where, which happens here very early, and we have the having, and they both happen before the window. So after the window function, you actually don't have another filter, so you need to use a common table expression. Classify facilities by value. So we want to classify facilities into equally sized groups of high, average, and low based on their revenue. And the result, you can see it here. For each facility, it's classified as high, average, or low. And the point is that we decided at the beginning that we want 3 groups, and this is arbitrary. We could have said we want 2 groups, or 5, or 6, or 7, but we have 3. And then all the facilities that we have are distributed equally within these groups. So because we have 9 facilities, we get 3 facilities within each group. And I can already tell you that there is a special function that will do this for us. So we will not go through the trouble of implementing this manually, which could be pretty complex. So I have copied here the code that allows me to get the total revenue for each facility. And we have seen this code more than one time in past exercises. So if you're still not clear about how we can get to this point, check out the previous exercises. So what we did in the previous exercise was rank the facilities based on the revenue. And how we did that is that we took the ranking window function and then we defined our window as order by revenue descending. Except that we don't have a revenue column here, but we do have the logic to compute the revenue. So we can just get this logic and paste it in here. And when I run this, I will get a rank for each of my facilities, where the biggest revenue gets rank 1, and then it goes up from there. Now the whole trick to solve this exercise is to replace the rank aggregation with an entile aggregation and provide here the number of groups in which we want to divide our facilities. And if I run this, you see that I get what I need. The facilities have been equally distributed into 3 groups, where group number 1 has the facilities with the highest revenue, and then we have group number 2, and finally group number 3, which has the facilities with the lowest revenue. And to see how this function works, I will simply go to Google and say Postgres entile. And the second link here is the Postgres documentation, and this is the page for window functions. So if I scroll down here, I can see all of the functions that I can use in window functions, and you will recognize some of our old friends here: row number, rank, dense rank, and here we have entile. And what we see here is that entile returns an integer ranging from 1 to the argument value, and the argument value is what we have here, which is the number of buckets, dividing the partition as equally as possible. So we call the entile function and we provide how many buckets we want to divide our data into, and then the function divides the data as equally as possible into our buckets. And how will this division take place? That depends on the definition of the window. In this case, we are ordering by revenue descending. And so this is how the entile function works. So we just need to clean this up a bit. I will remove the revenue part because that's not required from us. And I will call this entile quite simply. And now I need to add a label on top of this entile value, as you can see in the results. So to do that, I will wrap this into a common table expression. And when I have a common table expression, I don't need the ordering anymore. And then I can select from the table that I have just defined. And what do I want to get from this table? I want to get the name of the facility, and then I want to get the entile value with a label on top of it. So I will use a case when statement to assign this label. So case when entile equals 1, then I will have high. When entile equals 2, then I will have average. Else I will have low. end the case and call this revenue. And finally, I want to order by entile, so the results are first showing high, then average, then low, and also by facility name. And I get the result that I wanted. So to summarize, this is just like the previous exercise, except that we use a different window function, because instead of rank, we use entile so that we can bucket our data. And in the window, like we said in the previous exercise, there's a few nested operations, and you can figure it out by going to the deepest one and moving upwards. So the first one picks up the guest cost or member cost, multiplies it by slots, gets the revenue for each single booking. The next one aggregates on top of this within each facility, so we get the total revenue by facility. And then we use this, we order by revenue descending. This defines our window. And this is what the bucketing system uses to distribute the facilities in each bucket based on their revenue. And then finally, we need to add another layer of logic. Here we need to use a common table expression so that we can label our percentile with the required text labels. Calculate the payback time for each facility. So this requires some understanding of the business reality that this data represents. So if we look at the facilities table, we have an initial outlay, which represents the initial investment that was put into getting this facility. And then we also have a value of monthly maintenance, which is what we pay each month to keep this facility running. And of course, we will also have a value of monthly revenue for each facility. So how can we calculate the amount of time that each facility will take to repay its cost of ownership? Let's actually write it down so we don't lose track of it. We can get the monthly revenue of each facility, but what we're actually interested in is the monthly profit, right? And to get the profit, we can subtract the monthly maintenance for each facility. So revenue minus expenses equals profit. And when we know how much profit we make for the facility each month, we can take the initial investment and divide it by the monthly profit. And then we can see how many months it will take to repay the initial investment. So let us do that now. And what I have done here, once again, I copied the code to calculate the total revenue for each facility. And we have seen this in the previous exercises, so you can check those out if you still have some questions about this. And now that we have the total revenue for each facility, we know that we have 3 complete months of data so far. So how do we get to this, to the monthly revenue? It's as simple as dividing all of this by 3, and I will say 3.0 so we don't have integer division, but we have proper division, you know. And I can call this monthly revenue. And now the revenue column does not exist anymore, so I can remove the order by. And here I can see the monthly revenue for each facility. And now from the monthly revenue for each facility, I can subtract the monthly maintenance. And this will give me the monthly profit. But now we get this error, and can you figure out what this is about? Monthly maintenance does not appear in the group by clause. So what we did here is that we grouped by facility name, and then we selected that, which is fine. And all the rest was aggregation. So remember, as a rule, when you group by, you can only select the columns that you have grouped by and aggregations. And monthly maintenance is not an aggregation, so in order to make it work, we need to add it to the group by statement over here. And now I get the monthly profit. And finally, the last step that I need to take is to take the initial outlay and divide it by all of the rest that we have computed until now. And we can call these months, because this will give us the number of months that we need in order to repay our initial investment. And again, we get the same issue. Initial outlay is not an aggregation, does not appear in the group by clause. And easy solution, we can just add it to the group by clause. So something is pretty wrong here. The values look pretty weird. So looking at all this calculation that we have done until now, can you figure out why the value is wrong? The issue here is related to the order of operations. Because we have no round brackets here, the order of operation will be the following. Initial outlay will be divided by the total revenue, then it will be divided by 3.0, and then out of all of these we will subtract monthly maintenance. But that's not what we want to do, right? What we want to do is to take initial outlay and divide it by everything else, which is the profit. So I will add round brackets here and here. And now we get something that makes much more sense, because first we execute everything that's within these round brackets and we get the monthly profit, and then all of it we divide initial outlay by. And then what we want to do is to order by facility name. So I will add it here. And we get the result. So quite a representative business problem, calculating a revenue and profits and time to repay initial investment. And overall, it's just a bunch of calculations starting from the group by that allows us to get the total revenue for each booking. We sum those revenues to get the total revenue for each facility, divide by 3 to get the monthly revenue, subtract the monthly expenses to get the monthly profit, and then take the initial investment and divide by the monthly profit, and then we get the number of months that it will take to repay the facility. Calculate a rolling average of total revenue. So for each day in August 2012, we want to see a rolling average of total revenue over the previous 15 days. Rolling averages are quite common in business analytics, and how it works is that if you look at August 1st, this value over here is the average of daily revenue for all facilities over the past 15 days, including the day of August 1st. And then this average is rolling by one day or sliding by one day every time, so that the next average is the same one, except it has shifted by one day because now it includes the 2nd of August. So let's see how to calculate this. And in here I have basic code that calculates the revenue for each booking, and I've taken this from previous exercises, so if you have any questions, check those out. And what we have here is the name of each facility and the revenue for each booking. So each row here represents just a single booking. So this is what we had until now, but if you think about it, we're not actually interested in seeing the name of the facility because we're going to be summing up over all facilities. We're not interested in the revenue by each facility, but we are interested in seeing the date in which each booking occurs because we want to aggregate within the date here. So to get the date, I can get the start time field from bookings, And because this is a timestamp, so it shows hours, minutes, seconds, I need to reduce it to a date. And what I get here is that for, again, each row is a booking, and for each booking I know the date on which it occurred and the revenue that it generated. Now for the next step, I need to see the total revenue over each facility within the date, right? So this is a simple grouping. So if I group by this calculation over here, which gives me my date, I can then get the date. And now I have compressed all the different occurrences of dates to unique values, right? One row for every date. And now I need to compress as well all these different revenues for each date to a single value. And for that, I can put this logic inside the sum aggregation as we have done before. And this will give me the total revenue across all facilities for each day. And we have it here. For the next step, my question for you is, how can I see the global average over all revenues on each of these rows? So that is a row level aggregation that doesn't change the structure of the table, and that's a window function, right? So I can have a window function here that gets the average of revenue over, and for now I can leave my window definition open because I will look at the whole table. However, revenue will not work because revenue is just a label that I've given on this column, but this part here is not aware of the label. I don't actually have a revenue column at this point. But instead of saying revenue, I could actually copy this logic over here, and it would work because the window function occurs after computing the aggregation, so the window function is aware of it. So this should work. And now for every row, I see the global average over all the revenues by day. Now for the next step, I would like to first order by date, ascending. So we have it here in order. And my next question for you is, how can we make this a cumulative average? So let's say that our rows are already ordered by date. And how can I get the average to grow by date? So in the first case, the average would be equal to the revenue because we only have one value. On the second day, the average would be the average of these two values, so all the values we've seen until now. On the third day, it would be the average of the first three values, and so on. How can I do that? The way that I can do that is that I can go to my window definition over here, and I can add an ordering, and I can order by date. But of course, the column date does not exist because that's a label that will be assigned after all this part is done. Window function is not aware of labels, but again, window function works great with logic. So I will take the logic and put it in here. And now you can see that I get exactly what I wanted. On the first row, I get the average is equal to the revenue. And then as it grows, we only look at the current revenue and all the previous revenues to compute the average. But we don't look at all of the revenues. So on the second row, we have the average between this revenue over here and this one over here. And then on the third row, we have the average between these three revenues and so on. Now you will realize that we are almost done with our problem. And the only piece that's missing is that right now, if I pick a random day within my dataset, say this one, the average here is computed over all the revenues from the previous days. So all the days in my data that lead up to this one, they get averaged and we compute this revenue. And what I want to do to finish this problem is that instead of looking at all the days, I only want to look 15 days back. So I need to reduce the maximum length that this window can extend in time from unlimited to 15 days back. Now, here is where it gets interesting. So what we need to do is to fine-tune the window definition in order to only look 15 days back. And with window functions, we do have the option to fine-tune the window. And it turns out that there's another element to the window definition which is usually implicit. It's usually not written explicitly, but it's there in the background. And it's the rows part. So I will now write rows between unbounded preceding and current rows. Row. Now, what the rows part does is that it defines how far back the window can look and how far forward the window can look. And what we see in this command is actually the standard behavior. Is the thing that happens by default, which is why we usually don't need to write it. And what this means is that it says look as far back in the past as you can, look as far back as you can based on the ordering, and the current row. So this is what we've been seeing until now, and if I now run the query again after adding this part, you will see that the values don't change at all because this is what we have been doing until now. So now instead of unbounded preceding, I want to look 14 rows back plus the current row, which together makes 15. And if I run this, my averages change because I'm now looking I'm now averaging over the current row and the 14 previous rows. So the last 15 values. And now what's left to do to match our result is to remove the actual revenue over here and call this revenue. And finally, we're only interested in values for the month of August 2012. So we need to add a filter, but we cannot add a filter in this table definition here because if we added a where filter here, isolating the period for August 2012, can you see what the problem would be? If my data could only see revenue starting from the 1st of August, it wouldn't be able to compute the rolling average here because to get the rolling average for this value, you need to look 2 weeks back, and so you need to look into July. So you need all the data to compute the rolling revenue, and we must filter after getting our result. So what that looks like is that we can wrap all of this into a common table expression, and we won't need the order within the common table expression anymore. And then selecting this, we can filter to make sure that the date fits in the required period. So we could truncate this date at the month level and make sure that it is equal, that the truncated value is equal to the month of August. And we have seen how date trunc works in the previous exercises. And then we could select all of our columns and order by date. I believe we may have an extra small error here because I kept the partial where statement. And if I run this, I finally get the result that I wanted. So a query that was a bit more complex, it was the final boss of our exercises. So let's summarize it. We get the data we need by joining booking and facility. And then we are getting the revenue for each booking. That is this multiply slots by either guest cost or member cost, depending on whether the member is a guest or not. This is getting the revenue within each booking. Then we are grouping by date, which you see over here, and summing all of these revenues that we computed so that we get the total revenue within each day for all facilities. Then the total revenue for each day goes into a window function, which computes an aggregation at the level of each row. And the window function computes the average for these total revenues within a specific window. And the window defines an ordering based on time, so the ordering based on date. And the default behavior of the window would be to look at the average for the current day and all the days that precede up until the earliest date. And what we're doing here is that we are fine-tuning the behavior of this function by saying, hey, don't look all the way back in the past, only look at 14 rows preceding plus the current row, which means that given the time ordering, we compute the average over the last 15 values of total revenue. And then finally, we wrap this in a common table expression and we filter so that we only see the rolling average for the month of August, and we order by date. And that were all the exercises that I wanted to do with you. I hope you enjoyed it. I hope you learned something new. As you know, there are more sections in here that go more into depth into date functions and string functions and how you can modify data. I really think you can tackle those on your own. These were the essentials ones that I wanted to address. And once again, thank you to the author of this website, Alistair Owens, who created this and made it available for free. I did not create this website, so you can just go here and without signing up or paying anything, you can just do these exercises. My final advice for you, don't be afraid of repetition. We live in the age of endless content, so there's always something new to do, but there's a lot of value to repeating the same exercises over and over again. When I was preparing for interviews, when I began as a data engineer, I did these exercises, and altogether I did them like maybe 3 or 4 times, and I found that it was really helpful to do the same exercises over and over again, because often I did not remember the solution and I had to think through it all over again, and it strengthened those learning patterns for me. So now that you've gone through all the exercises and seen my solutions, let it rest for a bit and then come back here and try to do them again. I think it will be really beneficial. In my course, I start from the very basics and I show you in depth how each of the SQL components work. I explore the logical order of SQL operations, and I spend a lot of time in Google Sheets simulating SQL operations in the spreadsheet, coloring cells, moving them around, making some drawings in Excalidraw so that I can help you understand in depth what's happening and build those mental models for how SQL operations work. This course was actually intended as a complement to that, so be sure to check it out.